Hi everyone. So in this video we are going to study about implicants. So generally this topic is a bit typical and people find it difficult to study, and generally questions are also asked from this particular topic because this is one of the finest topic of this chapter. So we will cover this complete topic in this video only, and you will be very comfortable in the end of the video. So just watch till the end, right? So like this hierarchy I have written, these are all the subsets. Like there will be one Boolean expression, subset of that will be implicant, subset of that will be prime implicant, and then there you will get essential prime implicant, redundant prime implicant, and selective prime implicant. So this is the most important one, essential prime implicant. If some question is coming from this particular chapter, then it would be coming from essential prime implicant only. So essential prime implicant, this is known as essential prime implicant. So that is very important. We will study one by one everything. We will study all the implicants one by one. So first let's start with implicant. What do you mean by implicant? You know what is a Boolean expression, right? This is a given Boolean expression. So what do you mean by implicant? Implicant is simply a subset of the given function. So 0, 1, 4, 6, 9, 12, 15, that is there. So 1 is there, 9 is there, 12 is there, 15 is there. So it is a complete subset. G1 is a complete subset of function f. That means this is an implicant. This is an implicant because it is a subset. What about this one? 0 is there, 6 is there, 12 is there. So this is also an implicant. Implicant. But what about this one? 0 is there, 1 is there, 4 is there, but 3 is not there. So this is not a subset. That means this is not a implicant. So implicant is simply a subset. Now the same example can be asked in this manner as well. Basically here minterms are given and here the expression is written. So what you need to do? You need to find the minterms. So you can find the minterms of this. How will you write down the minterms? A and C will be there as it is, and all the expression of B and D will come. Basically without bar it will come. Then one bar, other is not bar. Then one is not bar, other is bar. Then both are bar. So in that manner we can write. So what will be your minterms? So I can write 8, 4, 2, 1. Now let's write down from here. Let's write down from here. So this is 0, 1, 0, 1, 0. 1, 0, 1, 0. That means 10. What about this one? 1, 1, 1. 1, 1, 1. 14. What about this one? 1, 0, 1, 1. 11. What about this one? 1, 1, 1, 1. 15. So 10, 11, 14, 15. 10, 11, 14, 15. All are there. That means this is an implicant. This is an implicant. Implicant. What about this one? Can I write down the expression? Yes, I can write down. A bar B C D plus A bar B C bar D plus A bar B bar C bar D plus A bar B bar C bar D bar, right? All the expression of C is coming here, C bar. All the expression of D is coming here, D bar. So let's write down the minterms. As far as I remember, it will come 0, 1, 5, 7, but let's try. For this one, what it would be? 0, because all are 0. What about this one? This would be 1. What about this one? 4 plus 1, 5. And what about this one? 0, 1, 1, 7. So this is also an implicant, right? This is also an implicant. What about this? This is given in terms of POS. So first I will write down the max terms. I will write down the max term. So component of D will come. Also component of D bar will also come. Right? So what will be the max terms? So max term will be 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. Because this is POS form. So 0, 0, 1, 0, 0, 0, 1, 0, that means 2. 0, 0, 1, 0. Here 0, 0, 1, 1, that means 3. 2, 3. So what will be the min terms? Min terms will be a lot of numbers. 0 would be there, 1 will be there, 4 will be there, 5 will be there, 6 will be there, 7 will be there, 8 will be there. In that manner it will go till 12, 13, 14 and 15. And here only we can see that 4 is not there. This 4 is not there, right? So this is not an implicant. Not a implicant. Okay, so this is not an implicant. So this is the basic definition, just the subset has to be there. That is the meaning of implicant, right? Let's study about prime implicant. From here the important topic start. No one will ask you find the implicants. No one will ask you because there can be a lot of implicants, right? But let's study about prime implicants. So prime implicant basic definition is it is the best possible group. In one line if we need to say, I will just say it is the best possible group. Now you are not able to understand this. We will read these points later on, but let's start. Let's just say this function is given. What is this function? That minterms m 0, 1, 2, 3, 5, 7. You need to find the all possible prime implicants. So what you will do? What you will do? You will start with the best possible group, that means biggest group. Which is the biggest group here? Can I make a octet here? No, I cannot make a octet. Can I make a quad? Yes. Can I make another quad? Yes. Now there are possible pairs, right? This is one of the possible pair. This is also one of the possible pair. This is one of the possible pair. This is again more possible pairs are there. But you need to make sure that no pair should be made in between the biggest possible pair. That means if I make the pair between 1 and 5. So 1 and 5 both elements are there in this quad, right? So this is not a valid pair. If I make this pair which is 2 and 3. So 2 and 3 is available in this quad as well. This is quad 2 I am saying, and this is quad 1. So 1 and 5 is present in quad 2, the quad 1. In quad 1. This 2 and 7 is present in quad 1. 2 and 3 is present in quad 2. 1 and 3 is present in quad 2. 0 and 1 is present in quad 2. And this 0 and 2 will be present in quad 2. Already these are already present. So they are not prime implicants. Okay, these groups are not prime implicant. Look, this chapter has nothing to do with K-maps. Okay, don't confuse it with K-maps. It has nothing to do with K-maps. Right? So here, like if I was drawing K-maps only, then only I would have chosen these two groups. Here, prime implicants are these two groups only. So both conditions are same for this particular example, but for different examples it can change. We will solve a lot of examples. So let's try finding prime implicants in this particular group. So first I will make the biggest club, which is the quad I can see. Can I make another quad? No. Now I can make pairs, right? I can make this pair. I can make this pair. I can make this pair. I can make this pair, right? If I make single element, let's just say I make this element. So this is already there in the pair, right? This single element is already present in the pair, right? This single element. So I will not take single element in action. So first I will think of quad, then I will think of pair. That's it. Now, can you tell me how many implicants are there? Will you say 4 implicants are there? Sorry, how many prime implicants are there? Will you say 4 prime implicants are there? Because you will say that, sir, this is redundant. This is redundant with respect to K-map, but this particular topic has nothing to do with the K-maps. What did I tell you? First I will choose the biggest one, and then I will choose another one. What was the other condition? The other condition was that in between the groups you cannot make any other club. Let's just say I cannot make this club 5, 7. This club I cannot make. I cannot make this club 13, 15 because this 13, 15 club is there in the quad itself. Are you getting this point? This 13, 15 club is there in the quad itself, but this 12, 13, this I can take. Why I can take? Because 13 is there in the quad, but one of the element is not there in the quad. So the complete pair is not in the quad. If complete pair was in the bigger group, then I could not have taken it. So inside the bigger club, no further small clubs are allowed. No further small clubs should be there inside the bigger club. So whole club has to be there in the bigger club, then it will not be allowed. Otherwise it can be allowed. So one element is connected, so it is allowed. So how many prime implicants are there? 5. And in these 5, what all are? 4 pair and 1 quad. Can you write it down? Yes, I can write down. So first write down the quad. 5, 7, 13, 15. 5, 7, 13, 15. Let's write down the pairs now. 1 5 6 7 11 15 12 13. That's it. So, and what about 5 7? This will not be accepted because 5 7 is inside the quad, inside the bigger club. What about 13 15? 13 15 is also not accepted because 13 15 is also there in the bigger club, right? Let's see more examples. Let's take first, what is my target? See the biggest club. So biggest club, can I make a octet here? No. Can I make a 16 club? No. I can make a club of 4. So there you go. Can I make another club of 4? No. I can make club of 2 only. So 1 pair, 2 pair, 3 pair. Can I make this pair? No, this will not be accepted because whole pair was there in this quad only. Can I make this pair? No, I cannot make this pair. But how I can make this pair? Because one element is there in the quad, one element is there here. How can I make this pair? One element is there in the pair, but this element was alone. Now this element is alone, so this can make pairs with 10 and 8. 10 and 8. Right? Is there any other possible pair? Is there any other possible pair? No. Now you cannot say that, sir, that what is the need of this 8 12? Why are you taking this 8 12? In K-maps I would not have taken this 8 12, but here I will take. In K-maps I would not have taken this 5 7 13 15 as well, because this is redundant. Here I would not have taken 8 12 in the K-maps, but here I will take it. Why I will take it? Because I need to find all possible groups, making sure that no group is there in the bigger club. What is my target? My target is to make all possible group by making sure that no group is there in the bigger group. That's why I did not take 5 13 5 7, but I can take these because this element was alone. Here this element was already clubbed, but this element was alone. Here this element was already clubbed, but this can be clubbed with this one, right? Because both are not being clubbed in a single cell. If both were clubbed, in a bigger quad, then it would be a problem for me. But now it is not a problem. Slowly you will understand more points. Okay, slowly you will build it up. Now you might be thinking, sir, we are not able to grasp it, but slowly you will build. So one quad is there, and how many cells? How many pairs were there? 1 2 3 4 pairs were there. Am I missing out on anything? 1 2 3 4 4 pairs were there, right? So let's write down the quad first. 5 7 13 15. Now the pairs 12 13, right? 1 5 12 8. What else? 10 8 10. Okay, so these many pairs are there. Now you need to find maximum number of prime implicants in a 2 variable function. So 2 variable function means 4 cells. I need to find maximum number of prime implicants. If I write my 1 in this manner, so tell me how many prime implicants will be there? Only one, only this group. These groups will not be allowed. This group and this group, these groups will not be allowed, right? So what I need to do, if I remove this one, then how many groups I can make? 1 and 2. Can I make a group of single cell like this? No, because this cell is completely there in this pair. So only 2 groups are allowed. So here there are 2 prime implicants. Let's try thinking for 3. Okay, this I have already shown, but I should not show. So what will be our target? I should not make any quad. My target would be I should not make any quad. If I make a quad, then what will happen? If I make a quad, let's just say I write my ones in this manner. If I make a quad, then this would be one of the group, and then let's just say one is here, one is here. So this would be 2 and only 3 I am getting, because inside the quad I cannot make the pair. These two pairs I cannot make, and that would be my loss, because I need to find the maximum number of prime implicants. So how will I find that? How will I write down my ones? So I will start here. I will write 1 1. This will make me a pair. This one, this will also make me a pair. I can write one more 1 here, because again one more pair I will get. Can I write 1 here? No, because this will be a quad, so that I will ignore. Here I can write 1. Yes, I can write 1. Can I write 1 here? Because no, I cannot write, because this will make a quad. Can I write 1 here? No, I cannot write, because this will also make a quad, right? So, but this one will go alone, so I do not want that to happen. So what I can do, I can write this one here and then this one here. Is that a good thing? Okay. Is there any quad? My target is to avoid any quad, so no quads are there. So let's see how many prime implicants are there. One of the element can be paired. 2, one of the element can be paired. 3, one of the element can be paired. 4, 5, one of the element can be paired, and 6. Now you will not say that, sir, both of the ones have been already paired. Why are you making a group? I need to find all possible groups. So this one has been paired with this one, has been paired with this one, and this one is there in this club, and this one has been paired with this one, and this one is there in this club. Are you getting this point? Inside a bigger quad, I was not able to make 2 clubs, because both of the clubs were there in the quad only. But if I am making cells, if I am making pairs, then I can make pairs anyhow. This is how I can make pairs. There you go. So how many were there? 6. How many were there? 6, right? Do you want me to write down the names? 0 1 2 3 4 5 6 7. Let's write it down then. 0 1 was there, 1 3 was there, 3 7 was there, 6 7 was there, 0 1 1 3 3 7 3 7 6 7, then 0 4 0 4 and 6 4, basically 4 6 you can say. So these many prime implicants are there. What about 4 variables? So intelligently you need to think, here there is no possible quad. I have adjusted the one in a manner that there are no possible quads. So let's write down the prime implicants. 1 2 3 4 5 6 7 8 9 10. Wait a second. Is there any pair? Let me think. Is there any quad possible? Let me see it. No, there are no quads possible. So I guess the pairs that we were making, that is fine only. I cannot see any quad here, because I wrote down the numbers thinking that only the 1 1 1 I can write. So if I write 1 here, that would be a quad. If I write 1 here, it would be a quad. So I wrote 1 1 1 in this manner. If I write 1 here, it would be a quad. 1 here, it would be a quad. Then I wrote 1 here. So in that manner I wrote. So 1 2. Actually there is no certain formula. That's why I am teaching this thing. No one will actually ask you the number of prime implicant. Okay, maximum number of prime implicant. But we have to solve in this manner. So 1 2 3 4 5, right? 5 and then 6. Wait a second, sorry, this one would be the 6th one. 6 7 8 9. This could be also possible. 10, right? 10 is there, this is 11, and this goes single 12. So 12 we have found. Did I miss anything? Am I missing anything? Yes, 12 I have found. 13th, where is the 13th one? There you go. This is the 13th one. 13. 13. 13 directly I am finding here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 13 I can directly find. Is there anything else? Am I missing anything? No. So in 4 variables I have seen 13. So what did you understand here? For two variables you got 2, for 3 variables you got 6, for 4 variables you are getting 13 here. So there is no certain formula. So if they are asking what is the maximum number of prime implicants, so they cannot ask. They will have to give you a function. Here they did not give any function here. They did not give any function. Directly I was putting 1 1 because my target was to find maximum number of prime implicant. So here I could find 2, here I could find 6, here I could find 13. And as far as I think, there are no quad. Hopefully I am not doing any blunder, because I have put these ones randomly, and you will not find these concepts in textbook as well, so you cannot even verify. So as per my understanding, everything is correct. I am getting in 4 variables, I am getting 13 prime implicants. So here there are 13 prime implicants. Here there were 6 prime implicants. So these are the maximum number of prime implicants which you can get. But this question will not be coming because there is no certain formula that in 2 variables 2 prime implicant is coming. I guess 13 is the correct answer. If someone is getting more than 13, then he can send me his solution on Telegram. I can check it. Okay, but I guess 13 is the maximum one. Okay, so now these kind of questions can come, that they will give you a function 1, 4, 6, 7, 8, 9, 10. Now you need to find their number of prime implicants. How many prime implicants are there? Before that, let's do the numbering. 0, 1, 2, 3. I should have done it before as well. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So let's start. Can I make a quad here? Yes, I can make 1. Can I make another quad here? Can I make another quad? No. 2, 3, 4, 5, and 6. So 6 you are getting. Okay. So 1 quad was there and 5 pairs were there. Let's write down the numbers. 8, 9, 10, 11. 15 or 11. 11, 15. Then 7, 15. Then 7, 6, 7. 3, 6, 7. And then 6, 4. 4, 6 you can say. Then this number, that is 5, 1. Sorry, 9, 1. 1, 9. 1, 9. Okay. So these are the possible prime implicants. Right. So these are the possible prime implicants. So these kind of questions can be coming in your examination. Okay. Let's study about essential prime implicants and the most important topic. What do you mean by essential prime implicants? So the group which cover at least one minterm that cannot be covered by other group. You are not understanding anything? Let me take some example and I will tell you how to find essential prime implicants. So what we will do? First we will mark up all the prime implicants. 1, 2, 3. Any other possible group is there? No. Now what I will do? I will go to the groups one by one. First I will go to this group. This is my first group. This is my second group, and this is my third group. I will go to this group and I will talk to each element of this group. So first I will go to this one and I will ask this one that, bro, do you have any other option than going with this one? That means, do you have any other option rather than staying in this group? Let's just say if one was there, then this would have been the pair, no? So if I had gone to this one and I would have asked that, bro, you are in the group 1, and this would have been, let's just say, group 4, that, bro, you are in group 1, do you have any other option to go without group 1? Yes, he will say, yes, I can go to group 4, right? But in this case, this group 4 is not there, right? I will go to this particular element, I will ask this one that where you can go. You can go with this one only, not this one. This one is also not there. So I will go to this one and I will ask you where you can go. So he will say, I can go only with this one. That means this element can go only with this. So if there is at least one term, there is at least, very important thing, if there is at least one min term that cannot be covered by other group, that means this min term can go with only this group only. So that is a prime implicant, essential prime implicant. So that is a essential prime implicant. Now I will go to group 2. So I will ask this one, bro, you are in group 2, do you have any other option? So he will say, yes, I have other option, I can go with group 1. I will go to this guy, I will ask him, bro, do you have any other option? He will say, yes, I have any other option, I can go with this one. So that means both are having other options. So this is not a essential prime implicant. Now in this group, I will go to this guy, he will say that I have the other option, but he will say I don't have any other option. I have only one option, which is this one. I have only one friend. He is having only one friend, which is this. So there are two essential prime implicants. Two essential prime implicants. What all are those? Group 1 and group 3. And there are 3 prime implicants. 3 prime implicants. Which all 3 prime implicants were there? Which all 3 prime implicants were there? 0, 1, 2, 3. 2, 3. 3. This is 3. 4, 5, 6, 7. 3, 7. And 4, 5, 6, 7. 5, 7. Okay. So in this group, 3 can go with 2 and 7 can go with 5. In this particular group, 3, 7, which is this one, 3, 7. So if I write down all the prime implicants, then I can see that this 3 has a chance to go with 2 and 7 has a chance to go with 5. That means this is not an essential prime implicant. Not essential prime implicant. So what all are the essential prime implicants? That is 2, 3 and 5, 7. We will see more examples. It will be more clear to you. Let's make prime implicants now. Okay. In this example, can I make prime implicant in this manner? No. What did I tell you? First, take the biggest pair. What is the biggest pair? Quad. There you go. Now can I make these pairs? 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 No, because all these pairs are there in the quad only. So only pair I can make is this. That's it. Now there are only 2 groups. This is one group. This is 2 groups. There are only 2 groups. That means there are 2 prime implicants. Right? How many of them will be essential prime implicant? So I will go to this group. I will talk with this one. Do you have any other option than going with this one? No. He will say, no, I have only one friend. Now I will go to this group. I will ask this one, do you have any other option? Without staying in group 2. Rather than staying in group 2, do you have any other option? He will say, yes, I have other option. I will go to this guy. I will ask him, do you have any other option? He will say, no, I don't have any other option. Because this is not possible. This is not possible. So he will say, I don't have any other option. So that means this one is also not having other option. Or you can go to this guy as well. If you ask this guy, bro, do you have any other option? He will also say, I don't have any other option, because this pairing or this pairing, these are not possible. I will go to this guy. I will ask him, do you have any other option? He will also say, I don't have any other option. So at least one I need to find. I just found that this guy don't have any other option. So I don't need to ask these guys. So both of them has to be essential prime implicant. So one by one I will go, and I just need to find one guy which is not having any other group. I just need to find one guy which has only one group. So that is this. Okay. 0, 1, 2, 3. 2, 3, 4, 5, 6, 7. 2, 3, 6, 7. 2, 3, 6, 7. So essential prime implicants are like those guys in college who belongs to only one group, right? They don't have any other friends. Like let's just say there is a group of 5 friends, right? So we take the name. Let's just say one guy is having the name of Ram. So Ram can have some other friends, but Sham, Mahesh, they are not having any other friends. So this is like essential prime implicant. That group is essential because those 4 guys are not having any other friend, or at least there has to be one of the guy who has only these 4 friends, not other friend, right? And in between the grouping is not allowed. Like there are 5 friends and 3 guys makes separate group and 2 guys make separate group. This is not allowed because that is not a good friendship, because in between the group there are groups, then there is an issue, right? So this is like you can relate it to friendship. 0, 1, 2, 3, 4, 5, 6, 7, 5, 7. Okay, let's solve this example. Can I make a quad here? No. So this group, this group, this group, and this group. 4 groups are there. 1, 2, 3, 4. Any other group are there? Any other group can you see? No. So 0, 1, 2, 3, 4, 5, 6, 7. Right? So 1, 2, 3, 4. 4 prime implicants were there. 4 prime implicants were there. What about essential prime implicant? So first I will go to this group. In this group I will ask him, do you have any other option? He will say, no, I have only one friend. I will go to this guy. I will ask 1, do you have any other option? He will say, yes. I am going into this group. This is the group 2. I am going to, first I went to 4, 5. When I went to 4, 5, I asked 4, do you have any other option? He said, oh, I have only 5 only. Then I am going to 5, 7. So I will go to 5 and I will ask him, do you have any other option? He will say, yes, I have the option of 4. I will go to 7, I will ask him, do you have any other option? He will say, yes, I have the option of 3, because 3, 7 is also there. So this is not a prime implicant, not an prime implicant, not EPI. Now I will go to 7. Sorry, I will go to this group. I am talking to this group now, 3 and 7. So I will ask 7, do you have any other option than 3? Yes, he will say, yes, I have the option of 5. I can go. 7 has other option. Now I will go to 3. I will ask him, do you have any other option other than 7? He will also say, yes, I do also have other option than 7, that is 2. So 3 can go with 2. Here you can see 3 can go with 7. 3 can go with 2 as well, and 7 can also go with 5. So 7 has 7, 5 option, and 3 has also other option. 3 has option 2. So this is also not essential prime implicant. So these 2 are not EPI, not essential prime implicants. Now I will go to this group. I will ask this one, bro, do you have any other option? 3 will say, I have other option, that is 7. But 1 do not have any other option. This 2 is only, this 2 have only one friend, that is this 3. So this is essential prime implicant. So this friendship is important. These 2 friends are not that important, because 3 has one more friend, 7 has one more friend. So 3, 7 is not important. 5, 7 is also not important, because 5 is having one more friend, that is 4, and 7 is having one more friend, that is 3. So this is also not important, but these friends are important because 4 is alone and 3 is alone. 2 is alone. So these 2 are essential prime implicants. So in that manner you can think. Let's start with this one. 1 quad, you can see biggest pair. 2, 3, 4, and then 5. Should write down all the number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 1, 2, 3, 4, 5. 5 prime implicants are there. In that, first I will go to 5, 7, 13, 15. 5, 7, 13, 15. So I can directly see that 5 has other option, 13 has other option, but 7 has no other option. 15 has no other option. So that is essential prime implicant. Then I will go and talk to other guys. Those are 1, 5. So I will go to 1, 5. So I will go to 5. He has other option, but 1 does not have any other option. Here this guy was not having any other option. So this is also essential prime implicant. Then I will go to this group 12, 13. So 13 is also having other option. So 13 is having this group, and 12 is also having other group, right? 12 is also having 12, 8 group, because 12 is also having 12, 8 group. So 13 also has other group and 12 also has other group. So this is not EPI, not EPI. What about this 12, 8? So 12 is having 13, 12 is having 13, and 8 is having 10 as well. So other group is also there. What is that? 8, 10. So 8 is having 10 and 12 is having 13. So this is also not EPI. And now I will go to 8. 8 is saying that I have 12, but 10 will say that I have only 8 only. So this is an EPI. So there are 3 EPIs and 2 which are not EPIs. So 5 prime implicants are there, and these are the essential prime implicants. So in that manner, if you are able to write down all the implicants, all the prime implicants, then it will be a cakewalk for you. You just need to see, okay, 1, 5, 1 is not having other friend, essential prime implicant. 13, 15 is not having another, 13 is having 12, okay, but 7 is not having another friend, so is essential prime implicant. So in that manner, you will never get the answer wrong, okay. Every time answer will be correct. Solve these questions on your own. Can you see a quad here? You can see a quad. Don't mess it up. You can see a quad. Which is that quad? This is the quad. This quad you can see here, right? Because a lot of guys would have messed it up. One quad you can see here directly. 2, 3, 4. That's it. So 4 prime implicants are there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So first pair is 0, 2, 8, 10. I can directly see that 8 is not having another option, 10 is not having any other option. So this is essential prime implicant. Then I go to this group 3, 2. 3, 2. 3 is not having any other option, right? This here, this 8 was not having any other option. Any of the element was not having other option. This 2 is having other option. This 2 is having this group, but 3 is not having any other group. So this is also essential prime implicant. Then I go to 5, 13. 5, 13. I can directly see that 13 is having other guy, but 5 is not having any other guy. This is essential prime implicant. And then I go to 13, 15. So I can see 13 is having other guy, but 15 is alone. So this is also essential prime implicant. So 4 prime implicants are there. All are essential prime implicants. Okay. Let's see other example. Again, can I see a quad here? Certainly I can see a quad here. Do I see another quad? Do I see another quad? No. So 1, 2, 3, 4, 5, 6, 7 and 8. So 8 prime implicants I can see. All the pairs I need to make, all the pairs. So 8 prime implicants are there. Wait a second. 8, not 8. There you go. 9. Right? This can also be possible. 9 prime implicants are there. Are you able to see? 1, 2, 3, 4, 5, 6, 7, 8. And this is also possible, 9. Because this has different pair, this has different pair. Both are different pairs. So this is also possible. In between, both are not there. In between, these are not there. So we will write down all. Do I need to write down all? No, because if you write down all, it will take a lot of time in the examination. Now I will not write down all, I will just calculate the essential prime implicants. So let's calculate the essential prime implicants. So in the first group, I can see this guy is alone, right? This guy is alone. because this guy doesn't have any other option. So this is the essential prime implicant, which is 0, 1, 0 to 8, 10 only. 0 to 8, 10. This is essential prime implicant. So this group I have talked. Now I will go to this group. So first group I have talked. I am talking to second group now. So this guy has this option and this guy has other option. So second group I have talked. Now I will talk to third group. So this one has this option and this one has other option as well. Now I will talk to fourth group. So this one has this option, this one has this option, right? This one has this option, this one has this option. So other options are there. I will go to fifth group. So this one has this option, this one has this option, this one has this option, and this one has this option. So all other options are there. I am talking to this group. So I will go to this guy. This guy will say I have this option as well, and this guy will say I have this option as well. I will talk to sixth group. So this guy will say I have this option, and this guy will say I have this option. So sixth group I have talked to, and now I will talk to seventh group, which is this one. So I am talking to seventh group now. So if I talk to seventh group, so this one will say I have this option, and this one will say that I have this option. So seventh group I have talked to. Now I will talk to this group, which is eighth group. So if I am talking to eighth group, so this one will say I have this option, and this one will say that I have other option as well. So this is also not an essential prime implicant. Now which group is left? 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so I talked to all the group, but I did not write the name. This is 8 and this is the ninth one. So all these are having other guys. All these are having other guys. All these are having other guys. This is also having other guy. This is also having other guy. This one is having other group. This one is having other group. All are having two groups. All are having two groups. All are having two groups. All these are having two groups. This is also having two group. Only this guy was there, which was not having. So I have talked to all the guys. So this guy was having only this particular group. This element also has two group. This element also has two group. This element also has two group. But this guy was alone. So because of this is essential prime implicant. So only one essential prime implicant is there. Only one. So one essential prime implicant. So if someone asks you in this particular K-map, how many essential prime implicants are there? So only one is there. Okay. Let's see more example. Can I make a quad? No. 1, 2, 3, 4, 5. Any other possible pair is there? Any other possible pair is there? No. So this guy one is alone. This is going to one group only. This is going to two groups. I can see this is also, this one is going to this group. This one is going to this group. This one is also going to this group. This one is also going. Like I can see there are two boxes. No, I can directly see. This one is also involved with someone else. This one is also involved with someone else. This one is also involved here. This one is also involved here. Only this guy is not involved. Only this guy is alone and this guy is alone. I can directly see with the boxes. I can talk to individual groups. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 prime implicants are there. Out of these, which all are essentials one? 0, 1. And then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these two are essential prime implicants. So 2 essential prime implicants are there. That's it. Okay. So this is the concept of essential prime implicants. There are 2 more terms which are not usually asked. They are not usually asked in the examination, but let's study it. Redundant prime implicant and selective prime implicant. So what do you mean by redundant prime implicant? Read the definition carefully. Prime implicants whose each of the midterm is a part of some essential prime implicant. Each midterm should be part of some essential prime implicant. Okay, then only it will be called redundant prime implicant. let's take the example. So first I will mark all the prime implicants. All the prime implicants I am marking. Now I will mark all the essential prime implicants, which is this one and this one. Okay. So this group, look, there are 3 prime implicants, right? And there are 2 essential prime implicants. So now there is chance that one can be redundant prime implicant or one can be selective prime implicant. That's it. Okay. Now one would be there which could be redundant, or because out of 3, 2 are essential prime implicant. One I am not sure. It would be a redundant prime implicant or it would be selective prime implicant. So that I need to check. So what do you think? This is the group, no? 0, 1, 2, 3, 4, 5. So the group is 1, 5. Other groups are 0, 1. Other groups are 5, 7. Okay. So 1, this term 1 is involved with 0, which is an essential prime implicant, and 5 is involved with 7, which is also an essential prime implicant. So each term should be a part of essential prime implicant. Then only we will say this is redundant prime implicant. Are you getting this point? Each term should be a part of essential prime implicant. Now I will show you one example where there are redundant prime implicants. So let's see this example now. So first we will mark all the prime implicants: 1, 2, 3, 4, and this one can also come. So it will be 5, right? 5. So basically there are 5 prime implicants. Out of these, which all are essential prime implicant? You can quickly tell. If you go to this group, this guy is alone. If you go to this group, these guys are alone, or this guy is also alone. So, but these are the part of only one group only. And if you go to this group, this guy is alone. If you go to this group, you can see that this one is involved with this one, and this one is involved with this group. If you go to this group, this particular group, then you can say that this one is involved with this guy, and this one is involved with this guy. So both are involved in other groups. So this is also not essential prime implicant. So 3 essential prime implicants are there. Now rest 2 are left. Now these 2 will be what? Redundant prime implicant or selective prime implicant? That we need to check. Okay. So let's check that. So first I will go to this group. How I will check it? That I am telling. First I will go to this group, which is not an essential prime implicant. Now I am going to this group. I will talk to this element. So this element is connected to this group. So where I am already in this group only. I have gone to their home. This one is involved with this one. I will ask you where you are other involved. So he will say that I am involved with this guy. He is involved with this guy. Is this guy an essential prime implicant? No, this guy is not an essential prime implicant. I need to check about this group. This group is 12, 13. So I am checking about 12, 13. I am checking to 12, 13. So this is our 12. This is our 12. So I went to 12 and I asked you where you are involved. So 12 said that I am involved to 12, 8. Is this an essential prime implicant? Not. Is this an essential prime implicant? Not an essential prime implicant. So each term should be involved with the other group. So now I am talking to this guy. I am talking to this group. So I don't know where 13 is involved, but I am sure that 12 is involved with 8, and this group 12, 8 is not an essential prime implicant. That means it is selective prime implicant. This 12, 13 is selective prime implicant. Are you getting this point or not? Did you understand this point? Here we went to this guy, which is this 1, 5. So I went to 1 and I asked you where you are involved. So one side I am involved with 0, and then I checked about this group 1, 0. Is this an essential prime implicant? Yes. I am happy. Then I went to 5. I asked 5 where you are involved. So 5 said that I am involved with 7. Is this an essential prime implicant? Yes. So if this is an essential prime implicant, both elements are involved with other essential prime implicants only. That means this is a redundant prime implicant. But here I went to 12. I asked where you are involved. He is involved with 8, and 12, 8. It is also not essential prime implicant. That means, what do you mean by that? That means this is certainly not redundant prime implicant, because if it was involved with some other guy, let's just say if it was involved with 12, 7, and 12 7 was essential prime implicant, then I would go and talk to 13 and I would check where 13 is involved. But when I talk to 12 only, I got to know that 12 is involved with 8, which is not an essential prime implicant. So certainly this is selective prime implicant. So this is selective prime implicant. Now I will go to this group. I will go to this group. I will talk to 12. So I will ask 12 where you are involved. So 12 will say I am involved with 13. 12 will say I am involved with 13. Then I will check this group, and then I will get to know that this is also not an essential prime implicant. So I went to 12. I talked to 12 and I got to know that 12 is involved with 13. Now I am talking to these guys. So 12 is involved with 13. So I checked this group 12 13, which is also not an essential prime implicant. That means this is also selective prime implicant. So two selective prime implicants are there. Look, you can drop redundant prime implicant and selective prime implicant if you are feeling that. I am certainly sure that you must have understood it. But like in the examination, you might get confused. But don't get confused in essential prime implicant, because that is very important. Don't forget essential prime implicant. That's why we are not going to see much example of selective prime implicant, because I don't want you to get into complexity. What is selective prime implicant? What is essential prime implicant? That I have only one friend. That you need to remember. Okay? That I have only one friend. That is selective prime implicant. That is essential prime implicant. For selective prime implicant, you need to talk to guys. I talk to 12. I know that it is involved with 13, but where it is other involved? It is involved with 8, which is also not an EPI. That means this is selective prime implicant. And when I go to this group, I got to know that this 12 is involved with 8, but it is involved with 13 as well, which is also not an API. That means both are selective prime implicants. Let's check more examples. First, I will make quad. 1 quad, 2 quad, and 3 quad. 3 quad directly I can see. More quad I can see, yes. 4 quad and 5 quad. All are quads only. So no pairs are there. All are quads. All are quads. All are quads. So 5 prime implicants are there. All are quads. I can see this one is alone. This one is alone, so this is essential prime implicant. When I go to this group, I get to know that this one is involved with this group. 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 So all are involved with some other guys, right? So this is not an essential prime implicant. When I go to this group, I get to know that this guy is alone, because this guy is involved with this one, but basically this group only. This is our group 1. This is our group 2. This is our group 3. This is our group 4. So when I go to this group 4, this one is involved with group 1. This one is involved with group 2. This is involved with group 3. But this one guy is alone. Right? And what is the other one left? This is our group 5. So when I go to this group, so this one is involved here. This one is involved to. This one is involved to group 3. This one is also involved to group 3. And this one is involved to group 4. So all ones are involved in some other group. So this is also not an API. So 3 APIs are there. Now, which all not are APIs? Basically, group 1 is API, group 3 is API, and group 4 is API. Now I will go to group 2 and I will talk to each of the element. So I went to 1, I went to this guy and I asked you where you are involved. He said that I am involved in group 3. He said that I am involved in group 3. This is our group 3. He said that I am involved in group 3. And group 3 is an API. So I am happy with the 1. I am happy with 1. Then I will go to this one. I will ask you where you are involved. He will say I am involved with this one will say that I am involved with group 1. And group 1 is an API. So I am happy with this one as well. Now I will go to this one. This one will say that sir, I am involved with this one is involved with group 5, and this one is involved with group 5, and this one is also involved in group 4 as well. This one is involved in group 5. You can directly see group 5 and group 1 as well. Sorry, group 4 as well. And group 4 is an API. So I am happy with this guy as well. I am happy with this guy as well. I will go and talk to this group. This will say that I am part of group 2, but I am involved with group 3 as well. And group 3 is an API. So I am happy with all the 4. I am happy with all the 4 that all 4 are involved in some other APIs. All 4 are involved in some other essential prime implicants. That means group 2 group 2, or I can directly tell their number, which is 4, 5, 6, 7. 4, 5, 6, 7 is redundant prime implicant, right? Let's talk about group 5. So I will go to group 5. I will ask this one, I am involved with group 4, essential prime implicant. I will ask this one, I am involved with group 4, essential prime implicant. I will ask this one, he will say that sir I am involved with group 3, which is also an essential prime implicant. I will go to this one, he will say that sir I am involved with group 3. So this is also an essential prime implicant. So all the elements are associated with other prime implicants. That means this group as well. Which is this group? 4, 5, 6, 7. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are also redundant prime implicants. So there are 2 redundant prime implicants, 3 essential prime implicants, and 5 total prime implicants. Okay. So this is the way of studying the complete implicants. This is being a long video. I know implicants are taught in a very small time, but I need to give you the in-depth concept because the questions can be coming from this particular topic. This is a very important topic. Okay. So I hope you must have understood everything. Now this is also an important point. Maximum number of essential prime implicants. In 2 variable, how I can get essential prime implicants maximum? This one and this one, if I replace this one and this one as like this, so this will be prime implicant, this will also be prime implicant, and this one has only one pair, this one also has only one pair. So here 2 essential prime implicants are there. If I replace one in this manner, so how many pairs I will make? 1, 2, 3 and 4. These 4 pairs I will make. So these 4 are the essential prime implicants. Are you getting this point? Because this one has only this chance, this one has only this chance. If I replace one in this manner, 1, 1, 1, 1, 1, 1, 1, 1. So what kind of pairing I can do? This is the possible pairing only. 3, 4, 5, 6, 7, 8. So 8 essential prime implicants are there. So alternatively, if I am placing 1 blank, 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 1 blank. If I am replacing alternatively, what does that mean? That means I am getting maximum number of essential prime implicant. So in 2 variables, I am getting number of variables is n. So I am getting 2 essential prime implicants. In 3 variables, I am getting 4. In 4 variables, I am getting 8. How I am getting it? Basically, if 4 variables are there, that means I can make 2 to the power 4 cells. I can make 2 to the power 4 cells. 16 cells are there. 2 to the power 4 cells are there. And if I replace 1 in half of that means 1, 3, and then this. So in 1 row, I am replacing in 2. Here also 2. Here also 2. Here also 2. So in half of that, I am replacing ones. That means 2 to the power 4 by 2. Here also what I am doing, total cells I am having 8, but alternatively I am writing 1. That means in these many cells I am writing 1. So if there are n variables, so how many cells are possible? 2 to the power n, and in alternatively I will write, so 2 to the power n by 2. So these many EPIs are there. So what is the total number EPI? Total EPIs are 2 to the power n minus 1 EPIs. Are you getting this point? So for n variable, total 2 to the power n maximum EPI. So if there are 4 variables, maximum essential prime implicant you can get is 8. What was the number of maximum prime implicants? That was 13. As per me, it was 13. Why it was 13? Because we made the table, right? Here we show it. It was coming out to be 13. I hope this is correct. Okay, because there is no way to recheck it. From nowhere you can recheck it, because like randomly we have to place, and this is the condition for maximum API, maximum prime implicants, I feel. But they will not ask you, because this is not a certain fact. There is no certain formula. You have to randomly place the ones. So I randomly place the ones, then I go to know that 13 prime implicants I am getting. So you can do the same. And you can try, if you are getting more prime implicants, then you can tell me on Telegram. I will also look into it. Okay, but this is not important. That was not important with respect to examination, but that is important because they can ask you the maximum number of essential prime implicants. Okay, now let's see. This would be our last topic of this particular chapter. So some examples of don't care we can see. So if don't care is coming, so I will use don't care only if it is helping me to make a major pair. Let's just say if I use this don't care, then I will have a group of 4. If I use these two don't care, then I will have a group of 4 again. If I use these two don't care, I will have a group of 4 again. Now why would I use these don't cares? There is no use of these don't care, right? And alone don't care will not frame any group. Like I will not say that this is a pair. Why this is not a pair? Because both are don't care only. I will not say this is a pair. I will not also take this pair. Why? Because this don't care is not helping me to frame a major group. Major group, what is the major group here? Major group is quad. So this don't care is helping me only to make a pair. So I will not take it. Are you getting this point? Till now in the GATE history or in any examination, the questions has not been asked on don't care. Okay, in any examination, don't care question did not come. But what if it comes? If it comes, you need to solve in this manner: 1, 2 and 3. That's it. Because these two don't care are not helping you to frame a major group. And if you are framing a group here, that would take both don't cares, and that I don't want. Let's just say if I was having one more don't care here, one more don't care here. So would I frame this major group? Which major group I am talking about? This major group. Would I frame this major group? No, this is not a prime implicant. Not a prime implicant. Why? Because of this property. Not because of this property, sorry. Because of this property. Because alone don't care will not frame any group. So in this particular group, you are only having don't cares. So that is not a prime implicant. This is not we want. So how many prime implicants are there? 1, 2, 3. 3 prime implicants are there. 3 prime implicants are there. Now, how many of them are essential prime implicants? Let's check that. So this don't care is considered as one only. So this one has only one chance, that is this group. So this is essential prime implicant. If I go to this one is having only one chance. If I go to this group I am talking about, this particular group. This is our group 2, this is our group 1, and this is our group 3. So 1 and 3 are essential prime implicant. But if I go to group 2, so group 2 will say that this one will say I can go here, this one will say I can go here, this one will say I can go here, this cross will say I can go here. So all are having other opportunities. This one is having group 1, this one is also having group 1, this one is having group 3, this cross is having group 3, right? So this is not essential prime implicant. So 2 essential prime implicants are there. So what is this group? Group 2. So I will go to group 2, I will talk to this one. One will say I am part of group 1, which is essential prime implicant. This one will say I am part of group 1, which is an essential prime implicant. This one will say I am part of group 3, which is an essential prime implicant. And this cross will say I am part of group 3, which is an essential prime implicant. So all the numbers are part of essential prime implicant. That means one redundant prime implicant is there. So this is redundant prime implicant. Okay, because all are part of essential prime implicant. So 3 prime implicants are there, 2 essential prime implicant and 1 redundant prime implicant. And that is the complete concept of implicants. I hope these are enough examples for you. We will take more examples in the assignment problem, which is the next video. So I will show you the assignment now, and you need to solve it on your own, and then you need to watch the next lecture. Okay, so I will show you the assignment. Do solve it on your own, because that would be a very good practice of you, and then you will be very comfortable by the end of this particular chapter. I would say in this chapter we have covered logic gates, Boolean algebra, then we saw the representation techniques, and then we saw the K-maps, which is a minimization technique. So these 4 topics we have covered in one chapter only. So I will show you the assignment, or I can assignment PDF also will be posted. So from PDF only you can see the assignment. Okay, I'm not going to show in the video. From PDF only you can see the assignment and solve it. Okay, then let's meet you in the next session now. Hi everyone, so in this video we are going to solve this assignment. So there are total of 14 questions. I can show you the problem first, or you can see it from the PDF as well. So this is the first one. This is the second one, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14. These 14 problems are there. Let's solve one by one. So yeah, let's start. You need to tell the minimized expression of K map. So shall I start solving now? No. Why so? Because you need to take care of this. 0 0 0 1, here it should be 1 1 1 0, because I told you there should be a difference of 1 bit only. So there is a difference of 1 bit, but there is a difference of 2 bits. So 1 1 should come here and 1 0 should go there, right? So these two will be interchanged, 1 1 1 0. So 1 1 line 1 x 1 1, that should come here, 1 x 1 1, and 1 0, that means this line 1 1 x 1, that should come here. Now I can write the minimized expression. So how will I write the minimized expression? Here I can see I can get a octet, right? So if I can get a octet here, now this one is left. Can I get it in the octet? No, not in octet. Can I get it in the quad? Yes, I can get it in the quad. There you go. So this is the quad we are having, right? So how will I write down the expression? So in this one, only a is constant, and here look, doesn't matter if AB is written here or AB is written here. It doesn't matter if AB is written here or AB is written here. Here I know one thing, that it would be AB, and this would be A B bar. So here A is constant and all these CD are changing. So only A would come. Plus these are the pair. So this would be A bar B bar. So here B bar is constant, and in this one CD, and this is C D bar. So C is constant. So A plus B bar C. So what is your MSB, what is your LSB? That doesn't matter here, right? So answer would be A plus B bar C. Let's solve this question. Minimize the expression you need to tell. So in temptation of making a quad, if I make this as a quad, then there would be an issue. So what you need to remember that wait a second, this should not be there, right? Or let's just keep it if I have kept it only. So what should be the ideal approach? That I will use the don't care only in the last. In the last only I will use the don't care. First I will see what all the pairs I can make. So this octet I can make. Okay. Now this one is left and this one is left. So can I make a quad here? Yes, I can make a quad. I can make a quad. There you go. Without even using the don't care, I have made the quad. If I had made this quad, then it would be redundant. There would be no use of this. So first our target would be that I will club all the ones without using the don't care. So without using the don't care, we have clubbed all the ones. That's it. So here what is constant? C is constant. Plus, actually in the assignment problem, you will not get these ones, I guess, as far as I remember. In the assignment problem, this problem would be a bit different, as far as I remember. So here only C is constant, and here D B bar. In this one D is constant, and in these ones B bar is constant. So C plus D B bar, that is the correct answer. Okay. So let's move to the next problem. You need to find the complement. Wait a second. So what will be the complement of this? Basically I can denote x y z as summation 1 0 1 0 1 5 0 1 5 7, right? This is how I can denote it. And then what will be the complement of this? That would be 2 3 4 6. So what is the answer? 2 3 4 6. Or directly you can say this. What does that mean? That 2 3 4 6 all are 0 and rest all are 1. So if I take the complement, these will be 1. and rest all will be 0. Rest all will be 0. So if which one will be 1? 2, 3, 4, 6 only will be 1. So directly I could have clicked on this. These are 0, this will become 1. So that would be the answer. Okay, let's solve this problem. This is given, it would be equals to, you need to write down in terms of the least literal count. The literal count should be the least. If I write down in this manner that this is 1, 1, 1, 1, 1, 1, because this is given, right? 1, 2, 3, 4, 5, 6, 7. So here, how will I do the clubbing? I will have to do the clubbing in this manner. 1 club is there, 2 club is there, and 3 club is there. So there 6 terms will come. A, B, C it is. So this is A bar A, this is B bar C bar, B bar C, B C, and B C bar. 6 terms will come here. We can check it, right? Here B is constant, here A bar is constant. So A bar plus B. In this one, only A is constant. In this 4. Sorry. Why 6 terms will come? Only 3 terms only will come, no? So if you see this, here only B is constant. Here only A is constant. And this one only C is constant. So answer is A plus B plus C. Or you could have directly seen that this would be 0. So if this is 0, that means this is 0 and this will be replaced with A and this will be replaced with B plus C if I am considering POS. So answer would be A plus B plus C only. So that would be correct. Okay. So if you solve by SOP or POS, if you solve by 1 or if you solve by 0, you are getting the same answer only. That is obvious, you will get the same answer. I don't know why did I say it would be 6. It would be 3 only, right? B plus C, just a bit more lengthy it would be. So 3 literals are there. Let's solve the next one. Now this is a very good question. What you need to find? You need to find minimum number of 2 input NOR gate to implement the Boolean function. So while solving these kind of problems, what did I tell you? Our first question will be, is this the form I want? No, I don't want this form because I am using NOR gate. In NOR gate, what do I want? In NOR gate, I want POS form. In NOR gate, I want what? POS form. If you remember it. You remember it? A plus B into C plus D. Right? So these kind of form we want when we are solving from NOR gate. So we want POS form. So if we want POS form, then what we can do? Directly converting POS would be difficult. So I can use the K-map. So that is the best thing about it. Then now I can use K-maps. A, B, C. Because now if you see a complex expression and you feel like that you will not be able to convert it into POS directly, then use the K-maps. How will you use the K-map? B bar C bar, B bar C, B C, B C bar. So A B C bar, A B C bar, A B C bar, AC, AC, A is there, C is there, AC, B bar C, B bar C. So these all are available, right? These all are the ones. Rest all will be 0. Rest all these will be 0. Right? So I can remove the ones now, or I can again make another one where I will write down POS form. That means this would be A, this would be B plus C. This would be A, this would be A bar. B plus C, B plus C bar, B bar plus C bar, B bar plus C. 0, 0, 0, 0. So what grouping I can see? One group and then another group. That's it. Okay. If you make this group, that would be redundant, right? So here B plus C is constant and here A is constant and B bar is constant. A plus B bar is constant. So your Y is A plus B bar into B plus C. And if you have watched the lecture, you know how to implement this. How many it will take? 4. How? This is B bar, this is A. B plus C. B, A, B plus C. Now what do I need to make? I need to make NOR gate. So if I am adding one inverter, then I will have to use another inverter. If I am adding one inverter, I will have to use another inverter. So what is this? This is one NOR gate. I have told you the method, right? I have told you the method how to solve these kind of problems. 1, 2, 3 and 4. Because for making one inverter, you would require one more NOR gate. So this is also a NOR gate only. So basically answer is 4. So answer will be 4. So these kind of good questions can come up. So you will have to see if I am making NOR gate, that means if I am using NOR gate, that means I have to convert it into POS, right? So let's solve this problem now. You need to find the number of essential prime implicants. Okay. Now zeros are mentioned. So shall I start solving this problem in this manner that this is a quad, this is a quad. Shall I start it like that? No, I cannot start. Because if you remember the chapter, everywhere there were ones only. We did not take 0. So there is an important note, that is that these all the terms know that prime implicants, essential prime implicants, essential prime implicants, redundant prime implicants and selective prime implicants. These are defined for minterms. These are defined for minterms. And if you need to define it for max terms, then what you will do? You will put a false word here. So if this question was find the number of false prime implicant, then you could have started in this manner. Okay. But the question is find the essential prime implicants. So now you need to see the max terms wherever wherever you are getting max terms. So where you will get max terms. Apart from 0, everything will be 1. Right. So first you need to see if you can see any quad. Yes, I can see a quad, which is this one. I can see a quad. Now first I am marking all the prime implicants, then I will mark all the essential prime implicants. So this is a quad, then this is a prime implicant, this is a prime implicant, this is also a prime implicant. Any other prime implicant could be there. This could not be a prime implicant. Why so? This is not a prime implicant because this is a part of quad only. This is also not a prime implicant because this is a part of quad only. So there are 1, 2, 3, 4. 4 prime implicants are there. 4 prime implicants are there. And certainly essential prime implicant will be lesser than that. So 3 or 4 could be 2 possible answer. If you go to this group, this guy is alone. If you go to this group, this guy is alone. If you go to this group, this guy is alone. If you go to this group, this guy is alone. Basically, in this pair, this guy is alone. In this pair, this guy is alone. In this pair, this guy is alone. And in this quad, this guy is alone. So alone guys you have found. So 4 alone guys are there. That means 4 EPI. Basically 4 alone guys in 4 different group. 4 alone guys in 4 different group. That means 4 EPIs are there. That's it. Okay, so this was a good question. Let's solve this problem. This is also a very good problem. Okay, like excellent problem it is. Minimized Boolean expression will have literal count of what? So minimized Boolean expression you need to write. Okay, so how do we solve these kind of problems? We remember it. This we need to solve it with K-maps. So we will solve it with K-map. Is A B C D, right? Now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 8, 9, 10, 11, 12, 13, 14, 15, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Quad, right? One quad is there, and another quad I can make. 3 quads I can make directly. Another quad I can make, and then another quad I can make here. So 6 terms I am getting. A bar, B bar, A bar, B, A B, A B bar. You can skip this part, but don't skip the complete solution. Okay, don't skip the complete solution. C bar, D, C D, C D bar. Here I did not use any don't care, right? I did not use any don't care. So y will be what? In the first one, A bar is constant and C bar is constant. So A bar, C bar plus. In this one, B bar is constant and C bar is constant. So B bar, C bar. In this one, D is constant and B bar is constant. So B bar, D. D is constant and B bar is constant. So that is the answer we are getting. So shall I directly mark that my answer would be 6? No. Whenever there is don't care, I know one thing, that SOP and POS will give me same expression. But when there are no don't cares, if there are don't cares, that means they can give different expression. If this function is given, that is 0, 1, 3, 5, 8, 9, 10, 11, this is given, can I write it in terms of max terms? Yes, certainly I can write it. That would be 2, 6, 7, 10, 0, 1, 2, 6, 7, 10, 12, 13, wait a second. Now 12 and 13 are, 12 and 15 are don't care. So in max term as well, they will be don't care only, no? What does it mean? That if 12 and 15 are don't care, what does that mean? That if your input is 12, when your input is 12, in decimal when your input is 12 and when your input is 15, at that time you do not need to care about output, what output is coming. In decimal, when your input is 12, when it will be 12? 8 and 4. And when it will be 15? So when your input is this, when ABCD values are these, then you don't need to care about output. This is what don't care means. So same thing will be happening here, no? So don't care will not change. Don't care will be 12, 15 only. So here 12 is the don't care, then 13, 14. Wait a second. So yeah, this is the function we are getting. Okay. So now I will make the diagram, I will make the K-map for max term as well, and then I will see what if I am getting lesser least count, lesser literal count. Because here I did not use don't care. What if I use don't care and get something different? Are you getting this point? Here I am getting a literal count of 6, but in max term as well I can get a different literal count by using these don't care. So what is the note? Note is that if don't cares are present, if don't cares are present, then SOP and POS can give you different Boolean expressions. Different Boolean expressions. Till now we studied one thing, that SOP and POS are same only. SOP and POS are same only, they will give you same Boolean expression. But if don't cares are present, then something different can happen. So for that, we will have to make the K-map again. Zero, 1, shall I write it down here? 2, 6, 7, 2, 6, 7, 10, 13, 14. 10, 13, 14. And not summation, it would be pi. and with don't care being 12, 15. Don't care being 12, 15. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Can I check? These two are same. 0, 0, 0, 0, 0, 0, 0, 0, and in the last there is a 0. So if I see 1, what I can see here is that this will make a quad. This can also make a quad, and this will also make a quad. So here we used all the don't care, but again here also you will get literal count of 6 only. You don't need to write it. You can see I am making a pair of 4. That means it will give me 2 variables. 2 variables, 2 variables. So literal count will be 6 only. So here luckily we are getting the same literal count. So in this problem, if someone did not know this concept, then he would have solved by this and got the same answer. But in some problems it can be different as well. So that we will check out. A plus B bar, A bar plus B bar, A bar plus B. Here C bar, C plus D, C plus D, C bar plus D, C bar plus D bar, C plus D bar. So what will be your y? C plus D bar into, in this one D bar is there and B bar is there. So B bar plus D bar, and in this one A bar plus B bar. So luckily we are having the literal count of 6 only. Okay. This was the expression we were getting here, and this is the expression we are getting here. So literal count is same here, but we will see more problems where it can be different. So in the examination we have to solve by both. We need to check if we are getting, in which one we are getting the least literal count, because don't cares are there. Let's solve the next one. Okay, you are having 4 variables. Total number of maximum possible Boolean expression is x kilo. So with 4 variables, how many total possible Boolean expression you can make? 4 variables. Boolean expression, do you remember it? In first chapter we studied it. When we were studying about Boolean algebra. With 4 variables. With 4 variables you will get 16 combination. With 4 variables you will get 16 combination. Right? And each combination will have 2 chances. It can get 0 or 1. It can get 0 or 1. It can get also 0 or 1. So each combination is having 2 chances. So 2 into 2 into 2. 2 will be multiplied how much time? 16 times. Right? 2 into 2 into 2 will be multiplied 16 times, because 16 combination you are having. So in that manner, you don't need to mug up anything. You can solve it. So better the formula was 2 to the power n, that would be 2 to the power 2 to the power 4, that would be 2 to the power 16. Now 2 to the power 16 can be written as 2 to the power 6 into 2 to the power 10. So this term is known as kilo. Okay, this term 2 to the power 10 is known as kilo. So that would be 64 kilo you can write. So x would be 64. So x is 64. 2 to the power 10 is kilo. Okay, you can remember it. 2 to the power 20 is mega. Okay, in that manner we go. So 2 to the power 10 is kilo. So 64 kilo we are getting. Self dual. That is 2 to the power n minus 1. So that would be 2 to the power 3. 2 to the power 8. What is 2 to the power 8? 256. Is this formula correct? Yeah, this was the formula. 2 to the power n minus 1. So 2 to the power 8, answer would be 256. Prime implicants with 4 variables. How much prime implicants did we get? 13. And essential prime implicant. What was the formula? 2 to the power n minus 1. Or you can remember, there will be 16 cells, and in half of that there will be ones. So 2 to the power 4, 3. So 8. So here you are getting 8, here you are getting 13, 256 and 64. So 256 plus 64 plus 13 plus 8. This has no formula. We derived it there. We checked that there were 13. What was the combination? This was the combination for prime implicants. There is no certain formula, but we checked in this manner. This was the combination as far as I remember. Here you don't need to make a quad. Here also you don't need to make a quad. So to avoid the quad, you will write one here and you will write one here. So total 13 combination we were getting. So this you need to add up. 260, 320, 320 plus 21, 320 plus 21, so 341. Third 72 plus 13, 85, 85, 356 minus 15, 341. So yeah, that's it. That's the answer. Okay. F1, F is equals to F1 dot F1 dot F2 is given. F1 is given and F is given. So what can be F2? Can you solve it on your own? So F is equals to F1 dot F2. What does that mean? We will take the common ones. So what F2 can be? F2 can have, F2 will certainly have 4, 7, 15 because 4, 7, 15 are there. So they will certainly be there. 4, 7, 15. 4, 7, 15 will certainly be there. It cannot have 0, it cannot have 1, it cannot have 2, it cannot have 3. These it cannot have. Why it cannot have? Because let's just say in F2 if there was 2, then common part would have been 2, 4, 7, 15. So this would come here. But here 4, 7, 15 are coming, that means 2 is not there. What else it can have? It can have 5 as well. It can have 6 as well because 5, 6 are not there. 7, 8, 9, 10 is there. 12 it can have, 13 it can have, 14 it can have. So it can have these many variables. These and these 6 it can have. Okay. So we need to check it by making the K-map only. So first one is BC plus BD bar. Okay, this is 4 variable. BC plus BD bar. Let's take it to the next page. Or what I can do, I will just write down the min terms. So first option is BC plus BD bar. Can I write down the min terms? So it would be A, B, C, D. Min terms will be a lot. But let's do it. We have to do it. So B is 1 and C is 1. A, B can take 0 value. They can take 0, 1 value. They can take 1, 0 value. And they can take 1, 1 value. Are you getting this point? How did I write those? Look, B and C are there, both are 1. So 0, 0, 0, 1, 1, 0, 1, 1. A and D will have all the variables 0, 0, 0, 1, 1, 0, 1, 1. Here B is 1 and D is 0, that is fixed. So 0, 0, right? These are fixed 0, 1. These are fixed 1, 0. And these are fixed 1, 1. Okay. So which all being are repeated twice? This is being repeated twice, so I can erase it. 1, 1, 1, 0 is being repeated twice, I can erase it. 1, 1, 0, 0. Yeah, that's it. So 1, 2, 4, 8. So 6. This is being 6. 1, 2, 4. This is 7. 1, 2, 4, 8. Basically 1, 2, 4, 8. This is 14. What about this? This is 15. What about this? 1, 2, 4. 4. 1, 2, 4, 8. This is 12. So this is having 6, 7. 6 is acceptable, 7 is acceptable, 14 is acceptable, 15 is acceptable, 4 is acceptable, and 12 is acceptable. Yes, this is correct. Okay, let's check for the next option, that is B C bar plus BD. So E 1, 0 is fixed, 1, 0 is fixed, 1, 0 is fixed, 1, 0 is fixed. 0 0 0 1 1 0 1 1. Okay, so this is, what about this BD? 1 1 is fixed, 0 0 0 1 1 0, sorry, what I am doing, 1 1 is fixed, 1 1 is fixed, 1 1 is fixed, 0 0 0 1 1 0 1 1. So which is being repeated? 0 1 0 1 0 1 1 1 1 0 1 1 1 0 1. This is being repeated. Let's check this out. This is 4, this is 5, 4 5 are accepted, 8 4 12, 12 is also accepted. This is 13, 13 is also accepted. This is what? This is 7, this is also accepted. This is 15, this is also accepted. So 4 5 12 13 7 15 all are accepted. This is also correct. So this is also correct. Then when you solve these two, these will not be correct. Okay, you can check on your own. These will not be correct. As far as I remember, these will not be correct. So this is how you need to solve. This is also very interesting one. Boolean expression is equals to. So do you remember about this function? If you remember the chapter, AB plus BC plus CA, let me write it down as F dash. Do you remember this particular expression? This is what? Self dual. This is self dual function. And if it is self dual function, that means F dual is equals to F. So dual of this will be AB plus BC plus CA. And if I have the dual, that means for getting the complement, from here if I need to get the complement, so what I need to do? If I need to get the complement, then I just need to put the complement on the individual terms. I just need to get the complement on individual terms. So individual terms I am putting the complement, so this option is correct. But it is an MSQ. MSQ. I forgot to write it. Will this option be correct? Yes, certainly. Let's talk about option B. A bar, B bar. Can I write this as A bar, B, C bar? Because my target is to eradicate this B. So here I can see B bar. So something I can do here now. Plus B bar, C bar. So A bar I can take common here. B bar plus B, C bar plus B bar, C bar. A bar, now what can happen to this one? B bar plus B, C bar. That would be B bar plus C bar. Say yes or no? Say yes or no? X plus YZ. Sorry, X plus X bar Z. This is X, X plus X bar Z would be X plus Z only. So that I have done. B bar plus C bar. Plus B bar C bar. So here what I am getting? A bar B bar plus A bar C bar plus B bar C bar. So this option is also correct. What about this one? Try solving it. Option C. So A bar, I am just multiplying A bar into C bar plus A bar into B bar plus B bar into C bar plus B bar into A bar. So here A bar B bar is being repeated twice. So if I solve it, what I am getting? A bar B bar plus A bar C bar plus A bar C bar plus B bar C bar. So this is also correct. What about this one? So when we study combination circuit, we will get to know that AB plus BC plus CA is equals to AB plus C into A XOR B. But for the option, how would we crack it? So if some function is given, that is, if this function was given, AB plus C A XOR B. So basically AB plus C A bar B plus C A B bar, right? Now can I write down the minterms of this? Certainly I can write down the minterms. So 1 1 0 1 1 1. Considering A as I am considering A as MSB. So 0 1 1. This is 1 0 1 1 0 1. Okay. So these are the minterms. What I am getting? What I am getting? 3 1 2 4. So 5 6 7. So minterms are 3 5 6 7. What about this? AB plus BC plus CA. what will be the minterms of these? Can you write down the minterms of these? AB plus BC plus CA. AB plus bar is there, bar is there. So basically bar is there in both. What I am doing, I am checking if both of these functions are having the same minterms. If they are having the same minterms, that means they are equal. So I am checking the minterms of these. So I will check the minterms of AB plus BC plus CA. So AB plus BC plus CA. So AB are constant, BC are constant, AC, right? AC are constant and B will have. So this 1 1 1 will get cancelled. So now what about this 1 1 0 1 1 1 0 1 1 1 0 1. So here also you can get to know that these binary only you can check 1 1 0 0 1 1 1 0 1 1 1 0 1. Here only you can check that all are equal only. So both minterms are equal. Both are equal. And if both minterms are equal, that means certainly this option is also correct. Say yes or no. Right? Minterms are equal. That means certainly this option is also correct. Let's move to the next one. If inputs ABCD equals to 1011 1001 and 1011 never occur, then simplified expression. What do you understand by this? That ABCD equals to these never occur. Then that means that if my input is 1001, then I do not need to care about output, because this will not even come. I don't know what will be the output if 1001. This condition will not even come. So these are don't cares. So which all are don't care? Basically, if the input, if I have a system, okay, I have a system, I have a digital system, and these are my inputs. These are my inputs. A, B, C, D. This is my system, and these are my inputs. So if these systems are 1001 and 1011, then I do not need to care about output. What will be the output? I do not need to care about the output. Output will be some whatever the output is. I do not need to care about that. So that means they are my don't cares, right? So 1 2 4 8 9 1 0 1 1 1 2 4 8 10 11. So these conditions will not come. So I do not need to care about the output. So 9 11 1 2 4 8. Yeah, 9 11 9 11. 1911 is very risky, na? 19 November. Do you remember what happened on this date? Huh? But 24th June is also there. You guys remember, certainly remember what happened on this day. Not June. Yeah, 24th June only. Okay, yeah. On this day, I left Bangalore and came full time to teaching. That day we won World Cup. Yeah. So don't care are 9 11. And simplified Boolean expression they are asking for this particular one. So I will have to again make a K-map. Again I will make K-map because there are don't care terms. So if there are don't care terms, then I will solve it by K-map. A, B, C, D. This would be A bar, B bar, A bar, B, A, B, A, B bar, C bar, D bar, C bar, D, C, D, C, D bar. So A bar, B, A bar, B, C bar, D, A bar, B, C bar, D, A bar, B, sorry, A bar, B bar, A bar, B bar, D, A bar, B bar, D, A bar, C, D, A bar, C, D, A bar, C, D, A bar, C, D, A, B, D, A, A, B, D, A, B, D, A, B, D, A, B, C, A, B, C. And which all are my don't cares? 9 and 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 8, 9, 10, 11. So these are my don't cares. 8, 9, 10, 11. So what I can see here? Directly I can see a octet. Can I make a quad from here? No, I cannot make a quad. So this has to be there. So here only D is constant. So D plus, what about this one? So C is varying. Basically C is constant and AB is constant. So ABC. So Y is ABC plus D. Very easy expression I am getting. Look, this would have been very complex. But if I need to implement only this, then it would be very easy for me. I just need to use two gates, A, B, C, and then D. Would be very easy. If I had to implement this, then a lot of hardware will be used. So that's these kind of applications are there. That's why we study this Boolean algebra and logic gate. So these are working as a prerequisite of our actual digital electronics. So actual digital electronics will start from combinational circuits. So these all are the prerequisites which we are doing. Okay, so I hope you are able to understand these problems. Let's move to the next one. Truth table is given. To get the simplest Boolean expression of y, what should be the value of x1 and x2? So again, I will have to make the x1 and x2 are don't cares. Okay. So again, I will have to make a k-map. अरे यार इस बार 3 वेरिएबल्स का था मैंने. Actually my health is not that well, but since a lot of work is there, we cannot postpone making the video. So A, B, C. So at 0 you are having 1, 0, 1, here you are having x1, 2, 3, 4, 5, 6, 7, 5, 6, 7. Now this group is there. I will make this as a group as well. Bas. That's it. Why would I use this x2? So x2 should be 0 and x1 should be 1. I will get the minimized Boolean expression. Again, good, very easy. So in that manner we need to solve. Let's solve this question. Find the number of prime implicant and essential prime implicant. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Can I make a quad? Can I make a quad? No chance. So 1, wait a second. 1, 2, 3, 4, 5, 6. Any other options are there? No. So 6 prime implicants. What about essential prime implicants? If you go to this group, this guy is alone. This guy is not alone, 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 this guy is alone. So only 2 groups guys are alone. So 2 essential prime implicants. Made all the groups and then I go to know 2 essential prime implicants are there. Let me check it again if there is any quad possible. Quad is not possible. Again I have checked, every time I have checked, quad is not possible. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in that manner it will go, only 2 prime implicants are there. That is the correct answer. Okay. Now this is also a very good question. Find the minimum possible literal count and this is given 1, 5, 1, 5, 6, 12, 13, 14 and don't here are 2, 4. Solve it on your own and tell me the answer. So it is 4 variable ones. Okay. If your answer is 7, then you haven't solved this assignment with a good amount of patience. You just skipped the problems. If your answer is 7, if your answer is anything other than 7, then it is good. A, B, C, D. Okay, so I will start 0, 1, 2, 3, 4, 5, 6, 7. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 13, 14. Okay. So Without using don't care, I cannot make any quad. So this one at least I will have to use. One quad is there. This can go with this one. This can go with this one. That's it. Three groups are there. 0 0, A bar, B bar, A bar, B, A B, A B bar, C bar, D bar, C bar, D, C D, C D bar. So Y is equals to, in this group B is there and C bar is there, B C bar, plus in this group which is constant, C bar D is constant also, C bar D is constant also, A bar is constant, A bar C D bar, plus in this group wait a second, this group is wrong, right? This group is wrong, this grouping is wrong, this is 1 1. So I can make a quad here, no? I can make a quad. So this grouping was wrong. These kind of blunders we should not make in the examination. I can make a quad, right? This is a quad. So when we write down the expression, it will come to you. Right? When I was writing down the expression, I got to know that this is a quad there. So D bar D bar B, B D bar. How many literals are there? 1, 2, 3, 4, 5, 6, 7. Answer is 7. Wrong. Why? Why it is wrong? I told you, whenever there is don't care can give different SOP and POS. Different SOP and POS. Both can be different. So if you are solving this problem with SOP, you need to solve it with POS as well. And you need to check whether you are getting minimized expression here or not. So 0, whenever there is don't care, you always need to check 7, 8, 9, 10, 11. 2 and 4 are don't care, so don't include these two. 2 and 4 are don't care. So 0, 3, 7, 8, 9, 10, 0, 3, 7, 8, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 15. Don't care will not change because this cross will be cross only. Basically 2 and 4 will never occur. If 2 and 4 are occurring, then you don't need to care about the output. That means 2 and 4 will never occur. If 2 and 4 will never occur, that means whether you are calculating from SOP or you are calculating from POS, they will never change. So these 2 and 4 will remain there as it is. Okay, so now again we will have to make the K-map. A, B, C, D. No. A plus B, A plus B, C plus D. A plus B, C plus D. First let's fill it. 0, 3, 7, 8, 9, 10, 11. 0, 1, 2, 3. 0, 1, 2, 3. 2 is don't care, 4 is don't care. 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 8, 9, 10, 11 and 15. One quad is there. Wait a second. 1. Okay. 2 and 3. All quads are there. All are quads. If all are quads, that means this will give me two literal count, this will give me 2 literal count, and this will also give me 2 literal count. So 2 plus 2 plus 2, literal count will be 6. So that would be the answer. Okay, so a lot of times I did not find these kind of problems in anyone's notes. I actually read all teachers' notes. Okay, I will be honest with that, because I need to see what they are teaching, so that I could improve my content. So there is nothing wrong in admitting that I have seen all the teachers of notes, all the notes of the teachers which all are teaching digital electronics in this GATE field. So there I did not find these kind of problems. I don't know why, but these kind of problems will certainly come up in your examination. Okay, C plus D, C plus D bar, C bar plus D bar, C bar plus D. So here what did you get to know? First let's check this one. Y is equals to C bar plus D bar, this is constant. In this one A bar plus B is constant, and this one here, if we go here, so D is constant, and if we go in these ones, then B is constant. D is constant and B is constant, so D plus B. So what is the literal count? Least count, sorry, least count is 6. That means what is the minimum number? That is 6. This is wrong. Okay, so that you need to take care. If there is don't care, then the question will be solved with K-map only. Also you need to solve with POS and SOP both, because which one will give you least literal count, that you don't know. So minimum possible literal count is 6, not 7. So that was a very good question. Okay then, so that is the end of the assignment. I hope you must have understood everything. So this is the end of our chapter. In this chapter we have covered logic gates, Boolean algebra we have covered already. Then we have covered representation of Boolean expression, and we covered K-maps. So in that manner we have concluded our second chapter, or you can say our first chapter. Now we will move towards number system. So number system will be a different topic, and then we will start combinational circuits. So everything that we have studied in these 3 chapters will be used in combinational circuits. So from there onwards we will start combinational circuits. Okay then, thank you very much. If you are finding it helpful, please do share it with your friends, with your batchmates, with your colleagues, or anyone, senior, junior. You just need to share it if you are finding it helpful. Okay, thank you very much. Hi everyone. So in this video we are going to start our new chapter, that is number system. Now in number system, first we will study number system, then we will study the operations, then we will study the codes, then we will study the operation of the codes, and then we will see the complements. So basically these five topics are there. You can tell the chapter name as number system and codes. So this is the complete chapter name, number system and codes. So those we are going to study. Now while studying this particular chapter, you might have some doubt that, sir, we are doing it, but where we will be using it? This question will be coming, sir, where we will be using it? So where you will be using it, that answer will be given in the next chapter, that is combinational circuit. So when you are done with the combination circuit, your all the doubts will be answered, that, sir, where we will be using it. Here you will be understanding the concept, but the question that, sir, where we will be using it, that will be answered in the next chapter. Where you will use it, why we are studying it. So here I will tell you certain things. You need to accept that we are studying that thing. Where we will be using it, that you will study later on. Okay, so let's start with the number system. So there are different kind of number systems. So first one is the decimal, that we already know. Decimal number system we already know. Let's just say what is the base of decimal number system, that is base 10. Why do I call it base 10? Because there are total 10 number possible. 10 digits are possible. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. These 10 digits are possible in binary number system. Sorry, in decimal number system. Let's just say there is some number written 93. So I have made this number from using 9 and using 3. So 2 digits I have used, that is 9 and 3. Right? So there could be examples. Basic what we already know, that is example is 93. Right? So here 9 is there and 3 is there. So this number is acceptable. If I write example 127, so this number is also acceptable, because 1 digit is used, 2 digit is used and 7 digit is used. So this number is also acceptable. But if I write A32, so you know that there is a digit called 2. There is a digit called 3 as well. But there is no digit called as A. We don't know what is A. There is no kind of digit called as A. So this is not acceptable. This is not a number. A32 when there is base 10, a cannot be a number because maximum number can be 9 only. Maximum we know till 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Maximum we can go till 9. You will not say, sir, here you have used 12. No, I did not use 12 here. Here I have used 1 and 2. Right? This is not 12. So no one will say that, sir, the number is 12 here. So you have used 12. Nah. I am using digit 1, digit 2 and digit 7. So we know all these digits. We know 1 as well, we know 2 as well, we know 7 as well. But we do not know what is A. So this number is not acceptable. In binary, what is the base? Base is 2. Base is 2, that means only 0 and 1 are known. Nothing else. That's it. 2 base means there will be only 2 numbers that are 0 and 1. So only 0 and 1 are known. So if I write a number which is 0, 1, 0, will this be acceptable? Yes, surely. If I write another number, let's just say 1, 0, 0, will this be acceptable? Yes, I know all the numbers. If I write this number 2, 1, 0 and I say the base is 2, will that be acceptable? No. This will not be acceptable. Why? Because you do not even know the number 2. If the base is 10, that means you know only 0 and 1. If the base is 2, that means you know only 0 and 1. If the base is 10, that means you know from 0 to 9. But now you do not know 2 because the base is 2 only. So you know 0 and 1 only. If base was 10, that means you know from 0 to 9. If base is 2, that means you know from 0 to 1 only. So this is not acceptable. Or 7 to 0, this will also not be acceptable because you do not know 2, you do not know 7. This will also not be acceptable. Octal means base 8. Base 8 means how many numbers would be there? You can write it on your own. 1, 2, 3, 4, 5, 6 and 7. Till 7 will be acceptable. So what all the examples can be there? If I write 723, so yes, that is acceptable. I know 7, I know 2, I know 3. But if I write 982, will that be acceptable? No. Why so? Because I do not know I do not know 8, I do not know 9. So that is not acceptable. If I write 777, will that be acceptable? Yes. Because I know 7, I know 7 and I know 7. So that will be acceptable. Hexadecimal means base 16. What do you mean by base 16? From 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 till 9. And then 10 will be there, but 10 we cannot write 10 because 10 is made from 1 and 0 only. So we cannot write 10. So we will write A, B, C, D, E, F. Base 16 means from 0 to 15 you will have, right? From 0 to 15. Total 16 numbers will be there from 0 to 15. So 9, 10, 11, 12, 13, 14 and 15. So F is 15. But we will not call it 15 because 15 is made from 1 and 5. So I have to write it in terms of A, B, C, D. So F is 15. Okay. So if I take examples, let's just say I write example of 923 in 16 base. Will that be acceptable? Yes, surely. Why that will not be acceptable? That will certainly be acceptable, right? Because 9 you know, 2 you know, 3 you know. If I write example D, E, F 16, will that be acceptable? Yes, that will be acceptable because D you know, E you know, F you know. If I write the example D 7 F, will that be acceptable? Yes, that will also be acceptable because you know D, you know 7, you know F. If I write H 9D, will that be acceptable? And base is 16. 16 means you can have till F only, you cannot have H. So that will not be acceptable. Are you getting this point? So that's the thing. So if base R is there, that means the number will, these are the most important ones, decimal, binary, octal and hexadecimal. In those only these two are important. And if we are studying digital circuit, then binary is more important. If you are studying mathematics, then decimal is more important. Okay. So base R is there. If base R is there, then the number will start from 0, 1, 2 till it will go R minus 1. And if the example is there in that manner, that there is some alpha, beta, gamma is written with base R, that means R has to be greater than alpha, beta has to be greater, R has to be greater than alpha, R has to be greater than beta, and r has to be greater than gamma as well. Then only this number will be acceptable. Otherwise, this number will not be acceptable. Are you getting this point? The return base has to be greater than all these values, alpha, beta, gamma. Then only it will be acceptable. If it is even if it is near, even if it is near, that is, let's just say 2 is there. So even if it is near means even if it is equal, then also it is wrong. It cannot even be equal. It has to be greater. Okay. And yeah, other examples. Let's just say here I take example of point that I did not take. So if I am writing 72.32, yes, certainly it is acceptable. Later on we can take the example. Here we can take the example. So in the example, if I take in point, if I take 729.32, this is acceptable, right? But if I take 8D2 point F3, this is not acceptable. If I take 794.3B, this will also not be acceptable, because all the number has to be in the base 10. So in points as well, it will follow the same thing. In points as well, it will follow the same thing. Just whatever the number you see, you should be knowing that number. So in 10 base, I do not know what is F. In 10 base, I do not know what is B. So all these are not acceptable. Now tell me one thing. If this number is written 2743, can I write this number as 3 into place value of 3? What is the place value of 3? 10 to the power 0. Plus 4 into place value of 10, that is 10 to the power 1. Sorry, place value of 4. Sorry, 4 into place value of 4. 7 into place value of 7, that is 10 to the power 2. And 2 into place value of 2, that is 10 to the power 3. So I can write it in this manner. So basically it is 2000 plus 700 plus 40 plus 3. And if you do the calculation, you will get the same number. Say yes or no? And the number you are getting in decimal, because the calculation that you are doing is in decimal. This calculation, whatever the calculation I know, that is there in decimal only. So you are getting the same number. Similarly, how will you write this? You will start from this point. You will start from this point. What will be the decimal value of this one? That would be 10 to the power 1. What will, sorry. This would be 10 to the power 0. What will be the decimal value of this one? That would be 10 to the power 1. What will be the decimal value of this? 10 to the power minus 1, right? Because if I write 3 into 10 to the power 0 plus 4 into 10 to the power 1 plus 5 into 10 to the power minus 1. So that would be 3 plus 40 plus 5 into 10 to the power minus 1 would be 0.5. So what I am getting? 43.5. Okay. You can write it down on your own. So what that would be? 9 into 0, 1, 2, 3, 4, 5. So 9 into 10 to the power 5 plus 7 into 10 to the power 4 plus 3 into 10 to the power 3 plus 2 into 10 to the power 2 plus 5 into 10 to the power 1 plus 6 into 10 to the power 0 plus 5 into 10 to the power minus 1 plus 3 into 10 to the power minus 2 plus 7 into 10 to the power minus 3 and plus 4 into 10 to the power minus 4. Basically we start from this point and we take base 0, 1, sorry, power 0, 1, 2, 3, 4, 5, 6, power minus 1, minus 2, minus 3, minus 4. In that manner we go. Okay. Let's remove it. Now similar thing if we are doing in base 2, that is binary. Let's take some examples which is acceptable. 110.0101 if base 2 acceptable. If I write 110.201 base 2 not acceptable, because the number 2 I don't know. If I write 310.21101 not acceptable, because number 3 I don't know. Here as well the same thing is there. How you can write it? What is the place value of this? 2 to the power 0. What is the place value of this? 2 to the power 1. What is the place value of this? 2 to the power 2. And what is the place value of this? 2 to the power 3. Here the base was 10. That's why the place value was 10 to the power 0, 10 to the power 1, 10 to the power 3, 10 to the power 4. Here the base is 2. That means these are the place value. So 1 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3. So what you will be getting? 1 plus 0 plus 4 plus 8. Now you will say that, sir, you do not even know this number in this base. I do not even know what is 4. I do not even know what is 8 when there is base 2. Yeah, I don't know. I am implementing that in decimal. I am representing this binary number into decimal. So what I am getting? So 13. So if 13 is there in decimal, then how it will look in binary? It will look like this. Are you getting this point? 13 in decimal will look like this in binary. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 1 into 2 to the power 0, 1 plus 0 plus 4 plus 8. So that is 13. What about this one? How it will look? So 1 plus 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus what will be the base value of this one? Can you tell me? Place value of this, that will be 2 to the power minus 1 and this would be 2 to the power minus 2. So 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. So that would be 1 by 2 plus 1 by 4, right? 0.75, and we can add this up. That would be 1 plus 4, 5. 5.75, and this number I am denoting in decimal. So 5.75 will look like this. Okay, let's solve this one. 1 plus 2 plus 4, 8 plus, are you getting this point? What I am doing? 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 to the power 3. Sorry, 0 into 2 to the power 2, that is 0 only, plus 1 into 2 to the power 3, that is 8, plus 0 into 2 to the power 4 plus 1 into 2 to the power 5, what that would be? 32, and plus 1 into 2 to the power 6, that would be 64. Now what I will do? 1 into 2 to the power minus 1, that would be 1 by 2, plus 0 into 2 to the power minus 2, that would be 1 by 4, plus 1 into 2 to the power minus 2, that would be, sorry, 1 into 2 to the power minus 3, that would be 1 by 8. Got it? Right? So let's solve it. We can use calculator. Why should we use our brain when you are having calculator? 40, 104, 104 plus 3, 107. This is very easy. 107. What is 1 by 8? 0.125, right? 0.125 plus 0.5, that would be 0.625. So that's it. I did not use calculator. Okay, let me check it again. 104, 104 plus 3, 107, and 1 by 8 is 0.125 plus 0.5. Yeah, 0.625. No, you need to use calculator. We are smart. Look, I am really on low confidence when it comes to calculation. Okay, I am not that confident in calculation, so that's why I always use calculator even for the minor calculations, because so that I can avoid calculation mistake in the examination. So 104. So yeah, this is how you will denote it in decimal. I hope you have got the point. 1 into 2 to the power 1 plus 1 into 2 to the power 2. Sorry, 2 to the power 0. From 0 it will start. 0, 1, 2, 3, 4, 5, 6. In that manner we are going. 0, 1, 2, 3, 4, 5, 6. Yeah. Okay. If octal is there, that means base is 8. So from 0 to 7, all the numbers will be there. If we take some examples, what those examples will be? 724. That would be acceptable? Yes. If you take 872.78, no. And if you take 971.33, that is also not acceptable, because 9 number I do not know. That I am talking about base 8. Now, what will be the place value of 2? 8 to the power 0. Plus, what will be the place value of 7? Wait a second. Yeah, okay. 1. What will be the place value of 7? 8 to the power 1. What will be the place value of 4? 8 to the power 3. What will be the place value of 6? 8 to the power 4. You can calculate it and you will get the answer in decimal. Whatever the calculation you do, whatever you get, you will get that answer in decimal. I guess we can calculate it. So 48 plus 52, 52 into 8 to the power 3. So one calculation I will do. So 8 6 जा 48, 48 4 52, 52 into 8 to the power 3, 8 to the power 3 into 52 plus 56 plus 2. So I am getting 26682. 26682, but that is in decimal. Okay, if I have written 1011, will I say that place value of 1 is 2 to the power 0? Is that so? Will I say place value of 1 is 2 to the power 0? No, no, no. I will check the base. It seems like that it is a binary number, but no, you need to check the base. Base is 8, so it is a octal number only. So 8 to the power 0 plus 8 to the power 1 plus 0 into 8 to the power 2 plus 1 into 8 to the power 3. Wait a second, wait a second, wait a second, wait a second. Here this is having base 2. Why I am doing these blunders? And this is having base 3. This is wrong. Sorry. So what we will get? 8 to the power 3 into 6 plus 64 into 4 plus 56 plus 2. 3386. 3386. Okay. Here 512 plus 9. 512 plus 9. 521. Okay, this would be 512 plus 9. Here base 8 to the power 1, 8 to the, yeah. So we will not be able to calculate this certainly because it will be a huge number, but we can write down the place values. So we will start from 6. So 6 into 8 to the power 0. This will have 8 to the power 0. This will have 8 to the power 1. This will have 8 to the power 2. This will have 8 to the power 3. This will have 8 to the power 4. What about this one? This will have 8 to the power minus 1. This will have 8 to the power minus 2. And this will have 8 to the power minus 3. So in that manner you can write and you will get your final answer. Okay. Same goes for hexadecimal. Base till f. Numbers will be till f. Acceptable number, what that would be? 923.f e. Will that be acceptable? Surely. If I write 92g.he, will that be acceptable? No. If I write klp dot 67, will that be acceptable? No. Okay. So 953 base 16. So how we will denote it in decimal? So 3 into 16 to the power 0 plus 5 into 16 to the power 1 plus 9 into 16 to the power 2. So 16 to the power 2 into 9 plus 16 पंजे 80 plus 3. So 2387. 2387 in base 10 I am getting. This is in the decimal because all these are decimal calculation. And what about this? What is f? F is 15. So 15 into 10 16 to the power 0 plus what is d? D is 13. 13 into 16 to the power 1 plus what is 9? 9 is 9 only. 16 to the power 2. This is 16 plus 4 into 16 to the power 3 plus 5 into 16 to the power 4 plus what is C? 10, 11, 12. 12 into 16 to the power 5. So 0, 1, 2, 3, 4, 5. That's it. You will do the calculation. You will get the answer in decimal. Right? What about this one? So here this will have the base 16 to the power 0. This will have 16 to the power 1. This will have 16 to the power 2. This will have 16 to the power 3. And this will have 16 to the power 4. What about this one? This will have 16 to the power minus 1. This one will have 16 to the power minus 2. And this one will have 16 to the power minus 3. And you can add them up and you will get the number in decimal. So if you want to convert any base to decimal, then what is the scene? How can you convert this number to decimal? Tell me. What is the place value of this? 5 to the power 0, 5 to the power 1 and 5 to the power 2. any value to decimal. And what is the place value of this? 5 to the power minus 1 and 5 to the power minus 2. So you will start from the number which is left to the point. 5 to the power 0, 1, 2. 5 to the power minus 1, 5 to the power minus 2. Okay. So 3 into 5 to the power 2, that is 3 into 25 plus 4 into 5 plus 2 into 1. 5 to the power 0 is 1 only, plus 1 into 5 to the power minus 1 plus 0 into 5 to the power minus 2, that would be 0 only. So 20 95 75 और 20 95 95 plus 2 97 97 by 97 plus 1 by 5, that would be 0.2. So 97.2 in decimal you are getting. Okay, 97.2. Okay, 75 20 95 plus 2 97 1 by 5.2. So this would be a bit tough calculation. So what A will have? 0 1 2 3. So A 10 will have 16 to the power 3 plus 2 will have 16 to the power 2 plus 7 will have 16 to the power 1, and F, that is 15, that will have 16 to the power 0 plus this C, that is 12, right, that will have 16 to the power minus 1. So if you calculate this, what you will get? Let's check out. So 16 to the power 3, 16 to the power 3 into 10 plus 16 square into 2 plus 7 into 16. Arey yaar. Let me pause it and do the calculation. So you are getting 41599.75. Okay, let's do the calculation here. 2 into 9 to the power 0. So this is 9 to the power 0, 9 to the power 1, 9 to the power 2, 9 to the power 3. So 8 into 9 to the power 3 plus 7 into 9 to the power 2 plus 6 into 9 to the power 1 plus 2 into 9 to the power 0, and this would be equal to 9 to the power 3 into 8 plus 81 into 7 plus 54 plus 2. So 604.55 with base 10. So from any base to decimal you can convert now. That would be very easy. Now if you want to go from decimal to any base, then how will you go? Like from decimal to base 2, base 16, base 8 and or base R. So let's understand the method by a simple example. So first we will take the example of decimal to binary. The method is same. What you will do? First you will pick this number, that is 73. You will pick the integer part. This is the integer part. So first you will pick the integer part, that is 73. So integer part I am picking, that is 73. Now what is the number here? That is 2. So now I will divide 73 by 2. What we will get? 36, and remainder is 1. So here I will write my remainder. Remainder is 1. I will again divide. What I will get? Remainder as 0. Now again I can divide, right? I can divide by 2 again. What the remainder I will get? 0. Then again I can divide by 2. What remainder I will get? 2 4 ja 8. I will get remainder as 1. Then again I can divide by 2. What I will get? 2 and remainder 0. Then again I can divide by 2. What I will get? 2 1 0. If I divide by 2 again, what I will get? 1 0 again, right? If I divide by 2 again, then I will get the same number because 1 is not divided by 2. Basically this number is less than 2. This number is less than 2, right? So here I will stop. Now what I will do? I will go from down I will go from down to up. I'm going from down to up. So going from down to up, what all number I am getting? 1 0 0 1 0 0 1. Surprisingly from up as well I am getting the same number. But don't get confused. I am going from down to up. Okay, that is a big blunder from my side. From down to up and from up to down I am getting the same number. So 73 can be written in this manner. But we need to do something of 0.25. So what I will do? 0.25 I will pick. Now I will multiply by this base, that is 2. So 2.5 by 2, that is 0.5. 0.5 by 2, 0.50 into 2, what I will get? 1.0. 0.0 into 2, what I will get? 0.00 only. What I am doing? Okay, sorry, I forgot to tell the method. 0.25 into 2, what I am getting? 0.50. So whatever I am getting after 0.5, that I am picking here, 0.50. Then into 2, 0.50 into 2, whatever that I am getting here, that I am picking here into 2. So I can keep on doing this, 0.00 into 2. So again I will get 0.00 only. So in that manner I can keep on doing it. I need to just do it for 3-4 digits. Okay, that would be more than enough. So for 3-4 digits, but now I will be writing from up to down. Okay, you do not need to do it till 0.00. You can do it for 3-4 digits, 3-4 numbers. Okay, it's not necessary that you need to go till 0.00. Till 3-4 number you need to do. So I am going from up to down now. So that would be 0.01. So 0.25 can be written as 0.01. So this is what? This is 73. And this is what? 0.25. So if I need to write 73.25, so what I will write? First I will write 73, that is 1001001. I will start writing from the below, 1001000, 0.01. That's it. I will start writing from the upward side. Okay, are you getting this point? We will take more examples. Let's take more examples. We need to convert it to base 8. How will you do it? Base 8. So 739 is there. So first I will pick the 739 part. Now I will do the division. So this I will get 8 9 ja 72, 9 2 ja 18. So one remainder I am getting. Eight 1 ja 8, 8 1 ja 8. What remainder you are getting? 4. Then again do the division. 8 1 ja 8. What remainder you are getting? 3. You will go from down to up, right? So 1 3 4 1, point something will come. 1 3 4 1. Now point something will come. 0.26 into 8. What do you get? 0.26 into 8, 2.08. 0.08 into 8, what you will get? 0.64. 0.64 into 8, 0.64 into 8, 0.64 into 8, 5.12. 5.12. I just need to look at the integer part only. Now again I can do 0.12 into 8. I can keep on doing it. 9 point, what I will get? 0.12 into 8, 9.6, right? 0.12 into 8, sorry, 0.96, sorry, 0.96, 0.96, really sorry, 0.96. So I can keep on doing it, I can keep on doing it, but I just need to write till 3-4 digits. I will go from up to down, up to down. So what is the number I am getting? Only the integer part you need to look. 2050. After point, basically, what will be my correct answer? 2050. Okay, in base 8. So you just need to look at the integer part. 20 here. What was the integer part? 0100. So that I wrote 0100. Also I could have written, basically in ahead of that I could have written 00 as well, but that is of no use. So that's why I did not write. So solve this on your own for 16. 7932. 7932. 16. Okay, so 7932, let's divide it. 7932 by 16, what you are getting? 495.75. that means 495 into 16. Here you will get 495 minus 7932, and here you will get 12. And what is 12? C. 12 is C. This is C. 16. 480, and you will get 15 here. What is 15? F. And again divide by 16. We divide by 16, so 16 1 ja 16, and what you will get here? 14. What is 14? E. So if you go from up to, sorry, down to up, so what all number you are getting? 1 E F C. Now in point something will come. So 0.67 into 16. 0.67 into 16 and into 16, that is 10.72. 10.72, and 10.72 will be written as A.72. 0.72 into 16. 0.72 into 16, that would be 11.52, and 11.52 will be written as B.52. 0.52 into 16. 0.52 into 16, that would be written as 8.32. So you can keep on doing that, but till a few step only we need to write it. Now we need to look at only integer part. Only the integer part. What is that? That is A, B, 8. So in that manner, will you be able to remember how to proceed in these kind of problems? Next problem you will solve on your own. From this to base 6 you need to convert. So base 6, what you will do? 8914. 8914 to base 6. So I will divide by 6. So 6 1 ja 6. 6 चौकी 24, 5 48, 3, 4. Let me confirm it. 485 into 6 plus 4. Okay. Divide by again 6. 3. 247 into 6 plus 3. 485. 6. 1. Again 6. 5. And then again 6. 6 1 ja 6 and 0 remainder is there. So let's check. 6 1 ja 6, 4, this was correct, this was also correct. 3, 1, 5. Okay. So let's go from up to down. Sorry, from down to up. So that would be 1 0 5 1 3 4. Point I need to write. So 0.73 into 6. 0.73 into 6. 4.38. 0.38 into 6. 0.38 into 6. 2.28. 0.28 into 6. 0.28 into 6. 1.68. 0.68 into 6. 4.08. You can keep on doing it, but let's not do it more for more steps. So you can keep on doing it. You will write from up to down, right? Up to down. 2, 4 to 1 and the base 6. Now what you can do, you can cross check as well. You can cross check as well. How you will cross check? 4 plus 3 into 6, that is 18, plus 1 into 6 to the power 2. 1 into 6 to the power 2. What that would be? 36 plus 5 into 6 to the power 3. What is 6 to the power 3? 6 to the power 3 is 216 into 5. That would be 1080. 1080 plus 6 to the power 4, 6 to the power 5 it would be. This would be 6 to the power 5. So 6 to the power 5. So that would be 7776. And if you add all these, plus 1080 plus 54, 7776 plus 1080 plus 58. So 8194 only you are getting. So this calculation is giving you 8194. Plus you can do 4 into 6 to the power minus 1 plus 2 into 6 to the power minus 2 plus 1 into 6 to the power minus 3. So what that would be? 4 by 6 plus 4. First it would be 4 by 6 plus 2 by 36. That would be 1 by 18. 4 by 6 plus 1 by 18 plus 1 by 6 to the power 3 is 1 by 216. Basically 0.726 you are getting, 0.726. This is what you are getting in decimal, which is nearly equals to 8194.73 only, right? 726, like if you keep on proceeding, what you will get in 6 to the power 4, 6 to the power minus 4, if you keep on doing that, then you will get 73. But we don't need to get exact, this would be the approximate one, right? So that is our answer. So in that manner you can cross check as well. Okay, let's see conversion from any base to another base. From any base to another base you need to convert. So from 5 to 6, how will you go? What do you think? What I can do is that I will first convert it to base 10 and then I will go to base 6, because I can convert any number to base 10. How can I convert this number to base 10? What that would be? 1 into 5 to the power 0 plus 4 into 5 plus 3 into 5, 5 square, that is 25, plus 3 into 25 plus 1 to the power 1 into 5 to the power minus 1 plus 2 into 5 to the power minus 2. That's it. So 75 plus 20, 95 plus 1, 96, 96 plus 0.28, 92.8, 96.28. This is in decimal. Now we need to convert it to base 6. So how will we convert it to base 6? So 96 0 9 16 into 6 is 96 on 0. Yeah, then 6 1 just 6, 6 2 12, 4. That's it. 240 in upward direction. What about 0.28? So 0.28 into 6. Now we are going to convert it in 6. So we just divided by 6, 240, and here we are going to multiply. So 28 into 6, that would be 1.68. Then 0.68 into 6, 0.68 into 6, 4.08, and 4.08. So 0.08 into 6, that would be 0.08 into 6, that would be 0.48. Then it in that manner it can go. So we will write downward. So what that number would be? 240.140 in base 6. So basically 314.12 in base 5 is equivalent to 240.140. That's the answer. So this is how you can convert any base to another base. First we converted it to decimal, then we will go to the other base. Okay, so that's the way we can proceed. Okay, I hope calculation are perfect. So let's move on to our next topic, that is a special case is there. The special case is in terms of binary. So from any binary number to 2 to the power n number system you are going. From binary to any 2 to the power n. So what 2 to the power n can be? 2 to the power, what is 8? 2 to the power 3. What is 12? 2 to the power 2. What is 4? 2 to the power 0. So from binary to any number you are going, from binary to any 2 to the power n you are going, where n is integer. n belongs to, we should say, natural number. When n is a natural number, okay, n is a natural number, 1 2 3 4 5 6 7 8. So from binary to 2 to the power 3 you are going, okay, this is the binary number. So first we are going from binary to 2 to the power 3. So what we need to do, first we need to check this number. What is that? 3. The number is 3. So from here we will start and we will take the groups of 3. 1 1 0, 0 1 0, 1 1 0, 1 1 0, and here only 1 0 you are getting, so another 0 you can put. So groups of 3 you are taking. Now 1 1 0, 1 1 0 in decimal, how you can write that? How you can write 1 1 0 in decimal? Here point is there, here point is there, or let's start from here. So group of 3 3 you have taken. Now let's start 0 1 0, 0 1 0, 1 2 4, 0 1 0. This we have already done, right? 0 1 0, what that would be? 2. 1 1 0, what that would be? 1 1 0, 4 plus 2 6. 1 1 0, what that would be? 6. 0 1 0, 0 1 0, what that would be? 2. 1 1 0, what that would be? 6. 0 1 0, 1 1 0, 1 1 0, 0 1 0, 1 1 0. Point. In that manner here you will go. So what would be 1 1 0? 1 1 0 will be 6. This is 1 1 only, so another 0 you will make. So this number will be 1 1 0. The group of 3 you need to take. So 1 1 0. What would be 1 1 0? That would also be 6. So that is the number in 8. Okay. If I need to convert it to, this was your A, you can say. If I need to convert it to 2 to the power 4, that means 16. So what is the number here? 4. So I have to make the group of 4. So let's remove it off. So let's start from here and make the group of 4. So from point only you will start. 4, 1 2 3 4, 4, 1 2 3 4, 4, 1 2 3. So another 0 I will have to make. So 2 zeros I will have to make here. 1 2 only was there, so 2 0 I will have to make. Now let's start writing. So now you can start writing from anywhere because group of 4 are there. So in group of 4, 1 2 4 8. So what this number will be? 2. What this number will be? 1 0 1 1. 1 0 1 1. So 8 4 12 13. 13. 13 means A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So 13 means D. 1 1 0 1. 8 4 12. Yeah. 1 0 0 1. So 8 1 9. 0 1 1 6. 0 1 1 0 basically. 0 1 1 0. Yeah, that is 6. Point 2D96 it is. So basically it is 2D96 point. What about this one? 1 1 0 1. 1 1 0 1. 1 1 0 1. That is 13. So that is D. Now what about this here? Here you have only 2 number. So you will make 4. You have only 1. So I have to add 3 0. So if I am adding 3 0, so 1 0 0 0, it would be 8. That is in 16. Are you getting this point? I hope you are understanding. 2D96.D8 in hexadecimal. And if you need to convert it to 4, so try doing it on your own. Try doing it on your own. So I will remove all the zeros which I have added. This was the number. So C is from binary to 2 to the power 2. So 2 to the power 2 is 2. So 2 I will start from the point 2 here, 2 here, 2 here, 2 here, 2 here, 2 here, and 2 here. Only till 1 2 I need to write 1 and 2. So let's start. What is this number? 2. What is the next one? 3. What is the next one? 0 1 1. What is the next one? 1 0 2. What is the next one? 0 1 1. What is the next one? 0 1. It was 1 0 2 0 1 1 0 1 again 1 1 0 is 2. 1 0 is 2 only. Point. Again take two numbers. Two numbers. And here also I will have to add a 0 so that I can take two numbers. Here I did not have to add a 0 because perfect grouping was there. So here I will have to add a number. So this is 3. 0 1 will be what? 1. And 1 0 will be what? 2. So that we will be writing in base 4. Okay. And no number is greater than 4. You can see no number is greater than 16. No number is greater than 8. So from binary to 2 to the power n, that means 2 to the power 3 I need to convert, so I will make a group of 3. 2 to the power 4 I need to convert, then I will make a group of 4. 2 to the power 2 I need to convert, so I will make a group of 2. So in that manner I will be proceeding. Let's check from 2 to the power n to binary. From 2 to the power n to binary. So how we will do it? So 742.32 8. So 8 can be written as 742.32. 8 can be written as 2 to the power 3, right? So each number has to be denoted in 3 digits, in 3 bits I should say. Each number should be denoted in 3 bits. Can you tell me how will you write 7 in 3 bits? That would be 1 1 1, because I have 1 2 4. 1 2 4. 4 plus 2 plus 1 7. So 1 1 1. Or you can do 7 is there. I need to convert 7 into, this is a decimal number, right? 7 is a decimal number. Do you accept it? Yes. I need to convert 7 into 2. I need to convert 7 into binary. So basically all the numbers will be, 7 will be denoted in 3 bits. So 7 in 3 bits will be 1 1 1. 4 in 3 bits will be 1 0 0. 2 in 3 bits will be 0 1 0. Now someone will say that, sir, I can write 2 in 0 1 only. Sorry, I can write 2 in 2 bits only, 1 0. No, but you need to denote in 3 bits. 3 bits. 3 bits. 3 bits. Okay. And what about 3? What about 3? So 3 will be 0 1 1. And what will be 2? 2 will be 0 1 0. So 3 bits here as well and 3 bits here as well. That's it. Okay. 2 will be 0 1 0. Now this 0 don't have any value, because after point, let's just say if I am writing 72.50 or I am writing 72.5, both are same, right? So similarly, this is the number, or I can write it in this manner: 1 1 1 1 0 0 0 1 0. This 0 has the value. This 0 has the value, like 70.0360. So this 0 has no value, but this 0 has the value. That's the thing. 0.011 or 0 1. That's it. So this could also be one of the option. Okay, so that's how we need to know. And 7, this was I will tell. This I was telling. 2 3 ja 6 1. 2 1 ja 2. Remainder is 1. So 1 1 1. Okay, so let's just say if you need to denote D, if you need to denote D in 4 bits, D in 4 bits, how you will denote it? What is D? D is 13. I know D is 13. And how I can denote 13? So 8 4 2 1. 8 4 2 1. So 1 13 I need to get. So 8 plus 2 plus 1 will be 13. So 1 0 1 1. 1 0 1 1. This has place value 2 to the power 0. This has place value 2 to the power 1. This has place value 2 to the power 2. And this has place value 2 to the power 3. So 8 4 2 1. So in that manner I will write 1 2 4 8. So 13 will be denoted as 1011. So that we will see in the next slide, hexadecimal. Now you are converting to hexadecimal. So what is 16? 16 is 2 to the power 4. So each number in 4 bits. So what will be 4 bits? 8, 4, 2, 1. So 7 can be denoted as 0, 1, 1, 1. E. A, B, C, D, E. What is E? E is 14. And 14 can be denoted as 8, 4, 12. 12 plus 2, 14. 1, 1, 1, 0. So 1, 1, 1, 0. What about B? What is B? B is 11. And 11 can be denoted as 8 plus 2 plus 1. So 1, 0, 1, 1. 8 plus 2 plus 1. So 1, 0, 1, 1. 1, 0, 1, 1. And what about 2? 2 can be denoted as 0, 1, sorry. Yeah, 0, 1, 0, 0, 1, 0. 2 is 0, 0, 1, 0. 2 is 0, 0, 1, 0. So 4 bits, these 4 bits, and these are also 4 bits. So here, now next is A. A is 10. So 10 can be denoted as 1, 0, 1, 0. 1, 0, 1, 0. Next is 4. 4 can be denoted as 0, 1, 0, 0. Okay. 4 bits, and that's it. So this will be the number in binary. So 4 bits, 4 bits, 4 bits, and 4 bits. Right? Or what all other answer can be there? Will this 0 have any value? No, because if I am writing 072.960, this 0 doesn't have any value, this 0 doesn't have any value. So same thing we can do here. The initial 0 doesn't have any value. 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0.1010, 0, 1, 2. There you go. Okay, each number in 4 bits. So each number in 4 bits. So if you need to convert this to hexadecimal, what you would do? 4 bits. Wait a second. 4. There is some issue. No. And here also 4, but one more 0 you need to put. Here 4 and only 2 are there, so 2 more 0 you need to put. So the same procedure is there. Whatever that you see here, now try to do it on your own. That is 4. 4 is 2 to the power 2. 2 to the power 2. So each number in 2 bits. So 1, 1, 0, 0. 3 can be denoted as 1, 1. 0 can be denoted as 0, 0. 2 can be denoted as 1, 0. 0 can be denoted as 0, 1. 0.3 can be denoted as 1, 1. 2 can be denoted as 1, 0. That's it. That's the answer. Okay. Very easy. Very easy thing. So if there is number from binary to the power n, then you need to put n bits all together. And if there is a number from 2 to the power n to binary, then you need to put each number in n bits. Is that clear? Should be clear. If you are going from any 2 to the power any 2 to the power n to any other 2 to the power n, what you can do? There is one way that you will convert it to base 10 and then can go here. Here also this way was there. Okay, the way was there that you convert it to base 10 and then go here. But we know there is a special case. Here also this was the way, here also this was the way, that you convert it to base 10 and then go here. Base 10 and go here. But it would take a lot of time. So here we know something, that 3 bits clubbed, if 2 to the power 3, that means if 3 bits are clubbed, then it would be, I should remove this. So here I can write 3 bits clubbed together. 3 bits clubbed. This is the starting point. I will go here and I will go there. So 3 bits clubbed. Here I am writing 4 bits clubbed. You need to start from this point. That you need to remember. And here 2 bits clubbed, that you will get to know. Okay. So here also there was the way that you go to base 10 and then go to base 8. But that would take a lot of time. Same thing can be done here, that you go to base 10 and then go to base 4. But what we will do, we will go from here to binary, and then we will go to base 4, because it would be very easy to go to binary. How we will go to binary? 8 means 2 to the power 3. That means each bit in 3 bits. Each number in 3 bits. So 1 1 1, what can be 3? 3 will be 0 1 1, and what will be 4? 4 will be 1 0 0. Point. What will be 2? 0 1 0. What will be 6? 1 1 0. That's it. So this is in binary. Now from binary to 2 to the power 4 you need to go. Binary to 2 to the power 4 you need to go. You went from 8 to this. Basically each number in 3 bits. 1 1 1, 0 1 1, 1 0 0, point 0 1 0, 1 1 0. Okay, now you need to go to, what is 4? 4 is 2 to the power 2. So you need to club 2 bits, 2 bits, 2 bits, 2 bits, 2 bits. Here another 0 I will have to make, 2 bits, 2 bits, 2 bits, and 2 bits. So 0 1 is 1, 3 1 3 0, 0 3 1 3 1. Okay, what about this? 1 1 2. That's it. Okay, so this is the answer. Well and good. So you have went from, oh sorry, this is base 4, sorry, this is base 4. So you have came from here to here, but very easily without converting it to base 10. So that is the way. So this completes our conversion. So we have seen all the conversion in 1 hour. Here I have written a summary. If you need to go from any base to base 10, then what is that? F into r to the power 0 plus e into r to the power 1 plus d into r to the power 2 plus c into r to the power 3 plus b into r to the power 4, in that manner. And here r to the power minus 1, basically this is r to the power 0, r to the power 1, r to the power 2, in that manner we will go. And here r to the power minus 1, r to the power minus 2, and r to the power minus 3, in that manner we will go. And if we talk about this, from base 10 to any base r, so we will divide it, and then we will see the remainder. Here we will follow the approach from up to down, and here we will just get the integer and this part. So this is an integer part, this I am calling some alpha part. So here point alpha part will come and multiplied with r, another I1, this is I2 part. So I2 part would be coming, here some beta part would be there, so some beta part would be coming, multiplied with r, some I3 part would be coming, and then some gamma part will be there. So in that manner we can proceed, and we will follow the up to down approach. Okay, and let's just say if you divide by r, you get some, not a, you get some p here, and your remainder is q. You again divide by r, you get some m here, and your remainder is n. You again divide by r, you get some k here, and your remainder is L, and you get to know that your k is less than r now. If your k is less than r, are you getting all these points? Because we have already studied. If k is less than r, then if you further divide, you will get k and l only. So what will be your number? Your number will be k, l, n, q dot alpha, beta, gamma. That's it. That would be your number. So on the top level I have given this thing so that you could revise it. Okay, so these are the summary only. And if I am going from 2 to any 2 to the power n, then I will club n bits all together, and I can write down my answer. Okay, n bits I will club, and then I will write down the, not decimal equivalent, their equivalent here. I write down the equivalent. I should not say decimal equivalent, because in hexadecimal, let's just say some number is 15. So in that, there I will not write 15, I will write f. So I cannot say I will write their decimal equivalent, I will just write their equivalent. Okay, and if I am going from 2 to the power 2, that means n bits clubbing together, and then I will write their equivalent here. Wait a second. Yeah. Or forget it, like, okay, I am going from any number to 2 to the power n to 2. So I will write their equivalent in n bits. I will write their equivalent. Each number will be denoted in n bits. 3 will be denoted in n bits. 1 will be denoted in n bits. 6 will be denoted in n bits. Here you can see this is 6. Here 5 will be denoted in n bits. Here I am denoting in 5 bits. Basically here everything I am denoting in 5 bits. This could be denoted in 5 bits. So this is actually, if this was 2 to the power 5, that means if this was 32. So from 32 to 2 I am coming. This is for the base 32. For base 32. This example is there for base 32, and here I am clubbing 3 bits, so this example would be there for base 8. Okay, so if I am clubbing 3, then what I will get? So this would be 1, 2, 4, 5, 5, 6.101, 5, 1,004, and 100 and 100 again, 100 again, that would be also 4. So that would be for base 8. So that is the example. So if you just read these 2 slides, then everything is clear. So only these 4 methods we have studied. Any number to decimal, any decimal to any number. With this effect you can change anything, and from 2 to from 2 to 2 to the power n, and from 2 to the power n to 2. Now you will be able to convert any number to any base. Let's solve some problems. So for a particular number system, 24 plus 17 is equals to 40. Find the base of the system. 24 plus 17, what is that? 24 plus 17. 24 plus 17 is 11, 41. But here they are saying that it is 40. That means something is different. Something is different. That means what they mean to say is that 24 in base r plus 17 in base r would be equals to 40 in some base r. We do not know these kind of calculation, but we know one thing, that we can do decimal addition. You know 3 plus 2 is 5. This much things you know. 23 plus 22 is 45. This I know. So what I will do, I will convert this number into decimal. How I can convert this number into decimal? What will be 24 in decimal? 4 into r to the power 0 plus 2 into r to the power 1. What will be 17 in decimal? 17 into r to, 7 into r to the power 0 plus 1 into r to the power 1. And what will be 40 in decimal? 14 into r to the power 0 into r to the power 0 plus 4 into r to the power 1. So this calculation I know now. 4 into r to the power 0 will be 4 plus 2 into r to the power 1 will be 2r plus this is 7 into r to the power 0 is 7 only. This will be r, this will be 0, this will be 4r. So I know this calculation now, because this is in decimal. Everything is decimal in now. Everything is in decimal. Our target is to find this r. So we can find this r. What that would be? From here I can get to know that my r is equals to 11. So here the base is 11. Okay, the base is 11. Root 41 is equals to 5. Find the base. So if I do that, 41 will be equals to 25. Step is wrong here. Why this step is wrong? You cannot do any calculation. Your first target would be always our first target would be convert into decimal. Convert into decimal, then perform the calculation. So first you will convert to decimal, then you perform the calculation. Okay, so first convert into decimal, then you perform the calculation. So root will be there as it is. Root is there as it is. How this will be converted? 1 into r to the power 0, that will be 1, plus 4 into r to the power 1, that would be r, 4r. 5 into r to the power 0. 5 into r to the power 0 will be 5 only. 5 into r to the power 0 is there. That would be 5 only. So 1 plus 4r. This is in decimal now. This is in decimal. Under root 5 into r to the power 0 is 5. This is also in decimal. Now all numbers are in decimal. Now you can take the root. So what we will get? 1 plus 4r is equals to 25. So r is equals to 24 by 4. That is 6. So the base was 6 here. So this number was actually 1 plus 24, and if you take the under root you will get the 5, and 5 is there. If you write it in decimal, if you write it in base 6 or you write it in base 10, it would be same only. And one more thing I need to take care, what is that? That all these numbers, all these digits 4, 1 and 5 all are less than 6. This also I need to take care. Why I need to take care? That 4, 1 and 5 all are less than 6, because in my, if my base is 6, then my number has to be lesser than 6. So 4, 1, 5 all are less than 6, then this answer is acceptable. Okay. Now some people will say that sir, here plus minus would come. Now someone say that if we take the under root here, so no plus minus would come. No one will say that. I am taking the square, not under root. So yeah, r would be 6 here. Only one answer is possible, that is 6. Let's see the next one. In a particular number system, the roots of the equation is this, you need to find the base. So root of the equation is this, roots are 3 and 6. So all these numbers are also written in some particular number system. Are you getting this point? This 11 is not 1110. Now this 11 is 11r. Okay, this 11 is 11r. 22 is 22r. So what they are saying? And we can do something. Let's change this question. 3 and alpha is 3 and alpha. Find the base. In a particular number system, one of the roots of this is 3. Find the base. This is the question now. Okay, only one root I have given. So now it would become more interesting. So what is the root I have? Root that I have is 3. But this root is 3 base r. That is some other number system. So what do I know? Multiplication of root. Multiplication of roots would be what? C by a. Do you know that? C by a, 22 by 1. Let's just say if there is an equation x square minus x square ax square plus bx plus c is equals to c. So what will be the roots, or what will be the addition of the roots? Minus b by a. And what will be the multiplication? That would be c by a. So I hope you remember this thing. Okay, in 10th class we have studied it, where alpha and beta are the roots. Alpha plus beta is minus b by a, and alpha into beta is c by a. So multiplication of roots will be c by a, that would be 22r. Okay, 22r, and addition of roots is minus c by a, minus b by a, minus b by a. So that would be 11r. Okay, 11r. Now one of the root is 3. Let the other root be alpha r. Other root is alpha. So what I can write? 3r into alpha r is equals to 22r. Say yes or no. I will not perform any calculation now. First my target will be to convert it into decimal. So 3r will be in decimal. What that would be? 3 into r to the power 0. That would be 3 only. Right? 3 into r to the power 0 it would be. So it would be 3. Into alpha r I don't know. What it would be? 2 into r to the power 0. 2 plus 2 into r to the power 1. 2r. So I am assuming alpha r as x. Okay. I am assuming alpha r as x. Alpha r is x. So here I am writing alpha r is some x value. So that it is easy for me to write. So alpha in base r is some x value. So 3x is equals to 2 plus 2r. This is one equation I am getting. What other equation I can get? Addition of roots. Addition of roots. So 3r plus alpha r would be equals to 11r. Again I will not perform any operation. First I will convert it to decimal. So what I will get? 3 plus x is equals to 1 into r to the power 0, 1 plus 1 into r to the power 1 r. So 2 equations I am getting. This was the first one, this is the second one. So what I can do? I do not need x, I can replace the value of x. I do not need x, so what will be the value of x? So here I can see x is equals to r minus 2. X is equals to r minus 2, right? This 3 goes here, x is equals to r minus 2. And from here if I see, x is equals to 2 plus 2r by 3. So 2 plus 2r by 3 is equals to r minus 2. So 2 plus 2r is equals to 3r minus 6. So r is equals to 8. R you are getting, that is 8. So answer is 8. So base is 8. Now if someone asks what was the other root? What was the other root? What was the other root? Other root. I am asking what was the other root? So here this is 3 plus this x I need to find. Sorry. Okay. 3 plus. Yeah, wait a second. Look, if I have converted this all these values, if I have converted 3 into base 10, this 3 into base 10, then certainly I have to convert this alpha into base 10 as well. Then only I can perform the operation. Let's just say there is base 10 and here there is base 8. Then how I can perform the operation? So alpha r is equals to x in base 10. Look, I have converted 3 into base 10. So I will, and 22 into base 10 as well. So I will convert all the numbers into base 10. 3 into alpha r would be x. So alpha r, if I am writing alpha r is equals to x, that means I am writing alpha r is x in base 10, right? So that is x in base 10. Eventually I don't need alpha, so that I will eradicate. So 3x is equals to 2 plus 2r, and here it is 3 plus x is equals to 1 plus r. So x value you are getting is r minus 2. X value you are getting is r minus 2 here, and then I put r minus 2 here, and I get 2 plus 2r by 3, so 3r minus 6, and from here I get r is equals to 8. So now I will put my r in this particular equation. 3 plus r is equals to 1 plus r. In this equation I am putting 3 plus x. 3 plus x is equals to 1 plus r. So 3 plus x would be equals to 1 plus r. R is 8. So x is equals to 6. 9 minus 3. So x is equals to 6. So this is the other root, and this root is in decimal. This root is in decimal. So other root is 6 in decimal. In decimal I am getting the other root, that is 6. In base 8 as well, this answer is in decimal. So in base 8, alpha r is equals to alpha base 8 is equals to 6 in base 10. So what that value will be in base 8? What do you think? You need to convert 6 from base 10 to base 8. My question is 6 from base 10 to base 8. So what you will do? 6 and divide by 8. So what will be the remainder? 6 only. Sorry, how it will be divided? 0 time. And what will be the remainder? 6. Basically 6 is less than 8. So it will be the same only, no? You can go upward. So 0, 6 only you will write. So 6, if this answer is in decimal, so that means this answer is 6 with base 10. So what will be the value of alpha? That would be 6. This answer is in base 8. So although luckily here our roots were here, luckily we got 6 value here. If we had got 11 here, let's just say my other root would have come out to be 11. Then what would be my answer? Will that be my answer? No, that would be wrong. Because 11 you are getting in base 10. Now your task would be to convert 11 into base 8. So 1 and 3. 1, 3. So answer would be 1, 3 in base 8. Are you getting this point? So the complexity start from here. that if you have converted everything into decimal, that means this x is also decimal. That means this alpha r has been converted into decimal. Okay, and if alpha r is converted into decimal, that means this is also decimal. So from here, if you are getting r is equals to 8, so if you put r equals to 8 here, that means x is equals to 6. So this answer you are getting in decimal. Now your task is to convert this decimal into base 8, because your given base is 8. So you need to check the option if the given options are there in base 8 or base 10. So the answer you are getting, that is there in base 10. So you need to convert it to base 8. Luckily we will get the same answer. So from here I am going here, from here I am going here. Okay, so that is the a lot of good points I have explained in this point, in this particular question. I hope you got it. Right, so these kind of questions you can expect in your examination. These are very good problems, and these kind of questions can come in your examination. Let's see the next one. 43x is equals to y38. You need to find all possible combination of x and y. So 3 plus 4x. Do you agree to this point? X 3 into x to the power 0. 3 into x to the power 0 plus 4 into x to the power 1 would be equals to 3 into 8 to the power 0 plus 8 into y to the power 1. So 3 plus 4x is equals to 3 plus 8y. So from here I am getting y is equals to x by 2. But if you have given that 43x is there, that means x has to be greater than or no sorry x has to be greater than 4. X has to be greater than 4, and x will be integer for sure. That means x can start from 5, 6, and in that manner it can go, right? What about y? y3 8. That means y has to be less than 8. Say yes or no? Y has to be less than 8, because this will be the bigger number. So y can go like, it will be less than 8, so it can have values 7, 6, 5 and so on till 0. Negative number cannot be there till 0. So 5, 7, 6, 0. Now if x is having, and all should be integers, that means all should be belonging to natural number. Now if x is 5, then y will be 5 by 2, not acceptable. If x is 6, not acceptable. So this is wrong. If x is 6, x can be 6, right? Then what will be y? Y will be 6 by 2, that is 3, acceptable. Y will be 6 by 2, that is 3. 7, 6, 5, 4, 3, 2, this is acceptable. If x is equals to 7, then what will be y? Y will be 7 by 2, not acceptable. If x is equals to, let's keep this question a bit downward. If x is equals to 8, then y will be equals to 4, acceptable. If x is equals to 9, then y will be 9 by 2, certainly not acceptable. If x equals to 10, then y will be 5, acceptable. If x equals to 11, then y will be 11 by 2, not acceptable. And if x equals to 12, so in that manner we will go. So you must have got the idea, right? That thing is, if x is 5, then it is not acceptable. So I am writing in xy order. So if x is 6, then y will be 3. X is 6, y will be 3. That is acceptable. If x is 8, y will be 4. If x is 10, y will be 5. And if x is 12, y will be 6. And if x is 14, y will be 7. Till that point only it will be acceptable. Because if x is 16, let me write it here. If x is 16 here, then what will be y? Y is 8. but y cannot have any value bigger than 7. So this will also not be acceptable. If x is 16, then y will be 8. So x can take, so we will start with x. Okay, we will start with x. So x can be 5. So y will be 5 by 2, not acceptable. X is 6, acceptable. 7 not acceptable. 8 acceptable. 9 not acceptable. 10 acceptable. 11 not acceptable. 12 acceptable. 13 not acceptable. 14 acceptable. After that, nothing will be acceptable because y will be greater than 7, which cannot be possible. So these are the expected values. So this is the answer. Okay. Now let's take this question here on, let's take this question here. Okay. Find the possible number of ones. क्या हो गया भाई इसको? इसको आना ही नहीं है यहाँ पे. Find the number of ones present in presentation of 3 into 512 into 7 plus 7 into 64 plus 3. What you will do? You need to find number of ones in binary presentation of. So what you will do? First you will convert it to decimal, because this all these are in decimal. So first you will convert it to decimal and then you convert it to binary. Is that the way you will be doing? No. So how you will be proceeding? So let me add a page. So what is the given number? The given number is 3 into 512 plus 7 into 64, 7 into 64 plus 3. One thing I can sense here is that this is 8 to the power 2, right? This is 8 to the power 2. This is 8 to the power 2. And this can be written as 8 to the power 0. So there has to be 0 into 8 to the power 1. That's why there is no term of 8 to the power 1. Plus this is 3 into 8 to the power 0. What if this is 3 into 8 to the power 3? Let's check if 512 is 8 to the power 3. So yes, 512 is 8 to the power 3. So here the first thing that I noticed was 64, and 64 is 8 to the power 2. So what I get to know here, that this number has this number has place value of 8 to the power 0, this has place value of 8 to the power 1, this has place value of 8 to the power 2, and this has place value of 8 to the power 3. That means this number is 3703 in base 8. So yes or no? If you need to go from here to here, you can go, right? 3 into 8 to the power 0 plus 0 into 8 to the power 1 plus 7 into 8 to the power 2 plus 3 into 8 to the power 3. Say yes or no? If I need to go from here to here, basically I will write 3 into 8 to the power 0 plus 0 into 8 to the power 1 plus 7 into 8 to the power 2 plus 3 into 8 to the power 3. This is how I will write it, right? Are you getting my point? Now I am going from here to base 2. That means this 8 is 2 to the power 3. So I need to denote all the number in 3 decimal. I need to denote all the number in 3 bits. So 3 can be denoted as 0, 1, 1. 7 can be denoted as 1, 1, 1. 0 can be denoted as 0, 0, 0. And this 3 can be denoted as 0, 1, 1. So how many ones are there? 1, 2, 3, 4, 5, 6, 7. So answer is 7 ones are there. 7 ones are there. So this is the answer. You can solve same kind of problems here. You need to denote this number in base 32. So what do you think? This I can sense that this is 32 to the power 2. What this could be? 32 to the power 3. Yes. So this is m into 32 to the power 3 plus j into 32 to the power 0. There has to be 0 into 32 to the power 1 plus 3 into 32 to the power 0. So this would be mj03 to the base 32. Right? Very easy problem. You can solve these kind of questions. Okay. 41 by 3 is equals to 13 in some number system. Find the base. You can do it on your own. In some number system, 41 by 3 is equals to 13. You need to find the base of the system. So I will not perform any calculation before converting into decimal. So this would be 4r plus 1. This would be the same, 3 into r to the power 0. This would be 3 plus r. So 4r plus 1 would be equals to 9 plus 3r. So r will be equals to 8. So this is the answer. So r is 8. So you can perform the calculation. If r is 8, 41, 8. So that would be 8 into 4, 32. That would be 33. 1 into 8 to the power 0 will be 1. 8 into 4, 32. 33 divided by 3. What you will get? 11. But you are getting it in decimal. 11. This performance you are getting it in decimal. But what answer they are giving? 13. So 13 in base 8. That means 3 plus 8. So 11 only you are getting. So the answer is same. So you can cross verify as well. Okay. Cross verify just putting 8 here. So if I put 8 here, I will get the same answer. 55 by 5 is equals to 11. What is the possible base? So 55 by 5, that is 11. In our normal calculation, the answer is 11. That means this is the answer. No, it could be other cases as well. Here it cannot be 3. It cannot be 5. Why? Because if I am saying that some number is there in number is 55, 5. This number is 5 in base r, and this number is 5 in base r. And so r has to be greater than 5. R has to be greater than 5, right? R has to be greater than 5. So what I will write here? 5r plus 5 divided by 5 is equals to 11. What that would be? R plus 1. 1 into r to the power 1 plus 1. So 5r plus 5 is equals to 5r plus 5. So always true. Always true. Always true. So for any base r greater than 5, for any base r greater than 5, 55 by 5 will be 11. So this answer is also correct. So if there were option, let's just say if there were option E, that was 7, then this will also be have been correct. If there was option B, that is 298. If the base is 298, then also it would be correct. Okay, any base could be there. For any base greater than 5, that would be the correct. Okay, so that's it. This is the end of our first lecture. There we studied about number system. So I hope till the end you are finding it interesting. A lot of good amount of problems we have solved, and a lot of good problems also we have solved. So nothing apart from this can be asked from this particular topic. Okay, and the number system is a important topic. There is very high chance that they will ask questions from this particular topic. So you cannot skip it. And I hope in this 1.5 hours you must have understood a lot of concept. So before moving on to the next lecture, I strictly advise you to revise it once. Just revise it, whatever that we have studied here. Just revise everything. You can revise it. Okay, then you can move to the next chapter. Right? So let's move to the next chapter. Not next chapter, sorry. In the next lecture, we will study about binary operations. Not only binary operation, we will study about all the operation, octal operation, hexadecimal operations, even the decimal operation, simple addition, subtraction we will study. So now we are going to study subtraction and addition. So in the next lecture, we will see that. Okay then, thank you very much. Hi everyone. So in this video, we are going to study about arithmetic operations. So we will see all kind of arithmetic operation in all kind of number system. So decimal, binary, hexadecimal, octal. But like I will tell you an easier method as well, how you can solve it, and the conventional method as well. Now the question will be coming, sir, we are studying it, but where we will be using it? So we will be using it in combinational circuits. So by using these calculation we will design some circuits when we study combination circuits. So using these calculation we will design the circuits, so there these calculation will be used. That's why we are studying it here. So now simple decimal addition. You know what is decimal addition? Simple addition and subtraction. You need to add 23 to 72. Can you add it? 3 plus 2 is 5. 7 plus 2 is 9. There was no carrying, nothing like that. There was no carrying, nothing. Simple addition. 3 plus 2, 2 plus 7. Let's solve this problem. 8 plus 4 is 12. 4 plus 8 is 12. Now will you write 12 here? No. What do you write? You write 2. Why do you write 2? Because you know I cannot write 12 because I have the number from 1 to 9 only. So I have to write one of the numbers. Now what is your base? Base is 10. So you subtract 10 from here, you get 2. So that 2 you have written. Since you subtracted 10, that's why there is 1 carry. Right? 8 plus 4 is 12. You cannot write 12, that means you have to subtract 10. If you have subtracted 10, that means 1 carry would be there. Right? 1 carry is there. Now what is 7 plus 8? What is 7 plus 8? 15 plus 1, 16. So your answer is 16. Will you write 16 there? No. You will subtract 10 from here. What you will get? 6. 6 you will write. Because you cannot write 16. Then there is 1 carry. There is 1 carry. So 1 plus 0, there is nothing. You will write 1. So that's how you did this calculation. Can you remember this? If the number we cannot write, we will subtract the base from there. So 2 I wrote. Then 1 went here. Then I wrote 16 I was getting, but I cannot write it. So minus 10 I had to do 6 and then 1. So this is how I solved my particular problem. Right? Now do the subtraction. 2 minus 1 is 1. 5 minus 2 is 3. Simple, very simple. In this one, 4 minus 6 I cannot do. So what I will do? I will borrow. How much I will borrow? I will borrow 10. Right? 4 was there. I cannot subtract 4 from 6. So what did I do? I borrowed 10. 10 plus 4, that is equals to 14. So I will subtract 14 minus 6, that is 8. 14 minus 6, that is 8. So I borrowed 10, which is equals to the base. Although also I should not have I should have written it 4 plus 8 is equals to 12. 12 minus 10 is equals to 2. And here 1 plus just a second, 1 plus 7 plus 8 is equals to 16. So 16 minus 10 is equals to 6. This I should have written here. Yeah. So base was 10, that I borrowed. If I am borrowing something, I am borrowing the base. So that I added, it would become 14. 14 minus 6 is 8. Now this is, if I borrow something, that means it will be 1 less, right? So this would become 6. 6 minus 3 will be 3. So that would be my answer. This is how I solve. If I borrow something, I borrowed 10. Okay, can you remember it? Now we need to perform the arithmetic calculation in other number system, like in decimal, binary. So there will be a standard calculation. You can solve it with standard calculations. Or what you can do, you first convert it to decimal, then you do the calculation. In decimal, we can easily do the calculation and then you revert back. Revert back means you again convert that number in that particular number system. Let's see what I mean to say. And there is one important point, that standard calculation in binary number system is important. So we will study that, and for other base we can do the calculation by converting it to decimal. That means I need to add 227 to 562, but in base 8. Do I know the calculation in base 8? I don't know. So what I can do, I can convert this into decimal. So 227 in base 8, I need to convert it to decimal. So 7 plus 2 into 8 plus 2 into 8 square, that would be 64. So 64 into 2 will be 128 plus 16 plus 7. 128 plus 16 plus 7. So that is 151. Okay, I did the calculation right. Yeah, 151. And what I would do with 562? So 2 plus 6 into 8 plus 5 into 64. 5 into 64. 370. Then I will add that. If I add that, what I will get? Basically, I am doing 227 in 8. That would be converted to 151 in base 10. This is 370 in base 10. Now I am adding it. So what I will get? I will get my answer in base 10 only. So 1, this would be 2. So 521 in base 10. Now what that would be in base 8? 1. What that would be in base 8? So I need to convert it to base 8. So 521 base 8. 65. 1. 8 8 ja 64. 1. 810. So what is the answer you are getting? 1011 in base 8. That is the answer. So how did we do? First we converted it to decimal. This also we converted it to decimal, and then we solved. We got the answer in decimal, and then I converted back. That's it. Now if I had to do the direct calculation, I could have saved the time in the examination if I am intelligent. How I would solve? How I would save the time? 227 plus 562 plus 562. Let's add it up. 7 plus 2 is 9. In base 8 I cannot write 9, so I have to subtract 8. What I will get? 1. I will write 1 here. If I am subtracting 8, that means 1 carry is there. Look, carry will not depend what you are getting here. Carry does not depend here. Carry will be, if you are subtracting 8, if you have subtracted 8, that means 1 carry is there, that's for sure. Now 6 plus 2 plus 1, 6 plus 2 plus 1, that is 9. 9 and I cannot write, so 9 minus 8 I will do. What I will get? 1. So this 1 I will write here, and 1 will be carried. The same kind of calculation we are doing that we did in our decimal number system. Now 1 plus 2 plus 5, what that would be? 8. Again I cannot write 8. I have to write something lesser than 8. So again 8 I will subtract. What I am getting? 0. So 0 I will write here, and 1 carry I will put, and 1 carry that will be copied. That's it. This is the answer. Did you understand this? So in that manner I could have solved it. Okay, let's see this problem. You need to add them, and then you need to write your final answer in base 2. So what you can do? First you convert it to 10. That would be 1.2. You need to convert it to decimal. So 1 plus, this has 4 to the power 0, and this has 4 to the power minus 1. So 1 plus 2 into 4 to the power minus 1. So 1 plus 1 by 2, that would be 1.5. And what about this? 2.34. So 2 into 4 to the power 0 plus 3 into 4 to the power 1. So that would be 2.75. So what you will get by adding up? 4.25. Now I need to convert it to our base 2. So 4. So I will go upward. Very easy method, right? We have already studied it. So from here I am getting 100. What about 0.25? So 0.25 into 2, that is 0.50. 0.50 into 2, that would be 1.00. 0.00 into 2 would be 0.00 only, and you will go from up to down. So 0 and 1. So 100.01. You only need to focus on integer part. So this is the answer. This is the correct answer. But this is from method 1 only, right? Method 1. Let's remove it off. What would be method 2? Direct calculation. Direct calculation. So 1.2 plus 2.3. 2.3. 2 plus 3. First I will do 2 plus 3. What that would be? 5. I cannot write it because base is 4. So 5 minus 4, that would be 1. So 1 I am writing here. If I have subtracted something, that means if I have subtracted 4, that means 1 will be carried. So 2 plus 1 plus 1, what that would be? 4. Again I cannot write 4, so I have to subtract. That would be 0. So this would be 0 and 1 is carried. So again 1. So 10.1. That is my answer in base 4. So my answer is 10.1 in base 4. That I need to convert it to base 2. So base 4 can be written as 2 to the power 2. So each digit will be expressed in 2 bits. So 1 is expressed in 2 bits, that is 0 1, and 0 is expressed in 2 bits, that is 0 0. 1 is expressed in 2 bits, that would be 1 is expressed in 2 bits, that would be 0 1, not 1 0. Take care of that. 1 is expressed in 2 bits, so that would be 0 1. If I write 1 0, that would be 2, it would become 2. I need to write 0 1. So this is our answer, or you can write 100.01. So I guess you will be able to solve it quicker in the examination if you have the basics clear. Let's study about binary addition, because that is more important part, but we will study about all the addition and subtraction. Okay, all kind of addition and subtraction here. We will deal some examples. With the examples it will be more clear, and I hope with these examples it is clear. But binary addition at least you need to study, because that is very important part. Binary addition and subtraction, these two are very important, that you need to study, otherwise your digital electronics will not work. So the same kind of thing we will do that we have already done. So add them up. 1 plus 0, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1. That's it. This is the answer. No carrying, nothing like that. No carry, no other calculation involved. Now let's solve this one. 1 plus 0, 1, 1 plus 0, 1, 0 plus 0, 0. 1 plus 1, 1 plus 1. That would be 2. 2 I cannot write. So 2 minus 2. What is the base? Base is 2. So 0. I will write 0. If I have subtracted something, then I will put the carry. 1 plus 1 plus 1. What that would be? 1 plus 1 plus 1. What that would be? 3. Right? So I have to subtract. 3 minus 2. What I will get? 1. What I will get? 1. What is carry? 1. 1 plus 1 plus 1. Again I will get 3. Again I have to subtract. What I will get? 1. 1 again is carried. Wait a second. Yeah, okay. 1 again is carried. So this 1 plus 0, that would be 1 only. So that's it. This is the answer. 1 1 1 0 0 1 1. 1 1 1 1 0 0 1. That would be 1. Then 1 plus 1 plus 1 is 3. 3 minus 2 1. You will be habitual of it. Okay. A lot of other examples are also there. Here you see 1 plus 1 will be 2. 1 plus, you can remember this thing. Okay. Very simple thing you can remember. 1 plus 1 will be 0 1. Sorry, 1 0. Because 1 plus 1 will be 2. 1 plus 1 will be 2. And 2 can be expressed as 1 0. So 1 plus 1 I will write 0 here, and then will give 1 here. 1 plus 1 I will write 0 here, and will give 1 here. 1 plus 1 I will write 0 here, and will give 1 here. So 1 plus 0 0 0, that would be 1 0 0. Again let's see. 1 1 plus 1 is 1 0. 1 plus 1 is 1 0. So 1 plus 1 is 1 0. So 0 I will write here, 1 carry. 1 plus 1 0, 1 carry. 1 plus 1 0, 1 carry. 1 carry. So 1 plus 0 plus 0, 1 0 0. That's it. Let's solve this problem. This will be very interesting. 1 plus 1 is 0 1. 1 plus 1 plus 1 is, what is that? 3. 1 plus 1 plus 1 is 3. So 3 minus 2, you will get 1, and 1 is carry. 1 plus 1 plus 1, what is that? 1 only. 1 plus 1 plus 1 is 3, and 3 can be written as basically 1 plus 1 plus, there is other way as well. 1 plus 1 plus 1 is what? 3, and 3 can be written as 1 1. Say yes or no? 3 can be written as 1 1. So 1 you write, and this 1 will be carried. Now 1 plus 1 plus 1, that is 3. So 3 can be written as 1 1. So this is the other method by which you can go. Only if you remember these things, then this would be the other method, or you can get the method that 1 plus 1 is 0, 1 plus 1 is 3, 3 minus 2 is 1, 1 carry. 1 plus 1 plus 1, that is 3, 3 minus 2 is 1, 1 carry. 1 plus 1 plus 1, that is 3. 3 minus 2, 1, and 1 is carried. So that one is coming here. So by that method also you can go, or this also you should remember, because there will be a lot of complex calculation which will be solving very easily by this method. So that we will use only in binary, not in other functions, only in binary we will be using that. Let's see it now. Subtraction is there. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. That's it. This is the answer. Okay. Let's do this. 0 minus 0 is 0. 1 minus 1 is 0. What you will do? 0 minus 1 you cannot do. So you will borrow from here. And how much you will borrow? In decimal we were borrowing plus 10. So how much you will borrow here? Plus 2. 2 minus 1 will be 1. And if you have borrowed, then this would become 0. 0 minus 0 will be 0. And 1 minus 1 will be 0. That's it. Did you understand this? 1 I borrowed. If I am borrowing here, I am borrowing plus 2. So 2 minus 1 is 1. So this would become 1 less. This would become 0. 0 minus 0 is 0. 1 minus 1 is 0. Let's solve this. 0 minus 0 is 1. 1 minus 0 is 0. 0 minus 0 is 1. 1 minus 0 is 0. You will carry 1 from here. Carry will be plus 2 basically. 2 minus 1 will be 1. This is 0. This is again 0. Now 0 minus 1 cannot be possible. Then again you will carry. 2 minus 1 will be 1. And this would become 0. 0 minus 0 will be 0. Negative number calculation we are not doing. Let's just say you can ask, sir, what will happen if 23 is subtracted from 52? So what will be the answer? That we will see. That we will see, but later on. Have the patience, right? So are you getting this point? 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. Get carry I am getting from, sorry, borrow I am getting from here. So plus 2 I will get. Plus 2 minus 1 would be 1. This would become 0. Then again borrow I will take, because 0 minus 1 is not possible. Again borrow I am taking. This would become 2. 2 minus 1 is 1. This would become 0. 0 minus 0 is 0. That's the correct answer. Okay. So that's how we will do the subtraction. Let's do the multiplication. So multiplication is simple, like first 1 will be multiplied to all the bits. So 0, 1, 0, 1. Then 0 will be multiplied to all the bits. 0, 0, 0, 0. Then again 1 will be multiplied to all the bits. 0, 1, 0, 1. Now you need to add them up. Basically cross you can put here. So 0, 1, 0 plus 0 plus 0 will be 1. 1 plus 1 will be 1 plus 1 will be 2, and 2 can be written as 0, 1. 1 plus 0 plus 1 will be 1 plus 0 plus 0 will be 1 only, and 1 you write here. Okay. Now let's solve this one. This is very interesting. So a very good point I will teach you here. So you need to take care of that. 1 into 1 in 1 1 1 1 into 1. So what you will get? 1 1 1 1. Here what you will get? 1 1 1 1. Next what you will get? 1 1 1 1. And next what you will get? 1 1 1 1. Now you need to add them up. Now that is the task. So first 1 plus 0, nothing will come. Now 1 plus 1 is what? 1 plus 1 is 2. 2. 2 is 1 0. So 0 I will write here, and carry is 1. Now 1 plus 1 plus 1 plus 1. 1 plus 1 plus 1 plus 1. What I am getting? 4. Right? Now if I subtract 2, then again I get 2. Then again I will have to subtract. So let's ignore this method. We will not go with this method. What we will do? 4, how it can be denoted? 4 can be denoted as 1 0 0. Say yes or no? So only one bit I will write, no? 0 only I will write here. What will be the carry? 1 0. And what is 1 0? The carry is only 1 0, not 1 0 0. So this will be as LSB, this will be MSB. So basically this will have the place value of 1, this will have place value of 2. That means this will have the place value of 2 to the power 0, this will have the place value of 2 to the power 1. Are you getting this point? This is very important point, very important point. What I got, here I am getting 4. 4 means 1 0 0. So I will write 0 here, and my carry will be 1 0. Carry will be 1 0. And what do you mean by 1 0? What is 1 0? This is my carry. This is my carry. Carry is 1 0. And what is 1 0? 1 0 is 2. So this number is written as 2. This number is 2. So 2 plus 3 plus 4 plus 5 plus 6. So 2 plus 1 plus 1 plus 1 plus 1. So you are getting 6. And 6 can be written as 1 1 0. Say yes or no? So only 0 I will write here. And my carry will be 1 1. And what do you mean by 1 1? This is my carry. What do you mean by 1 1? 1 1 is 3. 1 1 is 3. So 3 plus 4 plus 5 plus 6. Again you are getting 6. Again you are getting 6. That means you will write 0 here. What will be carry? 1 1. Carry will again be 1 1. Right? 0 you are writing here. Carry will again be 1 1. And what is 1 1? 1 1 is 3 only. So 3 plus 1 plus 1. What that would be? 3 plus 1 plus 1. That would be 5. And 5 can be written as 1 0 1. 5 can be written as 1 0 1. So 1 you have written. What will be carry? Carry will be 1 0. And what do you mean by 1 0? 1 0 means 2. 1 0 means 2. Now 2 plus 1 is 3. 2 plus 1 is 3. And how you can write 3? 3 is 1 1. There you go. This is the answer. Okay, so if there are more than 2 steps involved, like if this was the calculation, we could have solved it. If this was the calculation, 1 1 1 1 plus 1 1 1 1, you could have easily solved it. 1 1. 1 plus 1 is 0. 1 plus 1 is actually 2. So 1 will go as carry. So 1 plus 1 plus 1. 1 here, 1 will go as carry. 1 plus 1 plus 1. 1 here, 1 will go as carry. 1 plus 1, 0, 1. Then you could have added it. Then what you could have done? Then you could add 1 1 1 1. In this you need to add 1 1 1 1. So 0 1 1 1 is 0. 1 carry would be there. 1 1 1 will be 1. Another carry. 1 plus 1 will be 0. And that this would be 1 1 1 1. Now what you could have done? 1 1 0 1 0 0 0. In that you need to add 1 1 1 1. Okay. So 0 0 0. 1 plus 1 is 0. 1 plus 1 is 0. 1 1. And then this would be 1 1. There is some issue now. क्या गड़बड़ कर दिया? अच्छा यहाँ पे 1 ही था. Here only you had 1 only. So this would be 1. So this would become 1. So yeah, this is how you could have solved it in each step. But if you are solving all together, then this is the way that I have written here. That do the calculation that you know, and then just write down the words. That I know it would be 5. 5 is 1 0 1. So 1 I can write. This is the carry. This is the carry. So in that manner you can proceed. So this calculation you should be comfortable with, this kind of calculation in 2 steps, where there is only 2 steps, A plus B. This calculation you should be comfortable with. And this kind of calculation you might use, very rare chance, but you might use it. Okay, so I hope you are understanding what is more important. Now this is not important at all. Okay, this is not that important. I should not say not important at all, but not that important. Okay. So how do we generally solve a division? So 6 is not divisible by 4. That means I need to take 48. So 6 8 ja 48. 0 you got. Now next number you will put, that is 2. Next number will come here, that is 2. 2 is not divisible by 6, so I have to put a 0. Then 24 will come. So 6 4 ja 24. That's it. This is the answer, right? Same goes here. 1 1 0 1 1. Right? I will do this thing. So 1 is not divisible by 1 1. It is not 11. It is 1 1. This is binary. It is not 11. Okay. This is 1 1. Surprisingly, even if it is 11, it will give the same answer. But let's forget it. This is 1 1. So 1 1 is not divisible by 1 1. So you need to take both of the digits, right? So I will take both of them together. Okay. So this will be 0 0. Now this 0 will come. This 0 is coming here. So basically 11 1 1 into 1 is 1 1. Okay. Again let me solve it. So 1 directly you cannot take. So you have to take these 2 numbers. So how will you get 1 1 from 1 1 into 1? 0 0 you will get. Now this 0 will be coming here. Now next number, if this 0 is coming here, you cannot do anything about it. If this 0 cannot be divisible by 1 1, right? So another number you have to pick. If you are picking another number, that means you need to put 1 0 from your side. 0 1 is not divisible by 1 1. So again you have to pick another number, that would be 1 1. So again 0 you have to pick, right? Now 1 1 is divisible by 1 1 by 1. So that's it. This is the answer. So remainder is 0 0 0 0. Are you getting this point? I hope you are understanding how we are doing the division. So 11 1 1 0 1. So 1 1 is not divisible by 1, then we need to take 2. So 1 1 I put, 0 0 I got. Then again 0, this 0 will be coming all together, it will be coming on its own. But 0 is not divisible by 1 1, so I have to put another number, that would be 1. So for that I will put a 0, because if I need another number I will put a 0 here. Even that is not divisible, then I need another number. So for that as well I need to put another 0. So this number is coming, and in that way we need to solve. Not that important, okay, not that important. Whatever the important part is there, that we have already covered. Let's see some problems. So what you will do, you will solve those problems by converting into decimal and on your own. Convert decimal and revert back. Convert decimal and revert back on your own, okay, on your own. अरे यार ये तो छोटा छोटा, on your own, sorry on your own. On your own means you need to do it on your own. खुद करना है इसका मतलब. Now 723 minus 564. Now I will do the subtraction in base 8. 3 is not divisible by 4. So what I will do? I will take plus 8 from here. 8 plus 3 is 11. 11 minus 4 is 7. If I have taken plus 8, that means this would have become 1. This is becoming 1. Now 1 cannot be subtracted from 6. So I will take plus 8 from here. So plus 8 plus 1, that would be 9. 9 minus 6 is 3. This would become 6. 6 minus 5 is 1. 137. That's it. Did you understand? In the examination, it would take a lot of time. You will convert it to 10, you will convert it to 10, then you will get the answer in 10, and then you will convert it to 8. But simple thing is there, no? Only just a small amount of notice is required. 8 we will take. 8 plus 3, 11. 11 minus 4 is 7. It would be 1. Again 8 we will take. 9 minus 6 is 3. 6 minus 5 is 1. That's it. Now ADD, add plus dad, or ADD plus DAD. This addition we need to do. So what is D? D is 13 and A is, okay, let's write everything. E is 14 and F is 15. So this is 13 plus 13. 13 plus 13 is 26. 13 plus 13, 26. You cannot write 26. So what you will do? You will subtract 16. So what you will get? 10. 10 you can write. 10 is A. And since you have subtracted 1, that means 1 will be carried. So D plus A plus 1. D plus A plus 1. That will be 24. 13 plus 10 plus 1. That will be 24. Again it cannot be written. Subtract 6. What you get? 8. Since you have subtracted 16, 1 carry will be added. D plus A plus 1. D plus A plus 1. Again it would be 24. Cannot write 24 minus 16. What you will get? 8. So write 8. 1 will be carried. So 1 carry will be here. That's it. This is the answer. These kind of questions may come up in your examination. Okay, they can ask this in binary as well. They can ask this in binary, like they can ask this question as well. What that would be in binary. So you can directly convert it to binary, right? 0 0 0 1. Each number will be denoted in 4 bits. What about 8? 1 0 0 0, 1 0 0 0. And what about 10? 1 1 0 0. So the question, sorry, 1010, sorry, 1010, 1010. So the question that may come is that after performing this addition and converting it to binary, how many number of ones you get? How many numbers of ones you get? So 1, 2, 3, 4, 5. So these kind of questions can be coming, and it would take a lot of time if you convert it to decimal and then you again convert it to binary. So these kind of things may take some time. So we can avoid these kind of things and solve it if we are comfortable with this kind of calculation. And I hope you will be comfortable. Like I am writing each step so that you get the confidence. So let's see this. 974B 587C. Try it on your own. If you are not able to solve, then also it is fine, but try doing it on your own. What is B? B is 11. What is C? 12. Cannot happen. It has to take. So how much it will take? Plus 16. So 11 plus 16, what that would be? 27. And 27 minus 12 will be 15. So what we will get here? 15 is equals to E. Sorry, F. Sorry. This is very big blunder. Like everyone knows 15 is F, because in memory, when we study about all kind of things, this will be highly used. F will be highly used. So this will become 3. Now this will become 3. 3 cannot be subtracted from 7. So again it will take carry. That is 16. So 16 plus 4, 16 plus 3, because 4 has become 4 minus 1 now. So it would be 16 plus 3. 16 plus 3, that would be 16 plus 3 will be 19. This is 3. 19 minus 7. 19 minus 7 is 12. And what is 12? 12 is C. Again I am telling, this has become 3. 3 plus 16, that is 19. 19 minus 7, that is 12. 12 is C. This has become 6 now. 6 cannot be subtracted from 8. So again 6 will take plus 16. So 6 plus 16, what that would be? 6 plus 16, that would be 22. 22 minus 8. Yeah. So that would be 14. So what is 14? 14 is E. This would be E. And this has become 8 now. So 8 minus 5 is 3. Let's check back again. Okay. Not that tough. If you solve it by going like in decimal, it would take a lot of time. Right? But B minus C cannot happen. Take carry 16. So 16 plus 11. B is 11. So that is 27 minus 12, which is C, 15, F. 3 minus 7, 3 you cannot do. 19 minus 7, that would be 12. And 12 will be C. 6 minus 8, that cannot happen. So take 16, that would be 22. 22 minus 8. 22 minus 8, that would be 14. Right? 22 minus 8 will be 14 only. So 14, and that is equals to E, and 8 minus 5 is 3. Okay. So this is how we solve the problem. Now you need to find the value of W, Y and Z. In the examination hall, if this question is coming, you will say that sir, here base is 2, here it is 10, and then here it is 2. So better we should convert all in 10 and then we can solve it. Yeah, you can do it. Try doing it. It will be possible, but it will take a lot of time. So let's solve it and let's see how much time it takes. So this is Z, okay? This is Z. So Z plus this number will be 2. Basically 1, 2, 4, 8, 16. 1 plus 2 plus 4W plus 16 into 15. That would be equals to what? 1, 2, 4, 8, 16, 32, 64, 128 and 256. So 256y plus 64 plus 16 plus 8 plus 1. Okay. So let's solve it. 256y प्लस, इसको कैलकुलेटर से करूँगा, 25, 25 प्लस 64, that would be 89. And what about this? 15z, 15z, 18 into 15, 18 into 15, 18 into 15, 270 plus 60 w. Okay, so now you need to go hit and trial. There is this equation, it has 3 variables, only one equation is there. So what we need to go, hit and trial. One thing, what do I know, that w, z and y, w, z and y will certainly be less than 2. Say yes or no. This thing I know, because all are there in base 2. So it could be 0 or 1. W could be 0 or 1. Z could be 0 or 1. And y could be 0 or 1. So it is very easy to guess the values, because you can see if you put all equals to 1, then only you will get the answer. So w equals to y equals to z equals to 1. If you get all equals to 1, then you will get the answer. So that is the answer. By hit and trial you can solve it. Or in the examination, how I would have preferred, because this number is in binary, this number is also in binary. So why should not I convert this into binary and then I perform the multiplication? That also I can do, because but that will also take some time. So let's solve it. Is there any problem after that? No. So after that we will start our next lecture. So first let's solve it. So 10w1z, 10w1z into 15, that is 1 1 1 1, right? This is 15, this is 15, this is 15, that we have done. So now basically 10w1z, z1w01, this one I should write properly, z1w01, z1w01. Now here what will come? Z. But I know the answer already. That is y0 10 1101, y0 10 1101, y0 10 yeah. So I already know the answer, that this is my z, and from here what I can relate, here I can see directly that my z is equals to 1. So this number is 1 now. I got to know that this number is 1. So I can replace everywhere, this would be 1, or I should not do it. But it would be tougher to explain. So let's write down here 10w11, this is 1, this is also 1 now, w01, 1 1 w01, 1 1 w01, this is 1. Now 1 plus 1 will be 0, and here I will get 1. Now what is the scene? 1 plus w plus 1 plus 1. Now on the third digit I am getting 0. On the third one I am getting 0. 1 1 0, 1 plus 1 plus 1. If w is 0, yeah, if w is 0, if w is 0, then what this number would be? 3, and 3 is 1 1. 3 is 1 1. So I will have to write 1 here. Are you getting this calculation? 1 plus w plus 1 plus 1, that would be, this would be the answer here. And if w is 0, if w is 0, that means 1 plus 1 plus 1, that would be 3, and 3 will be 1 1. So I will have to write 1 here. but which is not in the case here, that is 0. That means if W is 1, so that would be 4, and 4 will be 1 0 0. So this would be 1 0 0, and carry will be 1 0. Carry will be 1 0. And what is 1 0? Carry will be 2. So 2 plus 3 plus 4 plus 5. 5 is 1 0 1. So 1 here, and carry will be 1 0. That is 1 2. 2 will be carried. So 2 plus 3 plus 4 plus 5. Again 1, 2 will be carried. 2 plus 3 plus 4. 4 means 0, and 1 0, that is also 2 will be carried. 2 plus 1 is 3. That means 1 will be carried, and 1 plus 1 is 2. That means 0 1. So 1 0 1 0 1 1 0 0 1. So y is equals to 1, z equals to 1 I got from here, w equals to 1 I got from here, and y is equals to 1 I am getting from here. Although this is also taking me more time only, but there is no hit and trial here. Here this is a complete method, right? All these are carries, so I should mark them here. So here I used a complete method, but in the last one I had to go with hit and trial. So that's the thing, like just wanted to tell everything. You revise this lecture again, okay? The thing with this particular chapter is, with number system, that you need to revise everything that you study. Just if you have watched one lecture, then again revise it. Watch one lecture, again revise it. But because there are a lot of things that carry 16, so there are a lot of things like that. So you just need to revise it and study that. Where it will be used, that will come. So no need to worry about that. In combination circuits, we will design these kind of circuits where it will be used. So that will come, and that is very, very important for your examination. Okay then. So yeah, let's meet you in the next video. Now we will be studying about codes. So our first part is completed, that is number system. So number system we have completed, and the operations also we have seen. Now we will study about the codes. So what is code? That is very simple thing. So that we will study about. Okay then. Yeah. Thank you very much. Hi everyone. So in this video we are going to study about codes. Okay. So what do you mean by code? So let's just say you must have used the words like code word, code language. So there will be a group of symbols which will be used to represent a particular number, letter or words. Let's just say there is a word fish. So F will be represented by hash, I is represented by star, S is represented by dot, and H is represented by alpha, and gate, GATE, G is represented by 2. So any particular word is represented by some other group of symbol. But this is just a general example. In digital design, we are going to study about binary, non-binary, and alphanumeric codes. And in our gate syllabus or for placements as well, this is the important part only, binary codes. So we are going to study about only binary codes. So in binary code as well, there are a lot of types. So first we are going to study about BCD code. So what do you mean by BCD? BCD means binary coded decimal. Binary coded decimal codes. Now you don't need to mug up this classification, you will generally understand it. Once we study one by one, you will understand it. Now BCD codes could be of two types, weighted and non-weighted. What do you mean by weighted? Weighted means each bit has certain place value. Let's just say I am writing 1101. So this has a fixed place value of 1. This has a place value of 2. This has a place value of 4. This has a place value of 8. So each bit has a certain place value, specific positional weight of each bit. So each bit has a specific positional weight. So that code we know as weighted code. So these codes are weighted code, and other one is non-weighted code. So there is no fixed value. Okay. Now weighted code could be of two types. Positively weighted, that means positively weighted could be written as 8421. What do you mean by 8421? That LSB would have the place value of 1 and MSB would have the place value of 8. And negatively weighted could be written as 84 minus 2 minus 1. That means MSB will have weight of 8 and LSB will have a weight of minus 1. Okay. Now if nothing is mentioned, if only this is written that this particular code is a BCD code, then you will understand that it is positively weighted BCD. If only BCD is written, that means this will be taken by default, 8421 code. If only BCD is written, so by default you will take 8421. For XS3 they will write the name XS3. We will understand one by one. What do you mean by XS3? What do you mean by 8421? We will understand it one by one. So let's see what do you mean by BCD code. So in BCD code, each decimal digit, so you need to take care of this line, each decimal digit is represented by 4 binary code. So each decimal digit will be represented by 4 binary codes, and in direct, if direct BCD is written, you have to consider it 8421 code. Okay, so this is the point, that if only BCD code is written, then you have to consider 8421 code. Now you need to write 7 in BCD code. So each digit will be, each decimal digit will be represented by 4 bits. So 7 in 4 bits, how will you write 7 in 4 bits? 7 in 3 bits will be 111, but you have to write it in 4 bits, so this will be the answer. That's it. Okay, so this is how you will represent it in BCD. Now 15, will you represent in this manner? Well, this is wrong. Why this is wrong? Because this is binary. This is binary, but we need to represent in BCD. BCD and binary are two different things. So what did I tell you? In BCD code, each decimal digit is represented by 4-bit binary code. Each decimal digit. That means 1 will be represented by 4 binary codes. 0, 0, 0, 1. Then 5 will be represented by 4 binary codes. So how 5 will be written? 0, 1, 0, 1. So this will be the correct BCD code. This is the correct BCD code. 5 is represented in 4 bits. Okay, and although here I should have written 8421 code, basically we are writing 8421. So place value of 84 and 21, 8421. So place value of 5, total 5 you need. That means this should be 1 and this should be 1. So 0, 1, 0, 1. Total 1 you need. That means all should be 0, this should be 1. Here total 7 you need. That means 0, 1, 1. Total 7 you will get. What about 319? How will you write it? So first you will denote 3. For 3 what you will write? 0, 0, 1, 1. Because if direct BCD is written, that means we will consider 8421. How will you write 1? 1 you will write as 0, 0, 0, 1. How will you write 9? 9 you will write as 1, 0, 0, 1. So that would be the BCD code. So binary and BCD are two different things. Okay, binary is not equals to BCD, that we will see later on as well. Now let's study about XS3 code. So XS3, it's a 4-bit code which can be derived from BCD code by adding 3 to each number. You need to add 3 to each number. So if I need to write XS3 code of 0, so what I will do? I will add 3 to 0. So what I will get? 3. Now I will write the BCD code of 3. So what that would be? BCD code of 3. Sorry. 1, 2, 4, 8. BCD code of 3 will be 0, 0, 1, 1. So that would be the XS3 code. You write it XS3 as well. Okay. Now, what will be the XS3 code of this? What is written? Which can be derived from by adding 3 to each coded number. 3 to each coded number. So, right, add 3 to each number. That means this will be 8. It's not that I will do 532 plus 3. No. Each number will be added by 3. So this will be 6 and this will be 5. So 865. So 8 can be represented as 1, 0, 0, 0. 6 can be represented as 0, 1, 1, 0. And 5 can be represented as 0, 1, 0, 1. That is XS3. Okay. How will you write 27? So 2 plus 3 will be 5 and 7 plus 3 will be 10. So 5, how will you write 5? 0, 1, 0, 1. And how will you write 10? Now after addition it has become 10. So I will not write 4 for this and 4 for this. No. I will write for 10 only. So 10. What I will get? 1, 0, 1, 0. Okay. Do it on your own. If you add 3 here, what you will get? 12. If you add 3 here, you will get 12. So my number is not 1, 2, 1, 2. No. 12, 12. My number is 12, 12. So for 12, what will be the BCD code? 12, 8, 4, 1, 0, 0, 0. And again 12, sorry, 1, 1, 0, 0. That would be the XS3 code. So in each digit you add 3 and then write it in this manner. Okay. So binary versus BCD, here I have given an example that 10 will be written as 1010 in binary This is your binary. But in BCD, each digit will be coded in 4. 0001 and 0 will be 0000. Right? Now, tell me, what will be the XS3 code for 0? XS3 code for 0. That means you will add 3 in 0, you will get 3. And what will be the binary code for 3? 0011. XS code of 1, you will add 3 in that. 4, what is the binary code of 4? That is 0100. But in 4 bits you need to write. 2 plus 3, 5. So for that, this will be the answer. 2 plus 3, 5. 3 plus 3 is 6. And then 7. Then 8. 5 plus 3 is 8. Then 9. Then 10. 10. Then 11. And then 12. Right? And 8421 code are very simple. I have already written 8421 code. You can already write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 8, 9 till 9 you can already write. On your own you can write. What about 8, 4 minus 2 minus 1? 8, 4 minus 2 minus 1. So you need to write 0. So 0 will be 0, 0, 0, 0. What about 1? How will you get 1? 4 minus 2 minus 1, right? 4 minus 2 minus 1. Then you get 4 minus 3, that is equals to 1. How will you get 2? 0, 1, 1, 0. 4 minus 2 is 2. How will you get 3? 0, 1, 0, 1. 4 minus 1 is 3. How will you get 4? So 0, 1, that is very easy. Directly 4 is there. How will you get 5? 8 minus 3 is 5. 8 minus 3 is 5. 1, 1. Look, 8 minus 2 minus 1, 5. How will you get 6? 8 minus 2 is 6. 1, 0, 1, 0. How will you get 7? 1, 0, 0, 1. How will you get 8? Sorry, wait a second. 0, 1, 2, 3, 4, 5, 6, 7. Now we need to write 8. So how will you get 8? 1, 0, 0, 0. And how will you get 9? How will you get 9? So all ones, right? All ones. If all ones are there, so 8, 4, 12, 12 minus 3, 9. Right? Now let's write down these codes. Okay. Let's practice something now. Let's practice a few questions. So 2 problems are there. 697, you need to write it in 8421 code. How will you write it? 8421. 6 can be written as, in 4 bits I need to write 6. So that would be 8421. Here only I will write 8421. So it would be 0, 1, 1, 0. What about 9? It would be 1, 0, 0, 1. What about 7? 0, 1, 1, 1. Okay, that is the BCD code, or 8421 code you can say, 8421. But generally only BCD word will be written. Now for XS3, you need to add 3. So in 6, if I add 3, it would be 9. So for 9, I will write 1, 0, 0, 1. In 9, if I add 3, that would be 12. 12. 1, 1, 0, 0. In 7, I need to add 3. That would be 10. 1, 0, 1, 0. That would be XS3. Let's check back again. 6 plus 3, 9. Okay. 9 plus 3, 12. Okay. 7 plus 3, 10. Okay. 8, 4 minus 2 minus 1. What do we need to write? 6. 6. So 8, 4 minus 2 minus 1. You need to write 6. So it would be 1, 0, 1, 0. Because 8 minus 2 is 6. You need to write 9. So how will you get 9? 1, 1, 1, 1. Or a bit closer I can write 1, 1, 1, 1. Because 8 plus 4, 12. 12 minus 3 is 9. And how will you get 7? For 7, 8 minus 1. 1, 0, 0, 1. 8 minus 1 will be 7. So this is how you write 8, 4 minus 2 minus 1 code. The state of a 12-bit register is this. Okay, 12-bit register. What is its content? Content in decimal. You need to tell the content in decimal. if this representation shows 3 decimal BCD code, so this is a BCD code of something. So whose BCD code is that? So you need to pick 4 bits. BCD means you need to consider 8421 now, because nothing is mentioned, so I will consider 8421. So 1000 will be 8. 0100, 0101, 0100, that would be, sorry, 100, so 1001, so that would be 9. 1001 would be 9. And what about 011? So 011 will be 7. So this is 897 in decimal. Whose BCD code will be what? This value. So this is the answer of first one. For the second one, first I will find BCD only, but this is a XS3 code. They are saying it is XS3. So if I find BCD and subtract 3 from each number, if I subtract 3 from each number, what I will get? 5, 6 and 4, right? 564. What will be the XS3 code of this? 5 plus 3, 8, 8 you will write. 6 plus 3, 9, 9 you will write. 4 plus 3, 7, 7 you will write. So this is the answer of second. Basically, XS3 code of this number is this number. XS3 code of this number, that means 897. 897 will be denoted by this. Did you understand the second question? Question B. It is very easy. XS3 code of this particular number is this. Okay, very straightforward. So let's write down all whatever that we have studied. 8421, XS3, 84, minus 2, minus 1. So you can, these are the decimal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8421 already we have written, XS3 also we have written, 84 minus 2 minus 1 also we have written. We know how to write down these numbers, how to write down these codes. In XS3 code, what do you see? That 0 and 9, if you see 0 and 9, so what is the XS3 code for 0? 0011. And what is the XS3 code for 9? 1100. Each bit is complemented. Basically 0011. From there you are going 1100. That means each bit is complemented, right? Each bit is complemented. So this property is known as self-complementary code, which will be used in combinational circuits. So that we will study later on in the next chapter only. We will study combinational circuit, but this is the property. Here you can see 0100, so 1011, 0101, so here 1010, 0110, so 011, sorry, 0110, so 1001, 0111, 1000. Okay. What about 84 minus 2 minus 1? Same thing goes here. 0000, 1111, 0111, 1000. That's why we are going with 84 minus 2 minus 1. Right? Like what was the need if we have 8421 code already? Why do we need 84 minus 2 minus 1? Because this also is all bits are individually complement. So these codes are known as self-complementary code. So if someone asks you XS3 and 84 minus 21 codes are self-complementary codes, and 8421 is not self-complementary code. Okay. And for weighted and non-weighted, weighted are 8421, 84 minus 2, weighted code. I told you which ones are weighted code, 8421 and 84 minus 2 minus 1, and non-weighted. So like in MSQ, they can frame a question like this, that which of the statement is true. Weighted codes are this, non-weighted codes are this. So in that manner, they can frame these kind of problems. So non-weighted codes are XS3 code. Gray code are also non-weighted. That we will see later on. Now we are going to study gray codes. So gray codes are unweighted code or non-weighted code. So here I can write now gray code. So what is gray code? That we will see. And it is unit distance code. So it is used in K-map. And what do you mean by unit distance code? That also I will tell. So it is used in K-maps. Okay. So why it is unit distance, that we will see. Both of the points we will see. Now you need to convert, any binary number is given, you need to convert that to gray. How will you do that? From binary to gray. So let's take an example. From example we will understand it. So first this number is given, so first I will convert it to binary. This is the binary, or why should I write 0? This is 1 1 1. This is your binary. So this I need to convert to gray. So the word that is written is, you are going from binary to gray. Binary to gray. Can you read it as BG? And can I read BG as BG? So if you are BG person, you will never look down. Can you remember this line? If you are a BG person, why would you look down? You have to work, na? So if I am converting binary to gray, this is my binary, and I am converting it to gray. So this 1 will come as it is. I will not look down. I will look ahead. So 1 XOR 1, what I will get? 0. I will not look down. I will look ahead. Again 1 XOR 1, what I will get? Again 0. So this is the gray code. This you are getting is gray code. So basically, if this is binary, then gray would be 1 0 0. This would be gray. Okay. Let's take more examples. Convert this to gray because this is already binary. Or let's make it more like this. So binary to gray you are going. Binary to gray. So if you are BG, you will never look down. So 0 will come as it is. You will look ahead. 0 XOR 1 will be 1. 1 XOR 0 will be 0. 0 XOR 0 will be 0. You are not looking down. You are just looking you are just writing down the answer downward. 0 XOR 1 1. 1 XOR 0 0. This is just a trick. Otherwise, I could have directly said that you need to remember it. But this is how I remember. If I am BG, why would I look? If I am BG, why would I look down? Now I need to convert gray to binary. I need to convert gray to binary. So how will I do that? So I am GB now. GB, not BG. GB. GB means ganda bachcha. Ganda bachcha. And if you are ganda bachcha means bad boy. If you are a bad boy, then you will look down. Because those who don't want to do anything in the career, they will look down. So 1 0 1 1 1. So ganda bachcha will look down. So 1 will be as it is. MSB comes as it is. MSB comes as it is. So this statement I will write for both of them. MSB comes as it is. As it is. After that, the game begins. So if you are ganda bachcha, you have to look down. So 1 XOR with 0 will be 1. So now this 1 XOR with 1 will be 0. 0 XOR with 1 will be 1. And 1 XOR with 0 will be 0. So first it came as it is. 1 XOR 0 1. 1 XOR 1 0. 0 XOR 1 1. 1 XOR 0. Sorry. 1 XOR 0 is 1. This 1 XOR 0 1 XOR 1 0 0 XOR 1 1 1 XOR 0 1. Okay. Do it on your own. 1 0 1 1 1. MSB as it is, but you have to look down. 1 XOR 0 1. 1 XOR 1 0. 0 XOR 1 1. And 1 XOR 1 0. So 1 1 0 1 0. That's the answer. So here the answer was 1 1 0 1 1. This was the binary, and here the answer is 1 1 0 1 0. This is the binary. Okay. So that way we can change. Now binary numbers I already know. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 15 14 15. Now let's take a random number and convert it to just for the practice, from binary to gray. Just for the practice, I am taking a random number 1 0 1 1. I need to convert it to gray. I am busy. Binary to gray I am going. I am busy, so I will not look down. So 0 XOR 1, 1. 1 XOR 0, 1. 1 XOR 1, 0. So this is our binary and this is our gray. 1 as it is, 0 XOR 1, 1. 1 XOR 0, 1, and 1 XOR 1, 0. I did not look down. At down I just wrote the answer. I was looking in the left or right, you can say. Okay. 0 and 1 XOR 0. Yeah. Now how do I write the gray codes? So 8 zeros and 8 1 first. Then how do we do? 4 zeros and 4 ones. Then in binary we write 4 0 and 4 1. But here what we need to do? We need to take the mirror image here. Wait a second. 1 2 3 4 0 and 4 ones. So 1 2 3 is 7. Okay, this I need to modify now. So again I will have to write 7 8 are there. So 0 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. So in the same manner 1 2 3 4 1 1 1 1. Now I will take the mirror image here. So 1 1 1 1 0 0 0 0. Here 2 times 0, 2 times 1, 2 times 0, 2 times 1. But again I will take the mirror image. 2 times 1, 2 times 0. Here again I will take the mirror image. 2 times 0, 2 times 1. Again 2 times 1, 2 times 0. So basically here 2 times we write. So 2 times 0, 2 times 1. Now 2 times 1, 2 times 0. Then 2 times 0, 2 times 1. Then 2 times 1, 2 times 0. Here 1 time 0, 1 time 1. Then 1 time 1, then 0. Now 1 time 0, 1 time 1. Then 1 time 1, then 1 time 0. Now 8 bits are there. Yeah. Now 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0. Are you getting this point? 2 times 0, 2 times 1, 2 times 1, 2 times 0, 2 times 0, 2 times 1, 2 times 1, 2 times 0. 0 1 1 0 0 1 1 0. Basically all the mirror images are there, no? Here also there is a mirror image. If you see here, whatever these 4 digits are the mirror image of these 4 digits. Here these all 8 bits are mirror image of these all 8 bits. You see, all 8 bits are mirror image of these all 8 bits. Right? Another mirror is here. These 4 bits are mirror image of these 4 bits. So everywhere, here also you can place a mirror. Here also you can place a mirror. Here also you can place a mirror. 0 1 1 0. So if there is a mirror, that means the same digit will be repeated. So which number we converted? 1 0 1 1. So that is coming out to be 1 1 1 0. Yes, the answer is correct. So this is how you can write the gray codes. Binary to gray directly. But for the 15, let's just say there is a big number coming, then we will not keep on writing the number. Big number. Another example, let's take 1 1 0 1 1 0 0 1 0 1. This is in binary. How will you convert it to gray? So let's write it down. 1 1 XOR 1 0 0 XOR 1 1 1 XOR 0 1 1 XOR 1 0 0 XOR 1 1 0 XOR 0 0 0 XOR 1 1 0 XOR 1 1 1 XOR 0 1 1 1 XOR 1 0 0 XOR 1 1 1 XOR 0 1 1 XOR 1 0 0 XOR 1 1 0 XOR 0 0 1 XOR 0 1 0 XOR 1 1 and 1 XOR 0 1. This is the gray code. So that's how we can convert it. Okay. Now what all are the unused cases in 4 bits BCD and XS3 code? So we wrote from, we can copy this, I guess. So if they are talking about BCD, that means they are only talking about 8421 and XS3. BCD means 8421. BCD means 8421, and XS3 means XS3 only. So let's forget about this. Let's not talk about this. So which all are the missed guesses here? This is 8 and 9 will be 1 0 0 1. If I need to represent 10 in BCD, what will be the answer? Will it be 1 0 1 0 in BCD? No, that is wrong. What will be the answer? 0 0 0 1 0 0 0 0. That will be the answer in BCD, right? That means this 1 0 1 0 is never used in BCD. 1 0 1 0 will never be used. So in BCD, what all are the unused bits? 1 0 1 0 will never be used, right? 11 will never be used. What that would be? 12 will never be used. 13 will never be used. 14 will never be used. And 15 will never be used. So these are the unused in BCD. And what about XS3? 0 0 0 0 will never be used. 0 0 0 1 will never be used. 0 0 1 0 will never be used, because the first one will be 0 0 1 1, because even for 0 it will be starting from 3 at least, right? And we are going till 9. 9 plus 3, 12. So till 12 we are going. That means 13 will never be used. 14 will never be used. And 15 will never be used. So these are the unused cases. BCD and unused in XS3. So in like one liner it may come that 0 0 0 is unused case in BCD. Is that statement true? No. 0 0 0 0 is used case in BCD. 1 1 0 0 is unused case in BCD. So 1 1 0 0 you will write okay 12. So 12 will not be written as 1 1 0 0. So certainly that is unused case. So this is how you will solve these kind of problems. Okay, and this is about XS3. So yeah, that's it about this video. Here we have studied the basics of code. So very simple video, very simple video. Just it will take you to 2 minutes to revise it. So I will do the revision by myself. So first we studied about binary codes. These are the codes 8421, 84 minus 2 minus 1, and XS3 code. If BCD directly is written, we will consider it 8421. So each bit is denoted by 4. Each digit is denoted by 4 bits. So 1 and 5, 3, 1, 9. XS3, each number will be increased by 3. Each number will be increased by 3. So now you are studying these codes, where we will use it, what we will do with these codes, that we will understand. Okay, no need to worry about that. So each will be increased. So 5 and 10. Here important thing to note that it will not become 510. It will be 5 and 10. It will be 12 and 12. So 12 in 4 bits and 12 in 4 bits. Then these are the codes. Then these were the example. Here this was the given in XS3 code. That means we have to subtract 3. So that will be our decimal number. From XS3 to decimal we are going. And these are the self-complementary codes. Okay, 0 0 1 1 1 1 0 0. So XS3 and 8 4 minus 2 minus 1 are self-complementary codes, and 8421 is non-self-complementary code. Okay, not self-complementary code. Yes, and weighted codes are 8421, 84 minus 2 minus 1, and non-weighted codes are XS3 and gray code, because in XS3 as well there is nothing weighted, right? Nothing weighted. Like you cannot say weight of this is 2 to the power 0, 2 to the power 1. Here in binary you can say weight of this is 2 to the power 0, 2 to the power 1, and 2 to the power 3. But there is nothing like that. Now if you need to go from binary to gray, so how will you go? Binary to gray. BG. If you are BG, you will never look down. 1 XOR 1 0, 1 XOR 1 0. Right? If you are going from gray to binary means you are GB. That means you are Ganda Bacha. If you are Ganda Bacha, that means you are looking down. So 1 XOR 0 1, 1 XOR 1 0, 0 XOR 1 1, 1 XOR 0 1. Okay, so that is the way of converting gray to binary and binary to gray. And how will you write in 16 numbers, or you can say in 16 decimal number? So binary we have already seen 8081, 4041, 4041, 2021, 2021, 2021, 2021, 0101 in that manner. Here 8041. Okay, 4041, 4140, 2021, 21, 2 0, 2 0, 2 1, 2 1, 2 0, 0 1 1 0, 0 1 1 0, 0 1 1 0, 0 1 1 0, 0 1 1 0, 0 1 1 0. In that manner we will write it. Okay. Yeah, that is the gray code. And what all are the unused bits that we have seen? These are the unused bits. So that's it about this video. In 2 minutes only you can revise it completely. In the next video we are going to see the BCD addition and XS3 addition. So we will study only the addition. When we study combinational circuits, we will design these circuits. We will design the circuit for BCD addition. We will design the circuit for XS3 addition. We will design the circuit for BCD subtractor as well. We will design the circuit for XS3 subtractor as well. Okay, so that we will do in our next chapter, but here we need to study all these kind of things as a prerequisite, that what is BCD addition, what is XS3 addition. So that we will be using later on. Okay then, yeah, so that's it about this video. Let's meet you in the next. Hi everyone, so let's start our video. So it is in the continuation of the previous video only. So now we are going to study about the arithmetics of the codes. So in that first we will study about BCD addition. So these are the rules, do not read it. Okay, just for the sake of writing it, I have written it. This is how you will solve it. This is the procedure to solve. So you need to perform a BCD addition. So what you will do? First you will add like binary. Then you will check then you will check if the carry is generated or not. If the carry is generated, then this guy is culprit. If carry is generated, that means this guy is culprit. If this guy is culprit, then we will add 6. That means we will add 0 1 1 0. You will be able to remember it. You will not forget, because we will solve a lot of examples. If carry is not generated, then we need to check the sum. If sum is greater than 9, then the guy is culprit. Again the guy is culprit, and if the guy is culprit, that means we will add 0 1 1 0. And if sum is less than 9, that means the guy is not culprit, then we can leave it as it is. So first add like binary. If carry is generated, then add 0 1 1 0. If carry is not generated, then you need to check the sum. If sum is greater than 9, then again the guy is culprit. And if sum is less than 9, then guy is not culprit. And do not do anything with the carry. Keep the carry as it is. Let's start solving the problem. 2 plus 3. What is 2 plus 3? I know. Answer will be 5. But if I do the BCD calculation, if I write 2 in BCD, 0 0 1 0. If I write 3 in BCD, that would be 0 0 1 1. If I add them, what I will get? 0 plus 1 is 1. 1 plus 1 is 0, and 1 goes carry. 1 0. Final carry is not generated. So this is the correct answer. What will be the BCD code of 5? BCD code of 5 will be 0 1 0 1 only. BCD code of 5. BCD of 5. What that would be? 0 1 0 1. So answer is correct. 21 plus 22. So 2 will be written as 0 0 1 0, and 1 will be written as 0 0 0 1. 2 will be 0 and 2 will be 0 1 0. So simply you need to do the addition. 1 plus 1 is 0. 1 plus 1 is basically 2, and 1 carry will go here. But final carry is not generated. Here nothing is generated. Here nothing is generated. So these guys are innocent. We will not do anything with that. And you can check what is the BCD code for 3. What is the BCD code for 4? That would be 0 1 0 0. What is the BCD code for 3? 0 0 0 1. Correct answer. Okay. Now someone will say that, sir, we can do this calculation on our own. Then we can simply convert. You can do it if this question is asked in the examination. Okay. But this question will not be asked. The problem will not be asked like that do the BCD addition of 21 plus 22. No. They will ask you to implement the circuit. Okay. And they will ask you to implement the circuit and write the equation of y. So there it will be used. So here we are studying BCD calculation. No question will be asked from here. That I can tell you. Even in the assignment, I will not put the questions from here. But all these things will be used when we study combinational circuits. So there I will be telling you, go revise BCD addition again. So all these things will be used there, right? Let's solve this problem now. 3 plus 1 is 4, 4 plus 2 is 6, 5 plus 3 is 8. That we know answer will be 864. But here, let's add it like binary. 1 plus 1 is 0, 1 goes here. So 1 plus 1 is 0, 1 goes here, it would be 1, 0. 0, 1, 1, 0. 1, 1, 0, 1 goes here, 0, 1, 0, 1. Right? So this is 8 only. This is 1, 0, 1, 2. So this is 3. Sorry. 1, 2, 4. 1, 2, 4. So this is 6 and this is 4 only. So no carry was generated here. No carry was generated. So no one is culprit here. Let's solve this problem. 1, 1, 0, 0. 1, 1, 1, 0. Till now no carry is generated. 1, 1, 0. 1 goes here. 0, 1, 0. 0, 1, 1, 0. 1, 1, 0. Here carry is generated. 0. Here also carry is generated. But no carry is generated here. No carry is generated here. No carry is generated here. Right? So I will not put the boxes. Instead I can tell no carry here, no carry here, no carry here, no carry here, no carry here. So no one is culprit. All are innocent. So 3, 7, 4, 6, 8. So it would be 864.73. You can check it. This is 7 only, this is 3 only, this is 4 only, this is 6 only, and this is 8 only. Now carry is involved. 9 plus 8 is 17. Sorry. 9 plus 8 is 17. But if I do direct BCD addition, then how will I do it? 1, 0, 0, 0, but carry is generated. If carry is generated, that means this guy is culprit. If this guy is culprit, then we can add this thing. Okay, so we have to add it. And then what did I tell? Do not do anything with the carry. We have to add it, but do not do anything with the carry. So 1, 1, 1, 0, and carry as it is. That's it. This is the answer. So 0, 0, 0, 0, 1. This is 1. And what is this? This is 17. And here what you were getting? 1, 0, 0, 0, 1. That means this is the answer you were getting. That is, this would be 1 and this would be 1. 11. Which is wrong? Answer is 17. So here you were getting 0, 0. Here only 1 I was getting. So I can add 0, 0, 0 in front. So this would be 1 and this would also be 1. So 11 I was getting here. So this was my 11. Which is wrong. So I have to add 0, 1, 1, 0. But I will not do anything with the carry. Carry will come as it is. Let's solve this one. 1, 1, 0, 0. 1, 0, 0, 0 and 1. As per this, what is the answer I am getting? 1. This will be 1 only because 0, 0, 0 I can add here. So this will be 1 only. What this will be? This will also be 1 and what this will be 3. So I am getting 1, 1, 3 which is wrong. Right? So who generated the carry? Who generated the carry? This guy generated the carry. This guy generated the carry? No. Who generated the carry? This guy generated the carry. So if this guy is generating the carry, then we will add 0, 1, 1, 0. Okay. And we will not do anything with other guys. So this will come as it is. Now I will have to add here 1, 1, 1, 0 and this will come as it is. So what I am getting? 173. These are just the method. You will get habitual of it. Okay. No need to worry. Sir, these are the methods. How will I remember it? You will get habitual of it. No need to worry about that. Okay. Let's add this up. So 1, 1, 0, 1, 0. Here 1 plus 1 will be 0 and 1 is carried. So this guy generated a carry here. This guy generated a carry. So this guy is also culprit this time. 1, 1, 0, 1, 0 and this would be 0 and 1. So this is, both of the guys are culprit this time. So here I will add 0, 1, 1. Look, in between if carry was generated here, that is fine. But the final term is generating the carry. Here the final term is generating the carry. So that means he is a culprit. So he is also generating carry. He is also generating a carry. So all are culprit. I will keep this as it is. So I will write down the final answer now. 0, 1. Sorry, 1 plus 1 is 0, 0, 1. टेढ़ा क्यों लिखा जा रहा है भाई? 1, 0, 0, 0, 1 and this is 1. So what is this? This is 1 only because 0, 0, 0 I can add 1. What is this? This is 8. This is 8. So correct answer. Okay. So wherever you see the culprit, you catch that up. What will be the answer of this one? 998. 1999.98. So let's add that up now. So here 1 plus 1 will be 0, 1, 0, 0. So 1 carry is generated. So this guy is culprit. Now 1 plus 1 plus 1, it would be 3, right? It would be 3. 3 is written as 1 1, so 1 goes here, 0, and this is again 0, dot will come as its place. So 1 plus 1 is 0 and 1 again is carry, so this guy is also culprit. So you add them up again now, so 1 1 0 0, again 1 goes carry, so again the same procedure will come, 1 1 0 0, again 1 goes here, so it would be 1 1 0 0, and again 1 is carried. So all are culprit, all guys are culprit, right? All are generating the carry. So what I will do, in every one I will add this. And this, every one I will add this and this. Okay, let's add that up now. So 0 0 and 1, right? What about this? 1 0 1 1. Wait a second, that's something is wrong. Yeah, it would be 0 only, no? 1 as it is, 1 plus 1 will be 0 1 0 1 1 0 0 1 1 0 0 1 1 0 0 and 1, and this one come as it is. So there you go, you can see. Okay, so this is 1 only, this is 9, this is also 9, this is also 9 point, this is also 9, and this is 8. So 1999.98. So are you getting the point? And in between, let's just say you get a carry in between. Let's just say if this was 0 plus 1, so here you would get 0 and 1 carry would be there. So if this happens, then again you are not going to do the same thing, that again add 0 1 1. No. What I mean to say is that here it is 0 0 1 1 0 0 1 0 and 0 1 1 0 and 1 1 1 0. Let's just say if this calculation was there at this place, if this calculation is there, then which will not be possible, I guess. Yeah, that will not even be possible. But let's just say even if you get, then 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is 0, and you get 1 carry here. In this calculation I am talking about. So you get 1 carry here, then let it be. You are not going to add here 0, you are not going to add 0 1 1 0. Just because this guy is not culprit now, he was culprit here and he got it. Okay, so nothing you are going to add. If this calculation is here, okay, if this calculation is here, then you are going to add. So just for one step you need to add 0 1 1 0. Okay, so this is all about BCD calculation for this particular case. Now we will see more cases. Yeah, in these cases when we solved, we always need to check whether the sum is greater than 9 or not. So nowhere the sum was greater than 9. 4 3 8 6 4 8 6 4 7 3. So nowhere the sum was greater than 9. But here we will check it. 1 plus 1 is 0. This will 1. This will be 1. No carry generated. So this is not a culprit. No. What we need to check? We need to check what is the sum. Sum is 10 here, which is greater than 9. So we need to add 0 1 1 0. Right? So what that would be? 0, 1 plus 1 will be 0, 1 plus 1 will be 0, and 1 here, and this would be 1. And rest, so we can see rest 3 0 I can add here. So this is my 1 and this is my 0. Here this is not even a valid BCD code, because in BCD code 10 cannot come. So for BCD code, this is what we are doing, BCD addition. So in BCD code you have to write in this manner. So now let's do it. This answer we already know, answer would be 60, but let's solve it here. 0 1 0 1 1 0 1 0. Check the sum. What is the sum here? 10. Carry is not generated, but sum is 10, so that means this guy is culprit. So we have to add 0 1 1 0. So 0 1 plus 1 is 0 1 0 1 0, and 1 goes here. So here we are giving a carry. That doesn't mean it becomes culprit again. No, forget it. Culprit, he was here. Now it is not culprit again. So 1 plus 1 is 0. 1, 1, 0. The answer would be 60. Okay. Let's solve this one here. 1, 1, 0, 1. 0, 1. Sorry. 1 plus 1 is 0, 1, 0, 1, 0. 0, 1, 1, 0. Let's check who is culprit now. Who is culprit? This guy is culprit because the sum is greater than 9. So we have to add 0, 1, 1, 0. So let's add it up. So 1 plus 0 is 0. 1 plus 0 is, so this calculation you can do on your own. This 1 goes here. 1 comes here. 0, 1, 0, 0, 1, 1, 0. So what is this? This is 6. What is this? This is 5. And what is this? This is 1. So you are getting the correct answer. Okay. So you are getting the correct answer. Right. Now sum is greater than 9 and carry is also generated. Both cases are there. So you do not even need to think here. If carry is generated, that means that guy is culprit. So we will do this. 0, 1, 0, 1. Carry is not generated, but I know that this is greater than 9. So this guy is already culprit in my eyes. What about this one? 1 plus 1 is 0, 0. 1 plus 1 again 0. 1, 1 again 0. 1 again 0 and then 1. So this guy is also generating and this guy is greater than 9. This guy is greater than 9 and this guy is generating the carry. So both are culprit. Both are culprit. Do not do anything with the last carry. Let it come as it is. What about this one? 0, 1 plus 1, 0, 0, 0, 1, 1, 1, 0. This is 1, 7 and 0, 170. What about this one? Answer I already know, but let's solve it with our BCD calculation. 1, 1, 1, 1. I already know this is culprit. 1, 1, 1, 1. This guy did nothing. Less than 9, no carry. 0, 0, 0, 0, 1. This guy generated a carry. If carry is generated, you don't even need to look at the addition. Look at this result. You don't even need to look at this result. If carry is generated, that means he is culprit. So I will add. This guy did nothing. This is less than 7 as well. Carry also not generated. I will not do anything with that. But this guy is greater than 9. So this guy is also culprit. Now I will do simple addition. So 1, 0. 1 plus 1 is 0. This would be 3. So this would be 1 here and this would be 0. So 1 goes here. So 1 plus 1 will become 0, 0, 0 and 1. 0, 1, 1, 0. And this would be 1, 0, 0, 0. 1, 6, 8, 5. Yes, this is 1. This is 6. This is 8. This is 5. So this is the last example where everything is used. No culprit guy. Looks like no culprit because it is not generating carry, but it is having sum greater than 9. This is generating a carry, but sum is less than 9, but that you don't need to think. If carry is generated, then he is culprit. So 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1 here. Simply do the addition. 1, 0, 1, 0. 1 carry is getting here. So do the addition here as well. 1 plus 1 is 0. 1 plus 1 is 0. Again 1 plus 1 is 0 and 1 is carry. So 1, 0, 1, 1, 0. I hope you know how I am doing the calculation because I have already taught you binary calculations. So that I am doing only. Okay. Now let's study about XS3 addition. So in XS3 addition, what we need to do? Even if the carry is generated or carry is not generated, both guys are culprit. Okay. And for the left alone carry as well, we need to do something. So for everything, we will do something. If carry is generated, then culprit will be added, because in the last one as well, if carry was generated, we were adding. So if carry is generated, we will add, and if carry is not generated, then we will subtract. And what we will add to subtract? Since this is XS3, so 3. So 3 we will add, 3 we will subtract. And if carry is carry alone is left. In the end, carry alone is left. So do the same operation which you have done previously. We will tell it, or you can simply remember that you need to add 3 in carry. So let's see the first example. So in this one you need to add them up. So what you are getting, 1 1 1 1, no carry. Even if there is no carry, both are culprit. So what we need to do, we need to we need to subtract 3. So always remember we need to subtract 3. So if we are subtracting 3, what we will do, 0 0 1 1. Now if you convert it to binary, what you are getting? If you convert it to binary, you are getting 12. So yeah, this is what you are supposed to get. When we were yeah, so I was saying, when we were doing BCD calculation, we were getting answer in BCD. So when we are doing XS3 calculation, we are getting answer in XS3 only. So this answer is XS3 of 9. This answer is XS3 of 9. Okay, so we will get the final answer in XS3 only. If I am doing calculation in the next, we will be studying 1's complement. So if I am doing the calculation in 1's complement plus 1's complement, my answer will be 1's complement only. So XS3 addition plus XS3 addition, I am expecting my answer to be in XS3 only. So this is my XS3 answer. Let's do it for this. So 0 0 0 1 and 1. So this guy is generating a carry. This guy is generating a carry. So he is a culprit. So for culprit, what we will do? We will add 1 here. Now this will not come as it is. What will happen to this? This will be also added with 3. This will also be added 3. Okay, in carry as well you need to add 3. So 1 1 in the final carry. Okay, so 0 0 1 0. So what you are getting, 1 2 4. So this is 4, and what is this, 1 2 4 8, that is 11. So what is the BCD code for this, 4, and what is the BCD code for, sorry, not BCD, XS3 code for this, 411. So same thing you are getting here, 411. Okay, so yeah, so this is the XS3 answer. XS3 of, again and again we will not write, but yeah, XS3 answer, you will get the answer in XS3. So now what about this, just add them, 0 0 1 plus 1 will be 0 1 and 1. So this guy is also culprit now, but this is not left alone carry, it will be used. 1 plus 1 is 0 1 and 1. So this will be added. So here this is also generating carry, this is also generating carry. So all are generating carry. 0 0 1 1 0 0 1 1 0 0 1 1, all will be added, all are added. 1 1 0 1 0 0 1 1. It might seem a bit boring, this lecture might seem a bit boring, and I understand that, but we have to study it as a prerequisite of our next chapter. So that we need to study. 1 plus 1 is 0 0 1 0. So what you are getting here, 4 12 and 4 12 and 11, 4 12 and 11, which is XS3 of what, XS3 of 1 9 8. Is that the answer? Yes. Let's solve this one. 0 1 0 1 will be added here, so this will be 0 and 1 goes here. So this guy is also culprit. Culprit, all are culprit, but it will be added. 1 plus 1 is 0. Again 1 goes here, 0. Again 1 goes here, 0 0, and this is 1 1 0 0 1 1 0 1 1 1 1 1 1. Okay, so okay, we forgot to check. So this guy generated 1 1 0 1. So this guy did not generate. This guy did not generate any carry. What about this? 1 1 0 1 1. This guy also did not generate any carry. This guy also did not generate any carry. So what will happen to these ones? Subtract here subtract. And what about this? This guy also did not generate any carry, so again subtract. What about this guy generated a carry, so added. And this guy also generated a carry, so added. Let's do the final calculation now. 1 0 1 0, right? 1 0 1 0, 1 1 0 0 0 1 1 0 1 1. Oh, sorry, subtraction you need to do. So 1 minus 1 is 0. Here you take you will take plus 2 from here. So plus 2 minus 1 will be 1. Wait a second. What is the issue? 1 0 0 1, and you need to subtract 0 0 1 1. So what is this number? 1 2 4 8. This is 9 minus 3. Answer will be 6. This number is 9 minus 3. Answer will be 6. So answer will be basically 0 1 1 0. 2 is getting 2 you are getting from here, plus 2. 2 minus 1 is 1 here. How this is becoming 1? So this will also take some from here. So this will become, the thing is, you cannot take 2 from here. You will take 2 from this 1, right? So first it will take, and then you will take. Basically this is like 5 0 0 minus 4. I am doing this calculation. So how will I do it? This will take 1 from him, and then it will take 1 from him. So what you will do? 10 minus 4 6. 10 minus 4 6. So this is getting plus 10. This guy is getting plus 10. So similarly this guy is getting plus 2. 2 minus 1 is 1. What about this one? This one will be 9. This one will be 9, right? Just 1 lesser than the base. So similarly this guy will be 1, and this guy will be what? This guy will be what? 1 lesser than what it was, 4. So this guy will be what? 1 lesser than what it was, 0. 0 minus 0 will be 0. You can take the difference of this, right? We were supposed to do this calculation. We were supposed to do this, which will be 4 minus 1, that means 3. 3 means 0 1 1. We will get 0 1 1. So how do we do it? We have we are directly borrowing from here. So it will be plus 2 minus 1. What this would become? This would become plus 1. Similarly this would become 9. So this would become plus 1. Plus 1 minus 0 is 1. What about this one? This will become just 1 lesser. 0 minus 0 is 0. Just now I also encountered it. Before all I did not even encounter. So these for these smaller calculation, you can just take the example of decimal and solve it, right? And what about this? 1 minus 1 is 0, and this 2 goes here. 2 minus 1 will be 1. This will be 0, and this will be 1. This calculation was easy, right? This you could have solved. Although here only I can see that it is 15 minus 3. So 12, 13, 13 minus 3. So 10 I am getting, or 1 minus 1 is 0. Cannot subtract 0 from 1. So 1 it will take as borrow. So it will be plus 2. Plus 2 minus 1 will be 1. This will be 0 as it is. This will be 1 as it is. 0, 0, 1, 1. So let's just see what we are getting here. 12. What we are getting here? 10. What we are getting here? 6. What we are getting here? 3. And what we are getting here? 5. So these are excess 3 of 9, 7, 3, point 0, point is there, point is there, point 0, 2. So is that the answer? Yes. Okay. So if I convert this into excess 3, this into excess 3, so that will be the expression. So that's it about this video. Very small video it is. So I will try to add calculation and codes in the same part only, because it would be less than 1 hour. So we will add it up. So yeah, it was like just the method you need to remember. Okay, just the methods you need to remember, that this is the way we solve. Where it will be used, that will come, and the questions can also come on this particular topic, BCD addition and excess 3 addition, because not many people take care of this. It might seem a bit boring, but interesting part of this will come in combinational circuit. So do not need to worry. You don't need to worry. Okay, a lot of interesting part of this particular chapter will come. Now we are going to study about signed representation. So till now we are seeing only unsigned number. Now we will represent the signed number as well. So we are going to see now signed representation. So signed number representation we can say. So numbers will be signed now. So that we will see, and that is the very important topic, and a lot of people are confused in these topics. A lot of people are confused in these topics as well. Like BCD addition is not that straightforward, but we have broke down in a way that it is looking like very simple. And this is our chart. From here we can solve all the problems. If we just remember this chart, we will be able to solve all the problems of BCD addition. And if we just remember these lines, that all are culprit. If carry is 1, add 3. If carry is 0, subtract 3. And if left alone carry will be added 3. Here left alone carry will be coming as it is. In left alone carry, added 3 will be added. So yeah, only these two things were there in this lecture. So it would be it. Okay then. Yeah, thank you very much. I will add both of the videos. Hi everyone. So in this video we are going to start studying about signed number representation. So this is a very important topic and also very conceptual topic as well. And I will tell you 99% of the students are not comfortable in this particular topic. So you have to listen to my words very carefully. Everything that I am saying, you need to take full amount of attention while watching this particular lecture. Okay, so I require your complete attention now. So till now we were talking about only unsigned number, right? Like I told that write down what you will write down 23 in binary. So you wrote it down. 23 in binary, that would be 23 in binary, that would be 10111. So you wrote it down in that manner. There was no negative sign, nowhere we used any negative sign, but we need to represent negative and positive both numbers now. So we will use certain ways. So first we will see signed magnitude representation, then we will see r minus 1's complement representation, then we will see r's complement representation. What is r? R is the base here. What do you mean by r? R is the base. So if base is 10, if base is binary, if base is 2, then r minus 1's complement will be 1's complement. R complements will be 2's complement. Decimal 9's complement. In here it would be 10's complement, right? In octal it would be 7's complement and 8's complement. And in hexadecimal it would be what we say F's complement. F's complement, or EF, G's complement you can say. EFG, yeah. Your 15 will be F and this would be G's complement you can say. Now we are going to study about our first representation, that is signed magnitude representation. But before that, just answer this particular problem. Express 24 in binary representation. We have already studied it, right? Decimal to binary. How you will express 24? 8, 4, 2, 1, 16. 24 you need to represent. So it would be 1, 1, 0, 0, 0. So that would be the answer. That's it, right? Very easy. We have studied this binary representation. So there was no sign involved, nothing like that. Now we are going to study signed magnitude representation. Look, these two names can be confusing. This is signed number representation. In signed number representation, all three will come. Signed, r's complement, r minus 1's complement. And this is signed magnitude representation, which is a separate thing. Signed magnitude representation is separate from this one. Signed number representation, that is the union set, and these ones are subsets. So signed magnitude representation is a part of signed number representation. So now we are going to study about signed magnitude representation. So here the MSB bit will tell the sign and rest of the bits will tell the magnitude. Okay, if MSB bit is 1, that means it will show negative sign, and if MSB bit is 0, that means it will show positive sign. So MSB bit will show the sign and rest of the bits will be modulus. Okay, represent plus 24 in signed magnitude representation. You need to represent plus 24. So MSB bit will be sign bit. So plus means 0. What about 24? 24 can be represented as 1, 1, 0, 0, 0. Right? 1, 1, 0, 0, 0. So this is how I will denote 24 in signed magnitude representation. This is signed magnitude representation. 24 in signed magnitude representation. So this bit is the sign bit. and these are the magnitude. Okay, so here how many bits you required? 3 plus 2, 5 and 6. Total 6 bits required. Total 6 bits required. So to represent 24, here total 6 bits were required. In binary representation, to represent 24, how many bits were required? 5 bits required. Total 5 bits required. Here which bit is added more? That is sign bit. So here total 5 bits required. Represent minus 24 in signed magnitude representation. So same thing will happen, just initial sign, this is the sign of negative and rest all will be the same. Okay, now this is the question, which decimal number is that? So this number is represented so which decimal number is that? So first one will denote sign and it will be 1248, 1248. So minus 13. Wrong answer. Why it is wrong? Because where did I say that this is signed magnitude representation? I did not say that it is signed magnitude representation. I have to tell that it is a signed magnitude representation. Then I will say that my MSB will be my sign bit. But here the number is 11011. I did not say this is a signed magnitude representation. Where is mentioned that it is signed magnitude representation? This is simply binary number. This is a simple binary number. So 1248, 1248, 16. So 16 plus 8 is 24 plus 3, 27. So this is the correct answer. Okay, this is wrong. 3, 8 plus 3, 11, 27. So this is the correct answer. 27 is the correct answer. Minus 13 is wrong. Okay, if I had written this answer, that is wrong. So you have to tell whether it is SMR or not. This question is given. The given number is represented in signed magnitude representation. Which number is that? So what will be the answer for this? So 1, 1, 0, 1, 1. So this bit will be sign bit. That means minus sign. And this bit will be the magnitude. So 1, 2, 4, 8. So 4 plus 1, 2, 4, 8. So this will be minus 11. So 1, 2, 4, 8. 8, 4, 12. Okay, here. Okay, yeah, sorry. 1, 2, 4, 8. Better to write always. 8 plus 2, 10. 8 plus 2, 10 and 11. Okay, it would be 11 only. This would also be minus 11 only here. 1, 2, 4, 8. Yeah, minus 11. So now this will be the correct answer. Okay, this will be the correct answer because it is represented in SMR. So that you need to take care. Now let's see next question. You need to represent 24 in sign magnitude representation but in 8 bits. So MSB bit will be of sign. So that will be 0. Now rest 7 bit will be denoted to 24. Rest 7 bit 3, 3, 6 and 7. Now how will you denote 24 in 7 bits? 1, 2, 4, 8, 16. So 1, 1, 0, 0, 0. 1, 1, 0, 0, 0 and rest to these two will be 0 only. Basically I need to denote 24 in 7 bits. 24 in 7 bits. How will you denote it? 24 in 7 bits. This bit is sign bit. So that will be 0. Now 24 in 7 bits. So it will take 5 bits. So 1, 1, 0, 0, 0 and rest 2 bits will be the magnitude. So 5 plus 2, 7 plus 1, 8. So answer would be 000, 000, 11, 000. 000, 11, 000. So 11, 000 and then 2 more bits. This will be 24 only and because of for the plus there will be a 0 sign. So this is the correct answer. What about this one? Here it will become 1 only. This sign will be 1 and rest all bits will be the same. Just the sign is changed. For negative sign 1 will come. Now 24 I need to represent in 7 bits. So 24 I am representing in 7 bits. There you go. Okay. So this is the answer. So till now again I am telling you because all things are being will be getting mixed now. Okay, so you will be getting confused, that I know. So that's why we are going step by step. So binary number representation was there and sign magnitude representation there. So we have studied two kinds of that. So binary number representation we already know. In sign magnitude representation, first MSB will be of sign, +1 for negative, 0 for 0 for positive, and they have to mention if it is a sign magnitude representation or not. Okay, that's it. And in 8 bits this is how we will mention, and in 8 bits negative number this is how we will mention. Now the range of binary number, so 0 0 0 1, this will be 2, this will be 3, this will be 4, this will be 5, this will be 6, this will be 7. So in 3 bits we are going till 7. So in n bits we are going from 0 to 2 to the power n minus 1. Do you remember it? For 4 bits total possible combinations are 16, but in decimal we will go till 15 number. So from 0 to 2 to the power n minus 1, from 0 to 2 to the power n minus 1 for n bits. This we already know. Now in sign magnitude representation, this represents the sign. So this is +0, this is +1, this is +2, because this is the sign bit. This is the sign bit. So this is sign bit. This is +3. This is minus sign. Minus sign, 0 0 will be 0 only. This is minus sign. 0 1 will be 1 only. If I ask you represent -1 in a signed magnitude representation, so how will you represent it? 0. And how can you represent 1? 0 1. Right? Are you getting this point? 1 can be, or you could have done in this manner as well, that I can represent 1 in this manner. So this would also be the answer. 1 1 can also be the answer. This is also correct. You need to represent -1 in a signed magnitude representation. So 1 will come for this, and this 1 will be 1 in binary can be written as 1 only. So 1 1 can also be the answer. If I am saying represent -1 in signed magnitude representation but in 3 bits, so 1 bit will be of sign, and what about the other 2 bit? Other 2 bit will be used for 1. So how will you write 1 in 2 bits? 0 1. So 1 0 1. So this is what you will get. And what this will denote? What this will denote? -2. And what this will denote? -3. So what all numbers you are having? -3 to +3. Here -0 is not equals to +0. But actually -0 is equals to +0. But in signed magnitude representation, -0 is not equals to +0. So if there are n bits, then how you are going? So let's understand it. So if there are n bits, total number of possible combinations are 2 to the power n. -2, because zeros are 2 different zeros are there, divided by 2. Basically, why I am doing in this manner, I just want to tell from where the formula is coming. I need to find this number, or sorry, from this number. I need to find this number. How will I find this number? If I am having 3 bits, so total possible combinations are 8. So I should be getting from 0 to 8, but 2 zeros are there. So I should be getting from 0 to 3, but negative numbers are different. So divided by. So basically I have 6 numbers now. I have 6 numbers. 2 zeros are different, that is being repeated. That is being eradicated now. Zeros are gone. Now I am left with 6 numbers. So 1, 2, 3, 4, 5, 6 I should have made, but 3 negative and 3 positive will be there. That means -3 to 3. So 8 minus 2 is 6 by 2. Are you getting this thing? If you are not getting, then you can simply remember it. So from -2 to plus of this. Or it can be written as -2 to the power n minus 1 -1 to plus 2 to the power n minus 1 -1. Very important. This is the range. अरे यार, now let's try writing it for 4 bits. If there were 4 bits, so total combination would have been 16. Total combination would have been 16. 2 zeros will be there. 14. 14 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But we have to represent positive as well and negative as well. So divided by 2. So 14 by 2 is 7. 14 by 2 is 7. So from minus 7 to plus 7. Okay, and if you put the value in the formula, so if you put 3 here, so sorry, if you put 4 here, so 2 to the power 3, 2 to the power 3 is 8. So 8 minus 1 is 7. So minus 7 to plus 7. Same thing you are getting. Okay. Represent minus f to 7a in sign magnitude representation. But this is in hexadecimal. So this negative sign is there. That is a sign bit. Now can I convert this number into binary? Yes. What will be f? 1 1 1 1. So this negative sign is showing you that here 1 should come. Rest all will be the magnitude. 2 in 4 bits. 0 0 1 0. 7 in 4 bits. 0 1 1 1. A is 10. 10 in 4 bits. 1 0 1 0. That's it. This is the signed magnitude representation. What about this one? The minus sign is saying you 1. 7 in 3 bits. 0 in 3 bits. 2 in 3 bits. That's it. This is signed magnitude representation. What about this one? Minus 43 but base 5. From base 5 to you are going to base 2. Can you directly do it? No. So first I need to go to base 10. So forget about the minus sign. Minus sign is there. That I am keeping in mind. That minus sign is there. Minus sign is there. What about 43? So 43 can be written as 3 plus 4 into 5 to the power 1. That means 23. So this is 23 10. So this number can be written as minus 23 10. So minus sign bit 1. What about 23? 23. You could have done in this manner as well. 23 11 1 will be left. 5 1 will be left. 1 will be left. 0. So that would be the answer. That 1 0 1 1 1. Right? Or you could have think in this manner as well. 8 4 2 1 16. So 23 you need. So this would be 24. So 16 plus 4 plus 2 plus 1 would be 23. So 1 0 1 1 1. In that manner also you could have think, or you could have gone in this manner as well. So this would be the signed magnitude representation. Signed magnitude representation. Well and good. So this we have studied about signed magnitude representation. Now we are going to move to r minus 1's complement representation. R minus 1's complement. So for 10 it would become 9's complement representation. For 8 it would become 7's complement representation. For 16 it would become f's complement representation. For 2 it will become 1's complement representation. So how do we find a complements representation? So 9's complement representation of 27, what that would be? So what is the, how many digits are there? Two digits are there. So what is the maximum number of 2 digits in decimal? 99. So 99 minus 27 you need to do. This is how you can find your 9's complement. So what you will get? 72. This is the answer. Okay. If you need to find 7's complement representation of 35. So what is the basically write 7 7 2 times. 7 7 2 times minus 35. Maximum number would be 7 7. In base 8, what will be the maximum number of 2 digits? That would be 7 7. So 2 minus 4. Basically, if I had to write the 7's complement of 432, what I would do? 7's complement representation of this number. So I would do 777 minus 432. If I need to write 9379215, 9's complement of this. So what I will do? 9 9 9 9 9 9 9. So 9379215. So I will just subtract it. So just how many digits are there? These many 9's I will write. That's it. Okay. So this is 42. What about this one? So f's complement, that means f A23. So 15 minus 3, that would be 12. And what is 12? C. 15 minus 2, that would be 13. What is 13? D. And 15 minus 10, that would be 5. So 5 DC, that would be the answer. Okay. But these are not important at all. No one will ask you, and nowhere you will use it. What is important? Because our computer will understand binary only, 1 or 0. So the important is one's complement representation. This is the important part. So you need to check first what is the procedure. You need to check if the number is positive or negative. If the number is positive, then the sign magnitude representation will be 1's complement, it will be 2's complement as well. So if number is positive, you don't need to think much. But if the number is negative, then first you will write sign magnitude representation, then you will keep the sign bit as it is and subtract rest of the number from 1 1 1 1 1. Or you can take complement of each magnitude bit. Let's understand by the example. So this is the first example. First what we need to check, we need to take 1's complement of this, 1's complement representation of plus 21. How we will take 1's complement of this? We need to check whether the number is positive or negative. If the number is positive, it will be same as SMR. It will be same as SMR. So for positive sign, 0 would come. And how will you denote 21? That would be 16 plus 4 plus 1. That's it. This is your 1's complement representation. So binary only I can write, and then I can say this is 1's complement representation. It will be same as SMR as well. And even that 2's complement representation will be the same. So for positive numbers, signed magnitude representation, 1's complement representation and 2's complement representation all are same. Okay. Sign bit plus 0 copied and rest of all the bits are 1, 2, 4, 8. Okay. Again I am doing it wrong. Again and again I write it wrong. 21 I need to write. 21. So 16. 1, 2, 4, 8, 16. So 21. So 16 would come and 4 would come. Yeah. So 1, 0, 1, 0, 1. That would be the answer. Okay. But if the number is negative, then let's check what will happen. So you need to represent minus 21 in 1's complement form. Okay, or 1's complement representation. So first task is write down the sign magnitude representation. So negative sign 1 will come. What about 21? 1, 0, 1, 0, 1. Now what you need to do? This sign will be as it is. And you will subtract 1, 1, 1, 1, 1. So you will subtract 1, 0, 1, 0, 1 from this 1, 1, 1, 1. So what you will get? 0, 1, 0, 1, 0. So this you will write here. 0, 1, 0, 1, 0. Okay. But what you can see, sign bit is as it is, and these are the complements of each other. These are simply the inverter ones of each other. So here the second point, what did I write? Keep the sign bit as it is, but take the complement of each magnitude bit. Or you can simply take the complement of each magnitude bit. Now represent plus 21 in 1's complement but in 8 bits. How will you do it? What is the scene? Number is positive. So it will be the same as SMR will be equals to 1's complement representation will be equals to 2's complement representation. First bit will be of sign bit. Rest all the bits will be used to write down 21. So 5 will be used to write down 21. 21 will be written as this. So 5 bits will be used. So 3 bits will be 0. 1, 2, 3, 1, 0, 1, 0, 1. That's it. Wait a second. 0, 1, 0, 1. Okay, just a second. I am getting. Yeah, so this would be the answer, right? Simply the sign magnitude representation you need to write. That's it. Now minus 21 is there. So what did I tell you? First write the sign magnitude representation. What will be the sign magnitude representation of minus 21 in 8 bits? Sign magnitude representation. So minus will be denoted by 1. How 21 will be written? In 7 bits you need to write 21. 7 bits you need to write 21. So 1, 2, 3 and 5 bits for 1, 0, 1, 0, 1. So this is your 21 and this is your negative sign, right? Now if I am writing 1's complement, then this is your 1's complement. This is your 1's complement representation. So if I am writing 1's complement representation, then what did I tell you? 1, this sign bit will be as it is, rest all will be complemented. 1 1 1 0 1 0 1 0. There you go. Okay, first bit, sorry, this bit as it is, rest all complemented. 1 1 1 0 1 0 1 0. Are we taking more example? Let's take more example. Okay, let's take more example. Example is, you need to represent minus 37, or we should do minus 28 would work. Minus 28 in 1's complement representation. Okay, so in 1's complement representation. So first I will write sign magnitude representation. So minus sign 1 would be there. How will I write 28? 28. So 1, 2, 4, 8, 16. 28 you need. So 24 plus 24, 20. So this this would be 1 1 1 0 0. Right? 1 1 1 0 0. So yeah. So this is sign magnitude representation, and what will be 1's complement? So this one will be copied as it is, rest all will be. So this is the answer in 6 bits. These answers are in 6 bits. If I need to do the same in 8 bits, then what will be the answer? This is the first one. If I need to do the same in 8 bits, so this one will be, sorry, the sign bit 1 will be as it is. Now I need to write 28 in 8 bits. So this 0 0 1 1 1 0 0. 5 bits these. Now 1's complement. This 1 will come as it is. 0 will be 1, 0 will be 1, 1 will be 0, this will be 0, this will be 1 1. So this will be represented in 8 bits. Getting the point? Okay. So I hope you are comfortable with sign magnitude representation and 1's complement representation. Now this number is given. This number n is represented in wait a second. Yeah. So this number is represented in sign magnitude representation. So which number is that? Number is represented in sign magnitude representation. So very easy question. 1 1 0 1 1. So this will represent the sign. So minus sign, and this will represent the magnitude. 1 2 4 8. So minus 11. Okay, very easy question. These kind of questions we have already solved. Okay, so this is the answer. Right? Now this number is given. This is a note. This number is given which is represented in sign magnitude representation only. Now I need to take 1's complement of that. It is represented in sign magnitude representation. That means this MSB will be as it is. If I am taking 1's complement of that, 1 will be 0, this will be 1, and this will be 0. So this will be 1's complement of n. 1's complement of n, and n is there in sign magnitude representation. N is there in sign magnitude representation. So it is 1's complement of n which is there in sign magnitude representation. Now what if I again take the 1's complement? If I again takes the 1's complement, 1's complement. So this 1 will be as it is, 1's complement. Yeah, one more thing I forgot to tell. If I am saying that this is like in minus 1 I have taken this 1's complement. So this will be considered as a sign magnitude representation as well. Like this 1 will show the sign only. That's why we are not doing anything. So this 1 is showing the sign. Okay. This 1 here shows the sign as well. Same goes for 2's complement as well. This MSB bit will show the sign in 1's complement as well, in 2's complement, or in signed magnitude representation. In all these three things, the MSB bit will show the sign. So this is showing the sign. This 1 is showing the sign. We will not do anything with that. For rest of them, we will take the complement. 1 0 1 1. So what we are getting? 1's complement of 1's complement of number n in signed magnitude representation, which is equals to the number in, basically this is the same thing we are getting here, right? So if you take 2 times 1's complement, you get the same number. If you take that 1's complement twice, you get the same number. So I am getting the same number which is denoted in signed magnitude representation. Make sure this number is in signed magnitude representation. So if there is a number which is represented in signed magnitude representation, you take 1's complement of that and again you take the 1's complement, you get the same number. Okay, let's solve a problem. Why did I take this problem? Now this number is given. N corresponds to the 1's complement of what? So basically this number is 1's complement of something. So I need to find which decimal number is that. So what I will do, this number is given. Certainly whether it is 1's complement or 2's complement or signed magnitude representation, always this will be the sign bit. So 1 will be as it is, rest all will be complemented. So now what did I do? I took 1's complement. Here I took 1's complement. 1's complement of n. So this n was already a 1's complement of some number. Now again 1's complement I have taken. That means I am getting the same number now. Are you getting this point? This n was 1's complement of some number. Then again 1's complement I took. That means I am getting the same number. So what is this number? Basically this is the sign, and 1, 2, 4, 8. So this number is minus 11 only. Minus 11 only. Okay. Minus 11. You can write minus 11, 10. So this is the decimal output. You can say this is the decimal output. So basically if the question was take 1's complement of minus 11, what would be your answer? That, sir, first I will write its sign magnitude, take 1's complement. So first I will write SMR, that would be, minus will be as it is. And what about 11? 11 can be denoted as 1, 0, 1, 1. Right? Now I need to take 1's complement. So what I will do, sign magnitude, sign bit as it is, 0, 1, 0, 0. So this I would get, and this is your n only. So n correspond to the 1's complement of what? So n correspond to the 1's complement of minus 11. So this much you don't need to think. If they are asking whose 1's complement is that, just take the 1's complement again, you will get the same number. Okay, so that's why I took this question. So this is the answer. This is the answer. So if someone is asking you whose 1's complement is that, you can simply take the 1's complement back. Now the following numbers are 1's complement of some number. Which of these numbers are there? So this is 1's complement of what? This bit will denote? Sign bit. This is sign bit. So this is a plus number, 0. So this is 1's complement of plus 0, because SMR for positive numbers, SMR is equals to 1's complement is equals to 2's complement, right? Here positive 1, here positive 2, here positive 3. Now this number is 1's complement of something. This number is 1's complement of something. Of which number it is, that I don't know. So how will I find it? 1 as it is, take complement of 0, 0, it would be 1, 1. So 1 will represent minus sign, 1, 1 would be 3. If the question was take 1's complement of minus 3, how would you do it? You will write 1, and now 1 for this negative sign, and 3, magnitude of 3 will be 1, 1. Then 1 as it is, and complement of these two, 1, 0, 0. That's the answer. So what did I do? Without thinking all these things, what did I do? I simply took 1's complement of this number. So that is minus 3. Now I will take 1's complement of this number, sign bit as it is, 1, 0. So I will write down 1 is minus sign and 1, 0 is 2. So this is minus 2. What about this one? 1 as it is, 0, 1. So this is sign bit minus 1. 1 as it is, 0, 0. This is sign bit minus 0. So here this is your minus 0 and this is your plus 0. So minus 0 and plus 0 both are different things here. Minus 0 and plus 0 both are different things. Okay. So what is the range again? In 3 bits you are again denoting the same number, so the range again is same. What is that range? Minus 2 to the power n minus 1 minus 1 2 plus 2 to the power n minus 1 minus 1. Same as SMR. So range here is same. Here also for 1's complement as well. For 1's complement representation as well, minus 0 is not equals to plus 0. Same was there in sign magnitude representation as well. If we remember, this was the scene. Minus 2 to the power n minus 1 2 plus 2 to the power n minus 1 minus 1. And here also this was the scene. Okay. So same thing is happening here. So this is the range. So these ranges are important. It can be asked. Okay. Let's see 2's complement now, which is also very, very important. So again, what is the method? Check if the number is positive or negative. If the number is positive, then answer would be same. If the number is negative, then please turn over. So before that, if the number is positive, what will be the 2's complement representation of this 21? That would be, for plus sign, 0 1 0 1 0 1, 21 as it is. So for a positive number, signed magnitude representation, 1's complement representation and 2's complement representation all are same. But for negative number, what you will do? So two method I have written. The same thing goes till here. Till here the same thing goes. Write SMR, keep the sign as it is, keep the sign bit as it is, write 1's complement. After that you add 1 in that. Or what you can do? Write SMR, keep the sign as it is, start writing the bits from the right end as it is until you encounter the first one. Take complement of each bit afterwards. You are not understanding it here. Let's take an example, you will understand it. So now you need to denote minus 21 in 2's complement representation. So what you will do? First you will write down sign magnitude representation. What that would be? Minus sign, 1 would come. 21 would be 1 0 1 0 1. Okay. Let's take 1's complement. What would be 1's complement? So this as it is, 0 1 0 1 0. Now what did I tell you? After 1's complement you need to add 1. If you add 1, this answer will give you 2's complement. This answer will give you 2's complement. So 1 plus 0 is 1 1 0 1 0 1. So that's the answer, which is my 2's complement representation. But every time I will not do this thing. So what I will do? First I will write sign magnitude representation. This is the method 1, I can say. Now this is method 2. So first I will write sign magnitude representation, which is 1 1 0 1 0 1. I will keep this bit as it is. This I am writing 2's complement. Directly I am writing now 2's complement representation. Now I will start from the right, from here. I will start from the right end. I will write 1 here. Immediately I got 1. Immediately I got 1. Right? I started from here and I got 1. So after that I will complement all the bits. 1 0 1 0. So I am getting the same answer. Let's just say if my sign magnitude representation is this. If my, there is the second example. Okay. Let's take this example. So my sign magnitude representation will be what? In minus 14. That is 1. And how will you denote 14? 8421. 8421 will be 1 1 1 0. 8421. Yeah, fine. So SMR you have taken. Now directly if I am writing 2's complement representation, or let's write 1's complement representation as well, because we should at least solve two problems with the same method. So 1 will be as it is, complement of each, and then add 1. This will give you 2's complement representation. So 0 1 0 1 1. That's the answer, right? Oh, sorry, why 1? This would be 0 only. 0 1 0 0 1. So this would be the answer, right? Now method 2. First I will write SMR. That is 1 1 1 1 0. Then I directly can write 2's complement representation. How will I write? Sign bit as it is. I will start from here. I am getting 0. Okay. I will wait till I get 1. I am getting 1 now. Yeah, I have got 1. Now after that I will complement all the bits. So 1 will be 0, 1 will be 0. Here I did the same thing. I started from here. I got 1 here only. So I will complement all the bits. 0 will be 1, 1 will be 0, 0 will be 1, 1 will be 0. Started from here. I got 0, stayed here. 1, just as I get 1, I will complement all the bits. But sign bit will remain there as it is. Because this shows the sign. This shows the sign. So there you go. This is the way you write 2's complement. Are you getting this point or not? Okay, you are getting the same answer here. You can check. Let's see more problems. Minus 21 in 2's complement representation in 8 bit. So what is the first task? First write in sign magnitude representation in 8 bits. So minus 21 in 8 bits. So 1 would be the sign bit and 21 in 8 bits, that would be 0 0 0 1 0 1 0 1 1 2 4 8 1 2 4 8 16, right? 21. So yeah, that's the answer. Now I need to take 2's complement representation. So this bit as it is, I will start from here. Just as I started, I got 1. So complement of all these numbers I will take. That's it. I started from here. Just as I got 1, complement of each number I am taking. 0 will be 1, 0 will be 1, 0 will be 1, 1 will be 0. Again there is a note. The same thing is there, that 2's complement of 2's complement of 2's complement, sorry, 2's complement of 2's complement of some number, but the number is in sign magnitude representation, you will get the same number. So this note is also there. Okay, let's take more examples. We can take more example of this minus 14 in 2's complement representation in 8 bits. This example we can take. So what will be the sign magnitude representation? That would be 1 would be there. Plus for plus 14 it would be the same. So for plus example we are not taking, only the negative ones example we are taking. So 1 would be there, and these would be 14 can be written in 3 bits, 4 bits only. So 4 zeros will be there, and how will the 14 be written? So 8 4 no 14, yeah. So 1 1 0 1 1 1 0, sorry, this would be 14. And if I need to write 2's complement representation, so 1 sign bit I am keeping as it is. I will start from here. I did not get 1 till here I got 1. So after that I will take complement of each number. After that I will take complement of each number. That's it. If I need to write 1's complement representation, what I will do? I will see the sign bit only. This sign bit will be there. Now all will be complemented. So first target is to write sign magnitude representation. So all will be complemented now. That's it. Okay. So in that manner we will proceed. Now 1 1 0 0 1 1 0 0 1 and 1 1 1 0 0 1 correspond to 2's complement of what? So all three numbers are there. 2's complement of what? So let's take the first one. 1 1 0 0 1. If I take, so if this number is 2's complement of some number, that means this will denote the sign only. Look, this number is 2's complement of some number. That means if it is a 2's complement, that means certainly this is denoting a sign. So this number is certainly negative. This number is certainly negative. So what I am going to do, I am going to take 2's complement of this number. 2's complement of this number. So this number, this sign will come as it is. I will start from here. I will start from here. Just as I got 1, just as I got 1, I will take the complements, right? So this will denote the sign, which is minus, and what this will denote? This will denote the magnitude, which is 7. So answer is minus 7. Are you getting this point? Let's see again one more problem. This property I am using, 2's complement of x. 2's complement of this number is already a 2's complement. Now I am again taking 2's complement of x, but x should be in sign magnitude. So I will get x in sign magnitude. So this x I got, but in sign magnitude. That means this will show the 1 here. So that is the negative. Now this is the question 1 0 0 1. So I will take the 2's complement. How will I take 2's complement? So 1 will be, the sign bit will be as it is. Now this 1 will come here, and then Since I got 1, so I will take the complement of 0, complement of 0. So this 1 will denote negative sign and this will denote 7, right? So answer is minus 7. For this one as well, answer is minus 7. We will notice a very interesting thing here. 1 1 1 0 0 1. What I need to do? I need to take 2's complement, right? The sign bit as it is. This 1 comes here, 1 as it is. Just as I got 1, this will be 1, this will be 1, and these 2 will be complemented. So this bit will represent the sign, so minus, and this will represent the magnitude, so minus 7. All are minus 7. If the question had been write down the 2's complement of minus 7 in 5 bits, this would be the answer. Write down the 2's complement of minus 7 in 4 bits, this would be the answer. Write down the 2's complement of minus 7 in 6 bits, this would be the answer, right? Okay, all are the same number. Let's take some revision example, so that till now whatever that we that we have studied, that will be your revision here. Till now whatever that we have studied. Represent plus 18 in sign magnitude representation. 18, 1 2 4 8 16, that will be 1 0 0 0 1, sorry, 1 0 0 1 0. So first positive sign is there, so 0 will come, then 1 0 0 1 0, 16 plus 2 18. For positive number, all these are same, 0 1 0 0 1 0, 0 1 0 0 1 0. Positive number but in 8 bits, so basically this will be 0, and rest all bits, basically you need to denote 18 in 7 bits, 18 in 7 bits. So 18 can be denoted in 5 bits only, so 2 more 0 will come, and all these are same only. For positive number, all these are same only, so you will not do anything. For positive number, all these are same, but here minus 18, so this one will show the sign, and answer will be 1 0 0 1 0. For 1's complement, the sign will be as it is, or start from here, sorry, sign will be as it is and complement of each, 0 1 1 0 1. For 2's complement, sign bit will as it is but start from here, this is 0, this is what, 1. After 1 you will complement everything, 0. That's it. What about this one? Minus 18 in 8 bits. So first one will denote the sign. Now 18 can be denoted in 4 bits only, sorry, in 5 bits only. So 2 more bits will come, that would be 0, because this will denote the sign, rest all will be the magnitude, 0 0 1 0 0 1 0. So sign will come as it is, rest all will be complemented, right? Rest all will be complemented. 2's complement, this sign will as it is, you will start from the back, this is 0, this is 1, after that you need to take the complements, 0 1 1. So first I will look at SMR, then I can find 1's complement. I will look at SMR, I can find 2's complement. I will look at SMR, I can find 1's complement. I will look at SMR, I can find 2's complement as well. Okay, you just need to look at the SMR and you will find 2's complement and 1's complement both. Now a very interesting thing you are noticing here. Notice the 1's complement in 7 bits, in this 6 bits, and notice 1's complement in 7 bits. Do you notice something? Let me show it. For 1's complement of minus 18 in 6 bit, what was the answer? 1 0 1 1 0 1 1 0 1. For 8 bits, what is the answer? So this sign bit is being repeated only, no? Say yes or no. This sign bit is only being repeated, right? A very interesting thing is about to come. Okay, you will see a proof of very interesting thing, very interesting, like no one will teach you ever. Okay, so that much interesting thing is there. Now in plus 18, this was the sign bit, so that is being repeated. This was the sign bit, this is being repeated. Minus 18 is 2's complement, so this was the sign bit which is being repeated. This was the sign bit which is being repeated, right? So a lot of sign bits are there. Let's just say 1 1 0 1 1 1 1. So these only 1 is the sign bit which is being repeated. For 1's and 2's complement, this is the sign bit, 1 is the sign bit. Now this is being repeated 1 times, Here this is being repeated two times more basically. Here this is being repeated 3 times more. So what you can do, you can eradicate these, right? Or if someone is asking you, like I have denoted this number in 6 bits. If someone is asking you, denote this number in 12 bits, write down the ones complement of minus 18 in 12 bits. So what you will do, you can write it down in 6 bits very quickly, and then rest you need to add ones. That's it. Just keep on adding ones, nothing else. So 12 bits, so 3, 3, 6. Yeah, that's it. This is answer in 12 bits. In 8 bits, if they were asking, so 1, 0, 1, 1, 0 I have written. In 8 bits, 2 more. Basically, I can cut these two. There is no use of that. Only the sign bit is being repeated. So this thing we have noticed, right? In 2's complement and in 1's complement. This is not true for sign magnitude representation. Only for 1's complement and for 2's complement. Okay, the sign is being repeated. So all these are equal only, right? So 2's complement of x is 1, 0, 1, 1, 0, 0, 1, 1. What will be 2's complement of x in 12 bits? So what are these bits? 3, 3, 6, 7, 8, 9, 10, 11, 12. Rest all number will be the same. 1, 0, 1, 1, 1, 0, 1, 1. So this is the sign bit which is being repeated. So I repeated it for 4 times. 1's complement of x is this. So what will be 1's complement in 12 bits? So these are 3, 3, 6, 7, 8 bits are there. So 8 bits are there. So 1, 2, 3, 4. 4 bits I have to use. 1, 0, 1, 0, 1, 1, 0, 1. If this one number was 0, 0, 1, 0, 0, 1, 1, 1, 0, then what would be the answer? So 3, 3, 6, 3, 3, 9. 9 bits are already there. I have to use 3 more bits. So these will only the sign bit I will use. So 0, 0, 0, 3 more, and then the same number. So for 0 as well it is applicable. Okay, for 0 as well it is applicable. The same sign bit will be there. Same sign bit will be copied. Because for 0 the thing is, all representation are same only. 1's complement, 2's complement and SMR. All representation are same. So we need to think of negative ones. So for 0 all representation are same, so that would be very easy. You are writing it for 1 in 7 bits, 10 bits, 12 bits, 13 bits, that would be very easy. But if this becomes long, then you would take complements again and again. So here we are thinking that here we get to know that the sign bit is being repeated. Now 1's complement of x is this, which the number x is in decimal. So what we can do, what we can see here, that 1, 1, 1, 1, 1, these are the sign bits only, no? 1's complement of x is this, so these are the sign bits. So that means 1's complement representation is 1, 0, 1, 1, 0, 1, right? Do you agree to this point? 1, 1, 1 are being repeated. I can cut it. 1, 0, 1, 1, 0, 1 in 1's complement is same as this number, right? I told you here, this is being repeated, so I can cut it. If I cut it here, 1, 0, 1, 1, 0, 1 I am getting. Now if I take 1's complement, so how it, again I will take 1's complement to find the number. I told you this 1's complement of x is this. So this number is 1's complement of something. So if I again take 1's complement, I will get to that number. So I am again taking the 1's complement. So sign bit as it is. This will be 0, 1, 0, 0, 1. So negative sign is there, minus 1, 2, 4, 8, 16. So that would be minus 20. 1, 2, 4, 8, 16. So minus 18, sorry. 16, minus 18. Okay, is that the same example we have took? 1, 0, 1, 1, 0, 1. 1, 0, 1, 1, 0, 1. Okay, the same example we are taking. So basically this is gone. So this answer is minus 18. So this is 1's complement representation of minus 18. Now let's see a very interesting thing. So there is a note which you have to remember. For 0 there is only one representation in 2's complement. In 2's complement, for 0 only there is one representation. It will be the same as 2's complement of plus 0. That means what is the sign magnitude representation of plus 0? So plus 0 will be the sign. Plus sign, if there is plus sign, then 0 will come. And how will you represent 0 in binary? 0 only. Same will be 2's complement and 1's complement, because this is a positive number. For negative number, this for sign 1 will come and 0 will be denoted as 0. Now 1's complement of minus 0. 1's complement of minus 0. So first I will denote it in sign magnitude representation, then 1 as it is, 1 as it is, and what 1 is the sign, that would be as it is, and I will take complement of 0, that would be 1. Are you getting this point? Sign magnitude representation, if I am saying that this is sign magnitude representation, so how will you take 1's complement? So this 1 as it is and complement of all these, right? So this I am saying 1 as it is, complement of 0, that is 1 only. But minus 0, 2's complement of minus 0. So sign magnitude representation is 1 0, right? Sign magnitude representation is 1 0. If I need to take 2's complement, let's just say I am taking 2's complement with the method that I have taught you. So this sign bit as it is, you start from here. What you are getting directly 0. So your answer is again 1 0. So that means you are saying that both are same. But that's not true. Okay. So this thing you need to remember that zeros are same. That means this would be 0 0 only. So 2's complement representation of minus 0 will be 0 0. So that you need to remember. Okay. So minus 0 is equals to 0 for 2's complement representation. But for 1's complement representation, it is not certainly 0. For SMR and 1's complement representation, it is certainly not equal, right? This we have already this. So this is the point that we need to remember. Okay, let's see more interesting thing. So this is the special case in 2's complement which we generally mug up, but here we will see the proof why it is happening. So for minus 4, this number is minus 4. You need to represent it in sign magnitude representation. So how will you represent? Minus sign is there, and 4 in 2 bits. What that would be? 4 will be denoted in 3 bits. So this is the sign magnitude representation. Minus sign and then 4. What will be 1's complement? This as it is, complement of rest. What will be 2's complement? This as it is. Start from here. If I start from back side, so 0 0 until I get 1. Here I am getting 1. After that there is no number. So this is the answer. So this is the 2's complement representation of minus 4 in decimal. So this is the 2's complement representation of minus 4. This 1 is being repeated twice, right? What did I tell you? In 2's complement and 1's complement, I can cut these ones if they are being repeated more. So here I can only keep 1 1. This I told you, right? So I can cut this 1 now. I can cut this 1. So if I cut this 1, what will be my answer? 100. So 2's complement of minus 4 is equals to 100 you are getting. Yes or no? In 3 bits only you denoted it. For these you require 4 bits. 4 bits are the minimum. Minimum 4 bits you require. Here also 4 bits you require. You solved with the same process. Let's start from here. 0 0 1 as it is. You solve with the same process. Then you got to know you are getting it in 4 bits. Then but these 2 bits are same. So you can cut it. You get 4. So this is the answer in 3 bits. We will see a very interesting result now. Minus 8. Sign magnitude representation. Negative sign. How will you denote 8? 8 will be 1 0 0 0 1 2 4 8. This will be 8, right? What will be 1's complement? 1 0 1 1 1. This will be 1's complement. What will be 2's complement? Sign bit as it is, start from here. 0 0 0 and 1 as it is. So what you can do? You can cut this one. So 1 0 0 0. What is this? This is in 4 bits only. What about these? This is what our, how many bits are there? 5 bits. And this is 5 bits. So in minimum 4 bits you can represent 8 minus 8. So 2's complement representation of minus 8 is 1 0 0 0. What is 8 to the power 3? What is 4 to the power 2? So what do you understand here? So this is the special case that if this is 2's complement representation, 2's complement representation. So in 2's complement representation, if you are getting 1 0 0 or 1 0 0 0 or 1 0 0 0 0, these kind of numbers, that means you just need to count the number of zeros, then put the negative sign minus 2 to the power n. That would be the answer. That means it would be the 2's complement of minus 32. Why is that so? I have proved it here. Right? We took the example. We are going from here to here, not from here to here. In all the notes you will find that this is a fact. Everyone will tell that it is a fact. But here we proved it. Where we are getting this from. So if this is the 2's complement representation, so basically this is the 2's complement representation. So number of zeros are 2, then the decimal number will be minus 2 to the power 2. That means minus 4. Here numbers of zeros are 3, that means decimal number will be minus 2 to the power 3, 8. You can go from here as well. Like if someone is saying that write down the minus 64, you see minus 64. Write down the 2's complement of this number. So you forget that this is a 2's power something. You forget this point. You forget this special property. You have forgotten this. Then how will you solve it? How will you solve it? You will say that, sir, first I will write it in sign magnitude form. So 64 I need to denote. So 1 will be for the sign, and 64 will be 1, 2, 4, 8, 16, 32, 64. So 7. 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 4, 8, 16, 32, 64. Yeah. So this is my sign magnitude representation. And then I will write 2's complement. So what will be the 2's complement? 1 as it is. And from here 0 I will count. 3, 0, 4, 5, 6, and this one as it is. Now 2 ones are being repeated. I will cut it. So that would be my answer. 1, 0, 0, 0, 0, 0, 0. 3, 3, 6. 3, 3, 6. Right? So this is basically answer minus 2 to the power 6. So what is 64? That is minus 2 to the power 6 only, no? So 6 0 you can add. So directly I can come. So basically from here to here it will not be that tough. But in the examination, if this is coming, then you should directly click to me. Okay, 6 zeros are there. So it is the 2's complement of minus 32. That's it. Okay. Let's see the next question. In the next question, what is there? This number n is there. X is signed magnitude representation of n. You need to find the value of x. It is signed magnitude representation. Signed magnitude representation. That means first will show negative. 1 will show negative, and this will show the magnitude. What is that? Minus 0. What will be the answer of B? N is 1 0 0 0 0, which is 1's complement of something. So what you can do? You can take again 1's complement. So 1 will be 1 as it is, and 1's complement of this will be 1 1 1 1. So what you are getting? This 1 will be for minus sign, and what is 1 1 1 1? That is minus 15. So y value is minus 15. This is your x value. X value is minus 0. X is a signed magnitude representation of n. So in sign magnitude representation, you don't need to do anything. First one will be your sign bit minus 0 0 0 will be 0. In 1's complement representation, you need to take 1's complement. Again, you need to take 1's complement. So 1 as it is, I again taken the 1's complement. So this is showing me the sign minus, and this will be 15. What about the third one? 1 0 0 0 0. What I will do? If this is 2's complement representation, if I again go on taking the 2's complement, I will get the same number. If I take 2's complement of this, what I will do? I will get the same number. 1 I will keep as it is. I will start from here. I will get the same number. I am not going anywhere now. I will say this is minus 0 because this sign is 1, and I will say that this is 0, so I will say minus 0, which is wrong because I told you one thing, the plus 0 and minus 0 is same in 2's complement. So this cannot happen. That means this is the special case. So here there are how many zeros? 4 zeros. This is minus 2 to the power 4. So answer is minus 16. This is the case of minus 16. That means this is 2's complement representation of minus 16. This is the value of Z. minus 16, 10 you can write. Here also 0, 10 you can write. So this is the 2's complement representation of minus 16. Okay. Now the following numbers are 2's complement representation of some number. You need to find those numbers. So for positive numbers it would be all same. 100 it would be minus 2 to the power 2, that would be minus 4, right? Are you getting this point? 100 will be minus 2 to the power 2 minus 4. What about this? Again take 2's complement. So 1 as it is, this 1 as it is, and this 0 will be 1. Basically 1 as it is, sign as it is. 101, I need to take 2's complement of that, because these are the 2's complement of some number. So I need to find 2's complement of this number again to get the same number. This we have done like 15 times in this lecture, right? So 1 as it is, this 1 will be copied. Since I got 1, this will be 1. I will take the complement. So I will start from 1 as it is. I will start from here. I got 1 here only. I will start 1 as it is. I will start from here. Since I got 1, I will take the complement. Okay. These are the 2's complement. So basically minus sign minus 3, minus sign 2, and minus sign 1. So what is the range? For 3 bits, what range we are getting? Here this negative sign is increased, minus 4 to 3, because minus 0 is equals to here plus 0. For 0 there is only one representation. So both are same here. Okay, it could be equals to minus 0 as well. Both are same here. That's why the range has increased, minus 4 to 3. So what would be the range here? Minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. Right? For 1's complement, what was the range? Minus 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. For sign magnitude representation, what was the range? Same range. Here one digit has increased in negative direction. So that's why minus 2 to the power n minus 1 minus 1 plus 1. So it would be minus 2 to the power n minus 1 to plus 2 to the power n minus 1. Let's write it in a table. So if there are 3 bits, 3 bits means total 8 possible combination. 2 will be 0. So divided by 2, 6 by 2. Basically we will start from minus 3 to plus 3. So it will go from minus 3 to plus 3. If there are 4 bits, total combination 16. 2 will be 0 divided by 2. So 8 by 2 we are getting 4. 8 by 2 we are getting, sorry, 14 by 2, 7. So minus 7 to plus 7. What about n? Minus 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. 1's complement representation same. Okay. The range is same, right? The range is same. Okay, sorry. 2 to the power n minus 1 minus 1, 2 to the power n minus 1 minus 1, minus 2 plus. And for here, minus 4 to plus 3, it would be minus 8 to plus 7. So this would be minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. There you go. Okay. So these formulas you need to keep in mind. You don't need to mug it up. If concept is clear, you will keep in mind. So this was the representation of sign number. We saw SMR, 1's complement and 2's complement. I hope you are not confused and everything is crystal clear. In the next lecture, we are going to see the arithmetic operation. Just like arithmetic operation we have seen in the codes, the same kind of arithmetic operation we will see in 1's complement and 2's complement as well. And there will be a very important concept, that will be the concept of overflow. So next video will be our last video of this chapter, and that would be very, very important. Okay then? Yeah. So let's meet you in the next video. Hi everyone. So in this video, we are going to start studying about complement arithmetic. So like the previous video, in this video as well, I want your full attention. Just give me your full attention for next 1 hour and you will be able to understand this topic. Otherwise, this topic becomes very complex. You can ask a lot of students, they will say that this topic is pretty complex. but you give your full concentration and you would be able to solve all the problems just for next 1 hour. Okay, so we have done BCD calculation, right? We have done XS3 calculation. So there was a certain method. So here also there will be a certain method. So ones complement arithmetic you need to do. So what you need to do? First you need to represent the number in ones complement form. First you need to represent it in SMR, then you need to represent it in ones complement form. Then just perform the binary addition. Same kind of thing we did in our previous calculation as well. In BCD addition, what we did? We represented the number in BCD and then we did the binary addition. Same thing we are doing here. Now, there are two things. If carry is generated, if carry is not generated. If carry is not generated, then it is fine. If carry is generated, then you will add that carry. That's it. Add that carry to the result. Okay. And if you add that carry to the result, answer will be in ones complement form. Because why answer will be in ones complement form? In both of the cases, answer will be in ones complement form only because you are converting the number in ones complement and then you are performing the addition. So answer will be in ones complement form only. No, are you getting this point? When you were doing the BCD calculation, answer was in BCD only. When we were doing XS3 calculation, answer was in XS3 calculation only. Answer was in XS3 numbers only. So similarly, if you are doing the ones complement calculation, the answer will be in ones complement only. Okay. Now these points you might not be able to understand as of now, but let me just spend some time, then we will come back to these points. Okay, we will come back, we will spend some time here, then we will come back. So tell me this point, this you see this line, if answer is positive and if answer is positive, you perform the addition, your answer is positive. If answer is positive, then can I say that my answer is in, if my answer is in ones complement form, then can I say that this answer is in normal form only? If answer is positive, if my answer is coming positive, that means my ones complement form, sign magnitude representation or normal form, all will be same, right? How you represent 13? Not let's take the example of 7. How you represent 7? 1 1 1. How you represent plus 7 in sign magnitude representation? 0 1 1. How you represent plus 7 in ones complement representation? 0 1 1 only, right? For positive number all are same. That means if my answer is coming positive, that means I can say that my answer is in normal form, or you can say it is in ones complement form, or you can say it is in sign magnitude representation, or you can say that it is in twos complement form, right? You can say anything if your answer is coming positive. And generally, if your carry is generated, then answer will be positive, and if your carry is not generated, then answer will be negative. But you need to make sure that you are performing the addition using minimum number of bits. Now what is the meaning of minimum number of bits? That we will see through the examples. So if you are performing the operation using minimum number of bits, then this thing is certain. Which thing is certain? That if carry is not generated, then answer will be negative, and if carry is generated, then answer is positive. How will you remember it? If carry is generated, something is generated, that means you have done something. If something is generated, that means you have done something positive, so answer will be positive. If nothing is generated, that means you have done nothing in your life. If you have done nothing, that means you are negative now, so answer will be negative. This is how you can remember it. Okay, although it will come to you on its own when you perform the calculation. So for as of now, you just need to take care of this thing, that first you need to represent in ones complement form, then you need to perform the binary addition, and then if carry is generated, you just need to add that up. That's it. You can forget about these things. Okay, just forget about these things, and this thing also you need to take care. If answer is coming positive, then I can say that it is in normal form, or it is in sign magnitude representation, or it is in ones complement representation. Let's perform this addition. So we know 26 minus 14 will be 12, that we know, but we need to perform it using ones complement representation. So can I write it in this manner, that it is plus 26 plus minus 14? Say yes or no, and the answer will be coming there. I can write it in this manner, right? Plus 26 plus minus 14. So what will be the sign magnitude representation of 26? Sign magnitude representation of, because you need to write ones complement representation. So first you will write sign magnitude representation, right? You need to write ones complement representation. So first you will write the sign magnitude representation. What that would be? 26, 12, 13, 0, 2, 6, 1, 2, 3, 0, 2, 1, 1. So 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. This 0 bit is for sign, and I can write 1, 2, 4, 8, 16, 32. So 2, yeah, 26. Yeah, that is fine. Just a second, let me turn on the charger. Okay, I will come. Just one sec. Yeah. So till then you can write down the ones complement representation. So it would be the same only. Ones complement representation of plus 26 would be the same. It would be 0 1 1 0 1 0 because it is a positive number. What about sign magnitude representation of 14? Minus 14. That would be first one is the sign bit. What about 14? 1 2 4 8. You can represent it like this, right? But this number is in 6 bits, right? This number is in 6 bits. So here also I will take 6 bits only. So 1 0 I will put here and 1 1 1 0. Why I put this 0? Because these were total 5 bits, so and 1 is sign bit. 5 bit magnitude bit and sign bit. So here also I would need the same bit. So because I need to perform the addition, no? That's why. So equal bits I will keep. Now what will be ones complement representation? Ones complement representation of minus 14 would be sign bit as it is, rest all inverted. Now you have ones complement of 26. You have ones complement of 26. That is this. And you have ones complement of minus 14. Ones complement of minus 14. What you need to do? You need to perform the addition here now. Because the sign is of addition. Just perform the addition. If you perform the addition, what you will get? 1 1 0 1 0 0 1. Just binary addition I am doing. Now this one will go here because if carry is generated, then 1 will be added. Now add it up. 1 plus 1 is 0 1 0 1 1 0 0. That's it. This is the final answer. So what is this? You can check it directly. It is plus 12. And what did I tell here? If carry is generated, answer will be positive. Carry is generated, answer will be positive. You can see. If carry was generated here, if carry is generated, then answer is positive. So how can you remember it? If carry is generated, that means I have done something in my life. Carry is generated, I am generating something. That means if I am doing something, that means answer will be positive. One thing more, this thing will work only if we are using the minimum number of bits. So here minimum number of bits, these much bits were required, right? To represent 26, these much bits were required. Although here we used one extra bit, this was not required, still we used one extra bit. This is extra bit only, no? I can cut it as well. But these are the minimum number of bits. Like here you required 6 bits and here you required, in this one you required 6 and in this one you required 5 only, but you represented it in 6 bits only. Why you represented it in 6 bits? Because you need to perform the addition. If you are represented it in 5 bits as well, then also then you would not be able to perform the addition correctly, no? Like all the bits should be the same, number of bits should be the same. But what if, so maximum of these are 6. So 6 bits are required. But what if I had represented this number in 7 bits? Then this carry, if I had represented this number in 7 bit, then this thing would not work. That carry is generated or carry is not generated. We will see those examples. Okay, we will see those examples when we will represent the numbers in more bits, and this concept will not work there. So this concept will work only if you are using the minimum number of bits. Then if carry is generated, your answer will be positive. If carry is not generated, then answer will be negative, and you will be able to remember that. So on a top level, I hope you are understanding what all you need to remember and how you need to perform the addition. So try doing it on your own. So how you can write this one? Plus 14 plus minus 26, right? This is what you need to do and you will get your answer. So what is one's complement representation of plus 14? Because directly we can write, since this is a positive number, so I will directly write it. So plus 14 that would be 0 0 1 1 1 0. Why I am writing two zeros? Because I know for 26 I would require 6 bits. So that's why I am representing it in 6 bits only. Now what will be the sign magnitude representation of minus 26? What that would be? Sign magnitude representation of minus 26. So first bit is 1, rest all are 1 1 0 1 0. What will be the ones complement representation of minus 26? So sign bit as it is, rest all complemented. Okay, so what we need to do? Plus 14 plus minus 26. We need to add these two, plus 14 and plus minus 26, that is 1 0 0 1 0 1. अरे यार कितने नोटिफिकेशन आएंगे, वेट अ सेकेंड. So just add them up. 1 1 0 0 1 1. Carry is generated? No. If carry is not generated, that means, what does that mean? Yeah, here one more thing I forgot to tell. Here this answer is in one's complement form only, but one's complement form is equals to sign magnitude representation because the answer is positive. Here this answer is coming in one's complement form only. This answer is in one's complement form, but the sign bit you can see that this answer is negative. So this answer is in one's complement form. This is your answer, but you need to check whose one's complement is that. You need to check whose one's complement. If you convert this into directly the number, so it would be 1 2 4 8 16. So 16 plus 3 19. You are getting minus 19. So you will say that the answer is wrong. Answer will be minus 12. No, this number is represented in one's complement form of your answer. One's complement representation of your answer. So if they are asking perform the addition and write down the final answer in one's complement form, then this would be the correct answer. And if they are asking write down the final answer in sign magnitude representation, you got some answer, you got this answer in one's complement form. Now if they are asking that you need to write down the final answer in sign magnitude representation, then what you will do? I told you this thing. If I need to get the sign magnitude representation again, then what I will do? I will again take one's complement. So again taking the one's complement. So I will again take one's complement. Again take one's complement. So if I am again taking one's complement, so 1 will be there as it is, 0 1 1 0 0. So this answer is in sign magnitude representation of your answer. Sign magnitude representation of your answer. And you can check it. What will be the sign? Since 1 is there, so minus sign is there. 1 2 4 8 minus 12. That's it. The answer is correct. So I will again repeat all the things. Within 2 examples, we are understanding everything. So first we wrote with respect to sign and we performed addition here. So this is the addition. Okay. Now plus number is there. So sign magnitude and one's complement are same. Minus 14 is there. So I represented it in one's complement. Then I performed the addition. I got a carry. I added it up. Then this is the final answer I am getting. Now this final answer is in one's complement form only because we have performed the one's complement application. One's complement we have performed the one's complement addition. So final answer is in one's complement representation only. But since this answer is positive, then one's complement representation will be equals to the sign magnitude representation. That means both are same. Or you can say normal form as well. You can call it normal form as well. That in normal form as well you will get this answer only 1 1 0 0. How you will represent 12 number 12 in binary 1 1 0 0 only. So if your answer is being positive, then you can say that my answer is in one's complement form, or it is in sign magnitude representation, or it is in normal form. So answer is plus 12. So if you are performing a one's complement arithmetic, then your answer will be in one's complement only. So here I perform the same thing. I got the answer, and here this answer is in one's complement representation. So if they are asking me, you need to write down the final answer in one's complement representation, then this would be the answer. But if they are asking me, you need to write down the final answer in sign magnitude representation, then this would be the answer. Okay. So if this they are asking, then I would write this answer. Sign magnitude representation and one's complement representation. And another thing we got to know here is that if carry is generated, then my final answer is positive. If carry is generated, that means if I am generating something, I have done something positive, so my final answer is positive. And if there is no carry generated, then my final answer is negative. So this answer is coming out to be negative. This answer is coming out to be negative, which is minus 12. So this much thing is there in one's complement representation. And if I have mixed all of these things, then you would be confused. But here every single thing is clear. Every chart is clear. Okay, first this chart is there, how we are performing. Then this chart is also there. So now everything we have broken down and things are clear. Now we need to study 2's complement arithmetic, and it is the same thing. We are doing the same thing, exactly the same thing. We will represent the number in 2's complement. Okay, we will represent the number in 2's complement. We will perform the binary addition. If carry is not generated, we will not do anything. If carry is generated, we will ignore the carry. Only difference is if carry is generated, you will ignore the carry, and result will certainly be in 2's complement representation because you are performing the 2's complement arithmetic. So in one's complement representation, we add the carry. In 2's complement representation, we ignore the carry. So how will you remember it? Like people get confused, sir. Okay, in one's complement we need to ignore it or we need to add it. So how will you remember it? So what will be your carry? Carry will be 1, right? Your carry will be 1. If you are doing one's complement arithmetic, you are doing one's complement arithmetic and your carry is 1. Both are similar, no? 1 and 1. If both are similar, that means they will fight. they will fight means you need to perform the addition. Here it is. You are doing 1's complement representation and you are getting carry 1. Both are similar, they will fight and you need to add 1. What about 2's complement representation? Your carry is 1 and you are performing 2's complement representation. So 2 guy is greater. 1 came to fight, but 2 is greater. 2 is greater than 1. So he will say, I will ignore you. If greater guy is there, he will ignore. If equal guys are there, they will fight. If you are greater than someone and he is coming to fight you, then what you will say? Just stay there, kid. Okay, if some 4-year-old guy coming to fight with you, then what you will say him? Just stay there, kid, I will ignore you. So similarly, 2's complement will ignore the carry and 1 will fight. अब अगर कोई 22 साल का आएगा वो बोलेगा लड़ते हैं तो फिर लड़ोगे आप. हाँ. Okay, so this is just a way to remember it. So let's start. The same things are written. If answer is positive, then we can say it is 1's complement representation. Sorry, here I should have written 2's complement representation, or you can say it will be equals to 1's complement representation as well. So you can say it would be equals to 2's complement representation or sign magnitude representation or in normal form, right? And if you perform the addition using minimum number of bits, then if carry is not generated, then answer would be negative, and if carry is generated, that means you have done something positive in your life, the answer will be positive. So that's the same thing. The slide is completely same. We just copied the slide, nothing else. So only difference is here is this. This is the only difference. Otherwise, all the things are same. Every single thing is same. Just only difference is this. You need to ignore the carry here, and here you are adding the carry. That's the only difference between 1's complement arithmetic and 2's complement arithmetic. So let's take the same example and solve it. So what will be the sign magnitude representation? So how I can represent it? So I need to perform 2's complement arithmetic. So how will I represent it? Plus 26 plus minus 14. So what you will get? So plus 26 in sign magnitude representation, it would be the same in 2's complement representation as well. So what would be 26? Here we have written, right? 0 1 1 0 1 0 110 10 0 1 1 0 1 0. What it would be? Plus 26 in 2's complement representation, 0 1 1 0 1 0. What about minus 14? Minus 14 in sign magnitude representation, that would be 1, and we have written 14 here. 0 1 1 1 0 0 1 1 1 0. And what it would be? Minus 14 in 2's complement representation. What that would be? So this one goes here. We will start from the back. 0 1. This would become 0 0 1. Since I got 1, rest all will be complemented. Okay, so that's the thing. So this is our 2's complement representation and this is our 2's complement representation. Now what we need to do? We need to perform the addition. So in these kind of problems, always you will go step by step and you will never be in a hurry. You will solve the questions with the patience. If you are solving it with the patience, you will get the correct answer. Otherwise there would be an issue. So this would be 0 and 1 carry. So the addition I have performed. 0 0 is 1, 1 1 is 0, 1 1 goes here, 1 plus 0 is 1, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0 and 1 carry. So this carry I will ignore. This carry is ignored. So what is the answer? This is the answer. So this is the answer, which is plus 12. You can directly see the answer is plus 12. And if carry is generated, your answer is positive. And you are performing the addition using minimum number of bits. This was 6, this was 5, but we will denote it in 6 only. So what is the maximum of 6 and 5? That is 6. So 6 bits if you are using, but if you are using more bits, then the answer could be different. Then sorry, the answer would be same. If you are using more bits, the answer would be same, but the concept that carry is generated, carry is not generated, that concept will not work. So that concept will work if you are using only the minimum number of bits. Okay, if you are using more bits, then that concept will not work. So generally we will perform the addition using minimum number of bits only, because why should we increase the size? If you are increasing the size, that means you are using more bits, that means you are using more size. So we will not do that. Let's start here. 2's complement representation. So what will be the 2's complement representation of plus 14? Plus 14. That would be this. So okay, plus 14. Sorry. Plus 14. Plus 14 would be 0 0 1 1 1 0. That would be plus 14, right? Because it will be the same as sign magnitude representation. So this sign bit will be 0 and 0 1 1 0 will be same. Now minus 26 in sign magnitude representation, what that would be? So 1 as it is, 1 1 0 1 0, and in 2's complement representation, what that would be? Minus 26. 1 here as it is, 0 1 1 0 0. So that would be in 2's complement representation. So if you perform the addition, what you will get? 0 0 0 0 1 1 1 0 1 0 0 1 1 0 0 0. 1 goes here, 1 1 1 would be 1, 1 goes here, 1 1 would be 0, 1 goes here, and 1 goes here. So what you are getting? Let me check back the calculation again. 0 0, 1 goes here, 1 goes here, 0 1 1. Okay, so this answer you are getting. This was also in 2's complement form only. This was also in 2's complement representation, but it would be equals to the sign magnitude representation since the answer was positive. Now this answer is also in 2's complement representation. This answer is in 2's complement representation, but here you cannot say it is equals to sign magnitude representation, because in 2's complement representation, if first bit is 1, that means this shows negative. So your answer that is coming out to be is 1 1 0 1 0, which is in 2's complement representation. So I need to find it in sign magnitude representation. So what I will do, I will again take that 2's complement. So this will be as it is, 0 0 1. Now all bits are complemented. So this is my sign magnitude representation, and you can directly see it is first bit is of sign, so minus, and 1 1 0 0, that is 12 only. So this is the answer you are getting. So I hope the things are clear, how to do 1's complement calculation and how to do 2's complement calculation. I hope the things are clear to you. Okay, let's see a revision question. This will be a complete revision problem. You need to perform the given operation using 1's complement representation and 2's complement representation. So first you will need to denote it in sign magnitude form, 1's complement form, and 2's complement form. Positive number is also there, negative number is also there. So first you need to denote that, and then you need to perform the addition. So that will be the revision of the previous chapter. So you should be doing it on your own. Previous chapter, I have told you how to represent 28 in sign magnitude representation. How to do it? It would be plus 28. So directly 0 and then 28. What about 1's complement? Let me check it is correct only. 1 2 4 1 2 4 8 16. So 28. Yeah, right. Same will be for 1's, same will be for 2's, because this is a positive number. Same goes for 12. This is your 12. Same for 1's, same for 2's. For minus 28, first bit will be 1. Rest all the magnitude bit. If you take the 2's complement, so sorry 1's complement, then what you will do? Complement each bit, and sign bit will remain there as it is. Here also sign bit will remain there as it is. We will start from here 0 0 1. Since I got 1, rest all bit will be complemented. So 0 0. Same goes for minus 12. So 1 you wrote, 0 1 1 0. These are the magnitude bits. So 1's complement, if you take, this sign bit remains there as it is, and rest all complemented. For 2's complement, sign bit remains as it is. You will start from the back, 0 0 1. 1 will be complemented to 0, 0 will be complemented to 1. Why we are doing so? Because since we get 1, after that we need to complement it. That's it. So this we have already studied in the previous lecture, so you should be able to do it on your own. Let's move towards the calculation. So first we will do 28 plus minus 12. So first one is 28. So plus 28, we can say plus 28 plus minus 12. Okay, so this we need to perform. So now let's solve the first question. So this is the first problem. Plus 28 minus 12. Plus 28 minus 12, that means plus 28 plus minus 12. Okay, so let's solve it with 1's complement representation. So how will you solve it? How will you denote plus 28? Plus 28 in 1's complement, that is 0 1 1 1 0 0, and minus 12 in 1's complement, that is 100 0 11, 110 0 11, 110 0 11. Now what I need to do? I need to perform the binary addition. Binary addition I can do. So although answer I know that would be 16. Answer is 16. That means answer is positive. If answer is positive, that means carry should be generated. So let's see if carry is generated or not. 1, 1, 1, 1, 0, 0 and 1. Yes, carry is generated. And if carry is generated, what do? We add it up. So now we will get the final answer. 0, 0, 0, 0 and finally 1. So this answer is in 1's complement form only, because we have performed 1's complement. We have performed 1's complement addition. So answer will be in 1's complement form only. But since the answer is positive, we can see the sign bit. Since the answer is positive, then we can say 1's complement representation will be equals to sign magnitude representation, or you can say it is equals to the normal form. So you don't need to do anything now. You can directly check this number is, since it is positive, so positive you are getting, and here 1, 2, 4, 8, 16 plus 16. That's the answer. Now let's do it in 2's complement representation. Okay. So 2's complement of plus 28 will be the same as 1's complement. And what about minus 12? That would be 110, 110, 100. 110, 100. Let me check it back. 110, 100. Now you need to perform the addition. Answer is positive. Then what do you think? Carry should be generated. So if carry will be generated here. But if carry is generated, what I need to do? I need to ignore this carry. So after ignoring this carry, what is the final answer we are having? This is the final answer we are having. And here you can see what is the sign bit. Sign bit shows that it is positive. Although the answer is in 2's complement representation, but since the answer is positive, you can say it is equals to the sign magnitude representation, or you can say it is normal form. Okay. So what is the answer? You can see plus 1, 2, 3, 4, 5. So 2 to the power, sorry, 4 zeros are there, no? So 1, 2, 4, 8, 16. So answer is plus 16. So that's it. Okay. So this we have done. Next you need to do it on your own. Then only you should see the solution. Will I be able to do on this page only? 12 minus 28 plus 12 plus minus 28. Do it on your own, then see the solution. So plus 12 will be represented as 00, 11, 00, 00, 11, 00, minus 28 in 1's complement, 1 0 0 11, 1 0 0 11. What will be the answer? Answer will be negative. I can see 12 minus 28. Answer will be negative. But if answer is negative, that means carry will not be generated. So 1, 1, 1, 1, 0, 1. Carry is not generated. But this answer is in 1's complement representation. So if they are asking, write down the final answer in 1's complement representation, you will stop here. This would be the answer. But if they are asking, what will be its sign magnitude representation? What will be its sign magnitude representation? So what you will do? You will again take 1's complement. So 1 here as it is, 1, 0, 0, 0, 0. Again I am taking 1's complement, so I am getting the sign magnitude representation. So this is the sign magnitude representation of this particular number, which we can see first bit is the sign bit, so minus, and rest all the magnitude 1. So answer is minus 16. Right? Let's perform it using, so this was 1's complement. Now we will do it with the 2's complement. So plus 12 will be 0, 0, 1, 1, 0, 0. What about minus 28? So 100, 100, 100, 100. We need to add them up. Since I know answer would be negative, so I should not generate any carry here. Carry would not be generated. Yes, carry is not generated. So this is the answer. So this is in 2's complement representation. Whose 2's complement representation is that? Can you tell me? Whose 2's complement representation is that? This is of minus 16. Why so? Do you remember the special case? If this is written, can I do this thing? I can remove it, because 1, 1 twice is being repeated. Here it was not repeated. Here it is twice being repeated. So whose 2's complement is that? Whose 2's complement is that? Do you remember the case? That is minus 2 to the power 4. Right? 1, 2, 3, 4. Minus 2 to the power 4. So this is the 2's complement of minus 16. Otherwise, if you don't even remember the case how you would do it, you would get 2's complement of that, because this answer is in 2's complement representation. If you need sign magnitude representation, then what you would do? You would get again 2's complement, right? If I need in sign magnitude representation, so what will be the 2's complement of that? It would be same only. It would be same, right? Because you will be keeping the sign bit as it is, and you will start from here 0 0 0 0 and 1. So if you take 2's complement, you get this number, which is in sign magnitude representation. Because if you take that 2's complement of a 2's complement number, then you get the same number. So here 1 will show the sign and rest of bits will show the magnitude. That would be minus 16. So here also you are getting the same answer. But the special case we usually remember, that is minus 2 to the power 4. Are you getting this point? Understandable, right? Okay then, so this is the answer, that is minus 16. So this we have done, and this is also separated. Okay, so yeah, this was a revision question. Everything is being revised here. Special case is also revised, and those normal cases are also revised. Everything is revised. Now, concept of overflow will come. So that is the most important concept. But first we will solve some problem, then we will understand what is the meaning of overflow. So forget about the overflow thing. Don't even look at the heading. Solve these problems using 2's complement representation. You can solve it on your own. Very basic thing. Plus 5. How that will be represented? 0 1 0 1 using 2's complement representation. Yeah, concept of overflow will occur in 2's complement representation only. Why so? Because it has something to do with the carry. Concept of overflow has something to do with the carry, that we will see. And carry, if carry is there in 1's complement, that is added, but here we are ignoring it. So that's the reason it will occur in only 2's complement. Here we are doing something with the carry, no, but here we are not doing anything with the carry. So that is the reason we will get some calculation wrong. How we will get the calculation wrong, how we can make it correct, what is the concept of overflow, that we will see. But it will occur only in 2's complement representation, not in 1's complement representation. Okay, so how will you denote 5? 0 1 0 1, right? How will you denote 6? So 6 in sign magnitude representation will be 1 1 0, right? Because 1 2 4, 6 in sign magnitude representation. And how will you denote minus 6? So 1 1 1 0. Okay, so sign it as it is. And now what you need to do, you need to take 2's complement. So 0 1 0, that would be the 2's complement of minus 6. First I represented it in sign magnitude representation, that would be 1 for the sign and 1 1 0. And then we need to take keep the sign bit as it is and start from here 0 1 and take a complement of that, since you have got 1. So 1 0 1 0. Till now you should be comfortable with all this. You should be comfortable with all these kind of things. Since I know answer would be negative, 5 minus 6, answer should be negative. So if answer is negative, then carry should not be generated. Let's check if we are getting a carry. No, we are not getting any carry. So this is the answer we are getting. So this answer is in what? Certainly the answer will be in 2's complement representation. So this is the answer. If we need to get sign magnitude representation, then we again need to take 2's complement. So what that will be? 1 as it is, start back from here. This one will be complemented, this will be complemented. So answer is what? You can see first bit is for sign and rest bit is for magnitude. So magnitude is 1 and sign bit is 1. So minus 1. So that's the answer. Okay. Look, if we have directly studied these topics, no, it would be very complex. Now you might seem this is easy, but if you study on all those together, then it would be very difficult. But we are breaking down all the things, so it becomes easy for you. So I hope this answer is correct. So what we got? Correct answer. We got correct answer. Here we got the correct answer. We performed the addition using 2's complement representation. We got the correct answer. Minus 1 here, minus 1 here. Let's do this. 6 minus 5. So 6 in sign magnitude, that would be this. And minus 5 in sign magnitude would be this. And what would be the 2's complement? That would be 1 as it is. 1 1 0. This will be 2's complement. 1 0 1 1. That would be 2's complement. Need to add them up. So 1 0 0 and 1. Carry is being generated. Ignore the carry. Ignore the carry. Now this is your final answer, which is in 2's complement form only. But since you can see sign bit is 0, that means this 2's complement representation is equals to sign magnitude representation only. So answer will be plus 1. This will show the what? This will show what? Sign, and this will show the magnitude. So plus 1. That's the answer. So plus 1 here. Correct answer we are getting. Again we are getting the correct answer. right? Till now there is no problem. Let's solve this one. 6 plus 5 is equals to 11. That we know. You need to solve this problem, but using 4 bits. I am telling you need to solve it using 4 bits. So what will be the representation of 6? That would be 0 1 1 0 in 2's complement, because it would be same as sign. And what would be the representation of this? 0 1 0 1, because both are positive numbers. So for both sign magnitude representation and 2's complement representation would be the same, right? Just add them up now. 1 1 0 and 1. Carry generated. Is carry generated? Forget about carry now. Now this is your answer, which is in 2's complement representation. I told you answer will always be in 2's complement representation. You are performing the 2's complement representation. You are performing 2's complement arithmetic. So answer will be in 2's complement only. Carry is not generated, so you know the answer should be positive. But what do you see here? This is in 2's complement representation. Now you need to get the correct answer. If you need to get the actual answer, that means you need to convert it into sign. This answer is in 2's complement representation. So you need to convert it into sign magnitude representation. How will you convert it? By taking the 2's complement again. So 1 will be remaining there as it is. 0, 0 and 1. What does this show? Negative sign. What does this show? Magnitude. What is the magnitude? 1, 2, 4. The magnitude I am getting is 1, 2, 4. Sorry. I am taking 2's complement. Really sorry. How would I take 2's complement? So this one as it is. This one will be copied and rest 2 will be complemented. So 1, this as it is, minus sign. 1 0 1 1 2 4 minus 5. So what you got as the answer? Minus 5. And this answer is incorrect, because answer should be 11. What we did, we did the same thing. Using 4 bits we did the same thing. And then answer will be certainly in 2's complement form. Whatever the answer that you are getting, that has to be in 2's complement form only, because you are performing the 2's complement addition. Here I always told that answer will be 2's complement in form only, but since the answer is positive, it would be equal to SMR. So this answer is also in 2's complement form. You need to take the sign magnitude representation now. So you need to get the sign magnitude representation. Then what you will do? You will take the 2's complement again. So if I take the 2's complement again, what I am getting? Sign bit as it is, and then start from here 1 0 1. This number I am getting. So what is this number is represented in sign magnitude representation. So what is that number? This number is minus 5. So answer you are getting is minus 5, but actual answer is 11. So this answer is wrong. Incorrect answer you are getting. Why that happened? Why that thing happened? We will check it. Or shall I tell it now? Why that happened? Because you are having 4 bits, no? You represented the number in 4 bits. So range of numbers in 2's complement representation using 4 bit. What is that? Using 4 bit, what is the range of number you can represent in 2's complement representation? That would be 2 to the power 4 minus 1 minus 2, 2 to the power 4 minus 1 minus 1. So that would be minus 8 to, here plus sign will be there, minus 8 to plus 7. So using 4 bits you can get these numbers, right? Using 4 bits from minus 8 to 7. And here you need to represent the number in 4 bits only. So if you are representing that number in 4 bits, what is the answer you are getting? Answer is your plus 11. But you cannot represent plus 11 using 4 bits. Using 4 bits, you cannot represent plus 11 in 2's complement representation. That's why you are getting your wrong answer. That means plus 11 and minus 11 does not lie in this range. So using 4 bits doing this calculation is impossible. Doing this calculation using 4 bits is impossible. So that's why you are getting the wrong answer. Here also you will get the wrong answer. Try doing it on your own. So minus 6 in 2's complement form. What that would be? 1 1 0. So 0 1 0 1 1 0 1 0. And what would be minus 5? 1 1 0 1. So 1 1 1 0. So 1 0 1 1. And if you perform it, 1 plus 0 is 1, 0 1 0, and carry is generated. So if carry is generated, you will ignore it. What is the final answer you are getting? What is the final answer you are getting? Here you can see 0. That means this is positive answer. Although this answer is in 2's complement representation, but since you can see initial bit is 0, that means it would be equals to sign magnitude representation only. It would be equals to sign magnitude representation only. So although you can take 2's complement here, if you take 2's complement you will get the same thing. What will be the 2's complement of this? The same thing. So same thing you will get here. So that would be equals to sign magnitude representation. So what will be the sign magnitude representation here? Plus 1, 2, 4 plus 5. So again this is incorrect answer. Why did you get incorrect answer here? Because they are lying out of the range. They are lying out of the range of this. That's why you are getting the incorrect answers. How can I get correct answer? If I represented these bits in 5 bits, using 5 bits, how many numbers you will get? Minus 2 to the power 5 minus 1. That would be minus 2 to the power 4, minus 16 to plus 15. These many numbers you will get. And plus 11 and minus 11 will lie in this range. So if I represent the number in 5 bits and I perform the addition, or if I perform the calculation, you will get the correct answer. Do the same calculation using 5 bits. So what will be the complement, 2's complement using 5 bits? That would be this. And what about this? That would be this. Perform the addition. 1, 1, 0, 1 and this 0 as it is. Here carry is not generated. In this case carry was not generated, answer was negative. Although this concept was working here, answer was wrong, but this concept was working now, that carry is not generated, the answer is negative. Here this calculation could have been done using these bits only, but you are using more bits. So these are not the minimum number of bits you are using. This calculation could have been done in these many bits, but you are using 5 bits here. So this is not the minimum number of bits. So if I say that sir carry is not generated, that means answer should be negative. That concept is wrong here. Why it is wrong? Because you are not performing the calculation using minimum number of bits. You are using more bits. So that's why that carry generated, carry not generated, that concept will not work here. So this answer is in 2's complement form only, but here you can see, what you can see, that my initial bit, sign bit is positive. That means this is equals to sign magnitude representation directly. So directly I can tell the answer. So 0 will tell plus 1, 0, 1, 1, 0, 1. So 1, 2, 4, 8, it is 11 only. So see, you are getting the correct answer. Correct. You perform the same addition using 2's complement representation only, but you used one extra bit. And why is that so? Because range of numbers in 2's complement representation using 5 bits is minus 2 to the power 5 minus 1 to plus 2 to the power 5 minus 1 minus 1. That would be minus 16 to plus 15, and plus 11 and minus 11 lies in this range. Okay, so that's why answer is correct. This answer will also be correct. You need to represent it in using 4 bits. So 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, right? This is correct. I am writing the 2's complement of minus 6. 2's complement of minus 6 using 4 bits is 1, 0, 1, 0. So how it will be using 5 bits? This one will be repeated. 2's complement of minus 5 using 4 bits is 1, 0, 1, 1. So how it will be in 5 bits? That would be 1, 0, 1, 1 and 2 times 1 repeated. 2 times 1 repeated. So just the sign bit gets repeated. In the previous lecture we have seen it. So the previous lecture was the prerequisite of that. Right? So 1 plus 0 is 1. This is 0, 1. 1 plus 0 is 0, 1, sorry, 1 plus 1 is 0 and 1 goes here, 1, and again you are getting 1. So since now you will say that sir, if carry is generated, that means answer should be positive. But no, answer will not be positive. Why so? Because this carry thing will not work here. That will work only with the minimum number of bits. So now this answer you are getting, this is the final answer, but this answer is in 2's complement form. This answer is in 2's complement representation. You need to get it in sign magnitude representation. So what you will do, you will take again 2's complement, because this answer is what? This answer is negative. If the answer is negative, sign magnitude representation and 2's complement representation will not be same. If the question is being asked that we need the final answer in 2's complement representation, then this would be the answer. But if the question is asked we need the final answer in sign magnitude representation, then you need to take 2's complement. So one here, one starting from here, and all are complemented. So what is the final answer? Here you can see it is first bit for sign, so minus 1, 2, 4, 8, 11 only. What you get? Correct answer. So if they are lying in the range, that means the answer is correct, but here the answer is incorrect. Why is that so? Because of overflow. What do you mean by overflow? That means your answer is going out of the range. So here overflow has occurred. Overflow has occurred. Since your answer is getting out of the range, that means we can call that overflow has occurred. Okay. So that's the thing. This is the concept of overflow. We will see a lot more things in this particular concept. We will see more things. So what is the conclusion? If addition of two positive numbers results in negative number, or addition of two negative numbers results in positive number, that means the overflow has occurred. Positive number result is negative, negative number result is positive. So overflow has occurred. Now let's see a question. In the following operation, if the following operations are performed using 2's complement representation, using minimum number of bits possible, then which of them will result in overflow? 3 plus 2 is 5. Look, 3 can be represented in 3 bits. Look, using 3 bits, what will be the range of 2's complement? Using 3 bits. Using 3 bits, what will be the range of 2's complement? Range of 2's complement representation, that would be 2 to the power 3 minus 1, that means minus 4. So minus 4 2 plus 3, that would be minus 4 2 plus 3. Using 4 bits, what that would be? It would be minus 2 to the power 4 minus 1, so minus 2 to the power 3, so minus 8 2 plus 7, minus 8 2 plus 7. So if you perform this addition, you will get answer as 5. 5 will come in this range? No. You can write it using 3 bits. You can write this as using 3 bits. But for this you would need 4 bits, because 5 will come in this range. So for this you would need 4 bits. So overflow will occur here. 3 minus 2. If there are opposite sign, overflow will never occur. Because what will be the answer? 1. For 3 you need 3 bits. For 2 you need 3 bits. For 3 you need 3 bits. For 2 also you need 3 bits. For 1 again you need. It can be represented in 2 bits as well. But in 3 bits it will come. In this range it will certainly come. In this range it will certainly come. Now you will not say that, sir, okay, 2 cannot be represented using 3 bits. So yeah, forget it. So for this as well you need 3 bits. For this as well you need 3 bits. This can be represented in 2 bits as well, or in 3 bits as well it will come. So for this as well you need 3 bits. So overflow will never occur here. And you can see whenever there are opposite sign, here there is plus sign, here there is minus sign, overflow will never occur. In this as well overflow will never occur, because answer is minus 1, that is coming in this range. So here also overflow will never occur. Here overflow will occur, because there are opposite signs, so answer will be minus 5. Answer will be minus 5, that is flowing out of the range. So overflow will occur. 4 plus 2 is 6. So 2 will come in this range. Sorry, yeah. But 4 will not come in this range, so we need to use 4 bits. Basically the thing is, you can represent 4 using 4 bits. Using 3 bits you cannot represent 4. And for this you can represent it using 3 bits only, but we have to use equal bits. So for this as well 4 bits will be required. And where the answer will lie? Okay, answer will lie in this range only. So answer will also lie in this range. Are you getting this point? So plus 4 in this range, using a minimum number of bits. That means using 3 bits you cannot represent plus 4. So you will have to use 4 bits. So you are using 4 bits here. In 2 as well you will use 4 bits. So answer is 6. So that is lying in the 4 bits as well. So there is also no overflow. Although the signs are same here. The signs are same. Still there is no overflow. Here the signs are same. Again minus 5, minus and minus. We need to check, will there be any overflow? What will be the answer? Minus 6. So minus 4 can be represented using 3 bits. Minus 4 can be represented using 3 bits. Minus 2 can be represented using 3 bits. But can minus 6 be represented using 3 bits? No. minus 6 cannot be represented, you need to use 4 bits for that. So overflow will occur here. Opposite signs are there, never overflow will occur. Here plus sign is there, here minus sign is there. Here plus sign is there, here minus sign is there. Overflow will never occur. You do not even need to check for the opposite sign. For opposite sign, overflow will never occur. So you don't need to check. But for the same sign, here plus sign is there, here minus sign is there, here plus sign is there, here minus sign is there. So you need to check that 4 can be represented using 4 bits only, and 2 can be represented using 3 bits, but we need to take the maximum of this. So you need to take 4 bits only. Now what is the final addition? That is 4 bits. So 6 can be represented, sorry, what is the final addition? That is 6. So 6 can be represented using these number of bits. So yeah, answer would be correct. Overflow will not occur here. So in 1, 2, 3, only in 3 conditions overflow will occur. Are you getting this point? So this is how you can check it. You do not need to solve it using binary, or you again and again you do not need to check the complement. If you have the concept clear, in that manner also you can check it. Now we checked the condition of overflow using, like, let's just say only this thing was given, and they asked you whether the concept of overflow will occur or not, and you cannot convert the number into decimal. Here we converted the number into decimal, then we can say the overflow will occur, sir. But what if you cannot convert the number into decimal? By looking at the binary only, you need to tell whether the overflow will occur or not. So how will you do that? How will you do that? So let's check this thing. Okay. So let's take the example of 3 and 2 again. So we will check how we can do it. Okay. That I want to let you know. So here plus 3 minus 2. So what will be plus 3? That would be 0, 1, 1. And what would be minus 2? Minus 2 can be represented as, minus 2 can be represented as this. So what will be like minus 2? For minus 2, what will be 2's complement of that? That would be this only. For minus 2 means 2 to the power 1. So only 1 0 would be there. So this will be the 2's complement of minus 2. But you have to increase sign bit. Why you need to increase sign bit? Because you need to denote both of the numbers in 3 bits. Or you can say like this is the sign bit and 1 0 is the magnitude. Basically what I am doing, minus 2 first you represent in sign magnitude representation. What that would be? 1 here, 1 0. Right? Now I need to take 2's complement. How will I take 2's complement? Sign bit as it is, start from the back, 0 and you get 1. After that there is no number. So this is the 2's complement representation. Or you can write it 1 0 only. 1 0 or 1 1 0. Both are same. So 1 1 0 I am writing. Right? This is the 2's complement representation. Now you need to add them up. So 1 0 0 and 1. Since we are doing it in what do we say, 1 plus 1 is 0. So here there is 1 carry, that also I am writing, and 0 plus 1 and 1 plus 1 is 0 and 1 carry. So you need to ignore the 1. If I ignore the 1, what is the answer I am getting? Plus 1 only. So the answer is correct. Here overflow will not occur. So the final answer we don't need to write. Only we need to check overflow will occur or not. So 2 minus 3 overflow will not occur here. 2 will be 0 0 1. What will be 3? 3 will be 1 0 1. That would be 3 in 2's complement representation. If you perform it, I know overflow will not occur. But 1 plus 1 is 0. 1 goes here, that I have written, and 0 plus 1 is 0. Answer will be minus 1 actually. Okay. So here you can check there is no carry. Here also there is no carry. Okay. Let's see this one. 3 will be 0 1 1. What will be 2? 0 1 0. Perform the addition. Here I know overflow will occur because 5 will go out of the range. 1 0 1 goes here. 1 plus 0 is 1. 1 plus 0 is 1. Here there is no carry. Minus 3 and minus 2. So how will you represent minus 3? 1 0 1. How will you represent minus 2? That would be 1 1 0. Right? Perform the addition. What you will get? 1 1 1 plus 1 is 0, and you get 1 carry here. Here you did not get any carry. Now if I am calling this as C in, okay, and this as C out. If I do this calculation, C in XOR C out, what I am getting here? 1 XOR 1, that is equals to 0. C in XOR C out. Here there was no carry. Here there is no carry. 0 XOR 0 is 0. In both of the conditions, overflow did not occur. Here, if I do this calculation, C in XOR C out. 1 XOR 0. Here there was 0. Here there was 0. Here also this was 0. This is also 0. So C in XOR C out. 1 XOR 0. 1. C in XOR C out. What is that? 0 XOR 1. This scene is known as carry into the MSB bit. This bit is MSB, no? This one MSB. So carry into the MSB bit. And this C out is known as carry out of the MSB bit. Carry out of the MSB bit. So what is the conclusion you are getting from here? If C in XOR C out is equals to 0, that means there is no overflow. Using the bits only, I am not converting the number to decimal. If only this was given, I could have seen here and here. Okay, C in XOR C out is becoming 1. That means certainly if you convert this number into decimal, the overflow will occur. Directly from here only I can tell that C in XOR C out is 1, that means overflow occurs. So this is the important point that we got to know, that you can see from here. There is one more thing. What is that? So this is the first condition, that if this kind of number is there, which I have represented in 2's complement, answer will also be in 2's complement. This is C in, C out I can write here as well. C out I can write here as well. So C in XOR C out would be 1. So that is the condition of overflow. What could be the other condition? There is other way to check it as well. What is that? We will take the overflow example only. 0 and 0, both are positive number. You are getting answer in 1. You can see if this number is represented in 2's complement form. If there is a particular number represented in 2's complement form, let's just say I am saying that this number is represented in 2's complement form. Now I am asking you whether this number is positive or negative. You can tell, sir, certainly this number is positive. And this number is represented in 2's complement form. You do not know what is that number. The only question is, tell me whether this number is positive or negative. You will say that, sir, certainly this number is negative, because first bit will show the sign. You can tell it, no? If this number is given and I am saying that this number is represented in 2's complement form, tell me whether it is positive or negative. You will say, sir, it is positive. If this number is represented in 2's complement form and I am asking you whether it is positive or negative, sir, you will say that, sir, it is certainly negative. So this is a positive number, this is a positive number. In the answer you get 2's complement form only. Certainly you get 2's complement form. And in the answer you are getting negative number. So 0 and 0 is there, but in the answer you are getting 1. Here this is a negative number, this is a negative number, but in the answer you are getting a positive number. 0, 1, 1. That means overflow has occurred. So what I can write here, that if an is 0 and bn is 0 and sn is 1, an is 0, so an 0 means I am writing SOP form. I am writing SOP form. So if it is 0, I will show it an bar. If it is 0, I will show it bn bar. And then if both are 0 and your answer is becoming 1, or if an is 1 and bn is 1, that means both are negative, still your answer is becoming 0. That means overflow has occurred. So one of the condition you need to check, if one of them is working, like if one of the condition is there that C in XOR C out is 1, or 0 0 you get 1 here, or 1 1 you get 0 here, that means overflow has occurred. Overflow has occurred. That's the concept of overflow. So in bits only, if the numbers are represented in bits in 2's complement representation, then how you can directly tell C in XOR C out is 1, or this is this MSB bit 0 0 1 1 1 0. All this is happening with MSB bits. These all are MSB bits. So you just need to focus on MSB bit. You need to see the carry in and carry out. If XOR of both of them is 1, then overflow has occurred, or if this condition is there, that means overflow has occurred. So if the example is given in decimal, then you do not need to convert it to binary and check if the overflow has occurred or not. And if the answer is given in binary only, then you do not need to convert it to decimal and check the answer. Are you getting this point? Although we should not say binary, we should say 2's complement. So basically, if numbers are given in decimal, you do not need to convert it to 2's complement. If numbers are given in 2's complement, you do not need to convert it to decimal. By looking at the final answer, you can tell whether the overflow has occurred or not. I hope the concept is clear, and this concept is confusing to a lot of people, but I tried to bring it down in small pieces, and this is the final conclusion. This is the final conclusion. So everything is clear about this particular chapter. Now let's see what else we have. So these are the questions only. So we can solve these 2 problems would be there. Now we will see why did we studied this particular 2's complement representation calculation or 1's complement representation calculation. Why did we study it? Okay, so the question is given, 2 numbers are represented in binary. Perform P minus Q without converting it to decimal. You need to perform P minus Q. Can you tell me what is this number? Will you say that, sir, it is minus something? No, you will not say that it is minus something. Why you will not say that? Because the number are presented in binary. This is not sign magnitude form. This is binary form. You need to perform the addition. What you need to perform the operation? What is that? P minus Q. You need to subtract 1010 minus 11001. You need to do this operation. Can you do it using binary subtraction? We have studied binary subtraction in last 2 videos, I guess. In last to last, we have studied binary subtraction. Can you do it? I can assume 0 here. So this would be 1. This would be 0, 0. This would be 1 minus 1, 0. Now how will you subtract 0 from 1? How will you subtract? There is nothing to borrow. You cannot subtract, right? So using binary operation, you cannot do this subtraction. So what other methods you are having? You will say that, sir, I have one more method. What is that? Sir, I can use 1's complement representation. So if I am doing using binary subtraction, we are not getting the final answer. But use 1's complement representation. If I use 1's complement representation, then what I need to perform? P minus Q. Or I can write plus P plus minus Q. So what will be your plus P in 1's complement representation? Tell me. Take your time and tell the correct answer. What will be your plus P in 1's complement representation? Look, this particular, without converting it to decimal, this particular number is given. Okay, that will show the magnitude. This number shows the magnitude, right? This number will also show the magnitude. This has nothing to do with the sign. So you know that this is your magnitude. You know the magnitude bits. These are the magnitude bits. Since there is plus sign, there you go. You put 0. These are the magnitude bits which are shown by the binary. Since there is plus sign, I can put one more 0. Now it is plus P. It is in sign magnitude form, which is equals to 2's complement form as well. So sign magnitude representation, which is equals to 2's complement representation. Are you getting this point? But I will add another 0 here because I know this will require more bits. So what will be your plus Q? Sorry, what will be your minus Q in sign magnitude representation? So I know these are the sign. What do I need? Minus Q. That means 1 will be here and this will represent the sign. So 1, 1, 0, 0, 1. So this is your sign magnitude representation. You need to get 2's complement. How will you get? 1, 1 here, 1, 1, 0, 0. So this is your 2's complement representation. So you have denoted plus P and minus Q in 2's complement representation. So now you will perform the, okay, I am doing it using 2's complement. So let's write 2's complement here. Using 2's complement representation. Then I can do it using 1's complement. So this I have converted into 2's complement. Now you can perform the addition. So what you will do? 0, 0, 1, 0, 1, 0 and 1 0 0 1 1 1. So 1 0 0 0 1 and 1. Carry is not generated. Carry is not generated. And what is this answer? This answer is in 2's complement representation. This answer is in 2's complement representation, right? We are performing that 2's complement representation addition. So answer is in 2's complement representation. Now if you need SMR, then what you will do? Sign bit as it is, this here as it is, and again take that 2's complement, right? 1 as it is. So this is 1, this is 1, this is 1, and 1 0. So what is the answer we are getting? Minus 15. So without converting it to decimal, I have got the answer, that is minus 15. And if they are asking like do this operation and write down the final answer in 2's complement form, then this would be the answer. Do this calculation and write down the final answer in sign magnitude form, then this would be the answer. Using binary subtraction, you were not able to do it. Did you understand the concept what we are doing here? Binary number were given, you needed to perform the addition, you needed to perform the subtraction. Let's convert it to binary. What that would be? 1 2 4 8. So that would be 10. This number is 10. So P is actually plus 10. P is 10 only. Why should I write plus 10? P is 10. And what is Q? 1 2 4 8 16. That is 25. Q is 25. So you need to perform 10 minus 25. The numbers are given in P and Q, but you cannot convert it to binary. That is the task. Sorry, you cannot convert it to decimal, because how will your computer perform it? How will your computer perform this calculation? He cannot convert it to decimal because he cannot understand 2, he cannot understand 5, he can understand only 0 and 1. So he is not going to convert it to your computer, your digital circuit. He is not going to convert this number into your decimal number and then perform the addition, and then it will convert it to 2's complement or sign magnitude. This is what your computer will never do, because he cannot understand 25 and 10. So how will your computer perform this addition? This is what the question is asking. So how will your computer will perform this addition? So this is how your computer will perform the addition. What he will see, I cannot subtract P from Q. I cannot subtract P from Q. Then what I can do? I can use 2's complement representation for this particular calculation. So what I will do? I will do plus P plus minus Q. So plus P in sign magnitude form will be the same as this only, and this will represent the magnitude. This is representing magnitude 1 0 1 0. I will put a sign bits are there. So this will be the same 2's complement representation. What about minus Q? So this is representing the magnitude, and since minus sign is there, so one more bit I will put. So this is my sign magnitude representation. If I need to take 2's complement, so this will be my 2's complement. So this is the 2's complement representation, and this is also 2's complement representation. I will simply add it up now. So this is the final answer I am getting, which is in 2's complement representation. So if I convert it to sign magnitude representation, then again I need to take 2's complement, and this is the answer I am getting. So final answer is minus 15. So this is what your computer will do. So if you are an engineer and you need to design a circuit which will do the addition and subtraction of any binary number, then you will use 2's complement. You will not convert it to first decimal and then you will convert it to 2's complement. You will not do this thing. As a designer, if you need to perform the subtraction, what you will do? You will first get the 2's complements and then you will perform the addition. Are you getting this point? So I will design only a adder, and from that adder only I can do the subtraction as well by the help of 2's complement. Is it understandable to you or not? Right? And how will I do 1's complement? The same thing I can do with the 1's complement as well. So plus P in 1's complement representation, what that would be? That is 00 would be there, or 10 only you can put. Since 1's complement representation, sign magnitude representation and 2's complement representation will be same for plus P. What about minus Q in sign magnitude representation? That would be minus Q. So first bit will be sign 1 and then 110 0 1 1 110 1 110 0 1 1 1 0 0 1. So what will be 1's complement representation of this that? So sign bit as it is, and then magnitude of complement of all those. Now you need to perform the addition only. Now it is, I hope it is clear why do we use 1's complement. Like you say, sir, I am smart. If these kind of questions are asked in the examination, first I will convert it to decimal, then I will perform the simple addition subtraction, and then I will get my final answer. You can do it, but your computer cannot do it, and you need to design the computer. So that's the thing. 1 1 and 1, right? So this is the answer, which is in 1's complement form only. This answer is in 1's complement form. So if you need to get the answer in sign magnitude form, then what you need to do? To get the answer in sign magnitude form, this is what you need to do. So this answer will be in sign magnitude representation. So yeah, this is the correct answer. Okay. Now the next one is a gate question. So the subtraction of a binary number y from another binary number x is done by adding x minus y you are doing. What they are doing? X plus 2's complement of, by adding that 2's complement of y to x. 2's complement of y to x. Wait a second. Yeah, so what I was saying, x minus 5 they are doing, so x plus 2's complement of y, this is what they are doing, 2's complement of y. So this is how they are performing the addition, and the results in binary number without overflow, this implies that the result is what? Okay. So what will be, if there is no overflow, that means normal condition is there. So if normal condition is there, then what could be the case? The answer could be negative or positive. So answer could be negative or positive. If answer is negative, answer could be negative or positive. Both the answer will be in 2's complement form. This will also be in 2's complement representation only, and this will also be in 2's complement representation only, right? But if this answer is in 2's complement representation, then you can say that it is in, you can say it is in SMR, sign magnitude representation, or you can say that it is in 2's complement form, or you can say that it is in 1's complement representation as well, or you can say it is in normal form as well. All the same will be, all the form will be same for positive answer. For negative answer, only this is correct. So answer could be negative and in 2's complement form. Answer could be negative in normal form, wrong. But answer could be positive and normal form, yes. Answer could be positive and in normal form. Answer could be positive and 2's complement form, yes. But wait a minute. This was the gate question, and probably all these answer could be correct. But this came in 1987. This came in 1987. In 1987 means like there was no MSQ. So they did not give these answers. Okay, they did not give these answers. They gave only this answer. So answer is, if answer is coming negative, then certainly it will be in 2's complement form. This option would be correct. But they did not give these answers. These should be the answer as well. That if answer is that your result can come positive and it would be in normal form, and your result can come positive and it would be in 2's complement form. Now someone will have one doubt here, that sir, you are doing x plus 2's complement of y. This is what it is written. It done by adding 2's complement of y to x. But here it should be written that sir, 2's complement of minus y, not 2's complement of x. It should be written in that manner, no? That it is done by adding 2's complement of minus y to x. Like tell me, let's just say y in binary is this, y in binary. This is the binary number, okay? Y in binary is this. What will be plus y in SMR? That would be this, right? And what will be minus y in SMR? That would be this. So like sometimes in the questions they can say that I am taking 2's complement of y. That means they mean that they are taking 2's complement of minus y. Are you getting this point? Like sometimes in gate examination it happens that if they are taking 2's complement, like tell me one thing, this is your SMR, right? And this is also your SMR, and this was binary. Aren't both these things same? I can write in this manner as well, no? And this would be equals to 2's complement as well. So if a number is positive, then why would you take 2's complement of that? If number is positive, then the same thing you are getting, no? So sometimes in the examination, if it is written that we are taking 2's complement of y, that means they are considering it that y is already negative. That's why we are taking 2's complement. Here 2's complement will be different. That would be 0 0 1 0 1. So both things are different here. But in that case, both things were no different. Here minus y is there, so both things are different. 2's complement and 2's complement. Both 2's complements are different here. But if we are talking about these two, plus y and minus y, they are the same. So sometimes it may happen that in the examination it would be written that you are taking 2's complement of y. That means they are considering 2's complement of minus y. Okay, it would be rarely that they will ask that 2's complement of a positive number. If they are talking about 2's complement, that means they are talking about negative number only. So it might happen in your examination that you need to think, if they are asking for 2's complement, you need to assume that a negative number, that means first sign bit will be 1. So what is the 2's complement? What is the 2's complement of y? As per them, the 2's complement of y is 0 1 0 0, and this is the sign bit. So they are forgetting the sign bit, and this is their 2's complement. And let's just say x was this 1 0 1 0. So what they are doing, they are taking the 2's complement of y and they are adding that up. So answer is negative and it is in 2's complement form. So this answer would be in 2's complement form. Now let's just say if this number was this 0 0 1 0. So here also there is no carry. Okay, there is no carry. Let's just say if this number is 1 only, and if this number is also 1. So in 2's complement, if this number is 1, so here you can generate a carry. So 1 plus 1 is 0, and this would be the carry. So if carry is generated, then the answer would be positive, and this answer would be in normal form or in 2's complement form. So both C and D could be correct. But wait a second, this carry will go here actually. In our actual calculation, this will be 0 and this carry will go here, and here carry can be generated. So carry is anyway generated only. So certainly C or D both could be correct. Okay, so there is no chance then we can make those incorrect. Certainly both will be, C and D will also be correct, but they did not give the answer. They did not give these options in the answer. They only give B. So if it was coming as MCQ, then I would certainly click on this only, because that's pretty sure that if answer is negative, it will be in 2's complement form only. But here both of the options are being correct, so I will not click on this. But if it is in coming in MSQ, then I will certainly click on C and D as well. Okay. So yeah, this is what they were thinking of this question. So this is a bit controversial question as per me. A lot of teacher would give only these two answers, the positive and in normal form. But if it is in positive, then certainly it is in 2's complement form as well, no? So this should be the answer as well. So all three options are correct. The first one is wrong. Negative and in normal form, that cannot happen. So yeah, that's it from my side about this particular chapter. So this 2's complement chapter we have studied. We have studied the complement arithmetic as well, which is somewhat complex, I know. And people are confused a lot of times in this particular chapter, but I hope we have covered everything in smaller steps. If you are not able to understand this, watch the video again. You will certainly be able to understand. Slowly move forward and it will be all clear to you. Okay then, thank you very much. Now we are going to see an assignment and then we will start our combinational circuits. So we will see the assignment now. Hi everyone, so let's solve our next assignment. So there is assignment PDF available. You must have seen the questions from there and then you need to solve the problems. Okay, so I will quickly show the problems here. These are the problems which will need to be solved. Okay, so yeah, that's it. So let's start with the first one. The minimum decimal equivalent of this particular number would be what? What would be the value of x? The base is not given. Base you have to take. So think one thing. Let's just say this number is written and the same number is written with base 5. Which number will be larger? This one. Why so? Because base is more. So this will have more place value. This will have the place value of 2 to the power 0. But this will have the place value of 2. So this number is 2. But this number will be 5. Because this have the place value of 5. So if more base, that means more value, right? But this x has to be greater than a. Why so? Because a is the biggest number. A is the biggest number. That means x has to be greater than 10. So this 7 1 a, the base, minimum base can be b. Minimum base can be b. If base is minimum, that means you will have the minimum number. So what will be the minimum number? So A is 10. So 10 into B is 11, 11 to the power 0 plus 1 into 11 to the power 1 plus 7 into 11 to the power 2. That would be 10 plus 11 is 21. Now let's do the calculation. 121 into 7 plus 11 plus 10, 21. So 868. So minimum decimal equivalent would be 868. That's the correct answer. Okay, 121 into 7 and plus 21. Okay, yeah, let's move on to the next number. The number of ones present in the binary representation of this. So these kind of questions we have already seen. So 13 into, this is what? This is 16 to the power 3, right? This number is 16 to the power 3 plus there is 0 into 16 to the power 2 plus there will be 7 into 16 to the power 1 plus 0 into 16 to the power 0. Look, you cannot write that, sir, it is plus minus 9 into 16 to the power 0. Minus 9 into 16 to the power 0. You cannot write it. So you will say, sir, my number is 13. 13 means, what is 13? 13 means D. So my number is, sir, D 0, 7 and minus 9. No, all numbers should be positive, no. So here there is 0 to the power 16. So that's the interesting thing in this one. It is 0 into 6 to the power 0 and minus 9 is there. Are you getting this point? This 9 is in decimal. So this number is D070 which is in 16 and minus 9 which is in 10. So this operation you need to perform and whatever the number that you get, that will be your final answer. So what you need to perform? D070. D is 13, no, A, B, C, D. 10, 11, 12, 13. Yeah. D070. D070. 16 minus 9 in decimal. Can you tell me one thing? Can I write it as D070 minus 9 in 16? Because 9 in decimal, you need to convert 9 in decimal to 9 in 16. What you will do? 9 divided by 16. What you will get? Same thing, no? Like, sorry. 16 0 you will get, because you cannot divide 9 by 16, so you will get 9 only, no. 9 in decimal and 9 in hexadecimal will be same, because hexadecimal can extend number up to 15. So 9 in decimal would be equals to 9 in hexadecimal. So this I can write in this manner. So what is my target? My target is to do this calculation. Now can I do the hexadecimal operation? Yes, I can do, because I have studied it. Or what you could have done, you could have converted this into decimal and then perform the calculation, and whatever the answer you get, you could convert that to binary. That you could have done. But this is what not we are going to do here, because I know I can convert decimal to binary very easily. So I am not going to convert this to decimal and perform it. No, I want my final answer in decimal so that I could convert it to binary very easily. So how much I will take from here? 16. This is how I take borrow. In decimal I take borrow of 10. So here I will take borrow of 16. So what I will get? 16 minus 9 is 7. This will be 6. This will be 0. This will be 9. That's it. So the number that was presented here, is this number, D067. So the number is D067. These kind of questions are not asked yet, and certainly I am thinking that this time they will ask minus sign here. So people will be getting confused, but you will not get confused. You just need to perform the operation, nothing else. Just do this thing, write this number and perform the operation. This is the final answer you are getting. So this is the number. So D is 13. 13 can be represented as 1, 2, 4, 8. 1101. 1101. 000. 6 is 42. 124 and 7 is, all numbers should be represented in 4 bits, because 16 is 2 to the power 4. So look, very easily you are able to get this answer. If you have done it by converting it to decimal, then how much long you need to do? Are you getting this point? this much bits will be there. How many bits will be there? 16 bits are there, so it would be very long. But here easily you got the answer. So what is the answer? 1, 2, 3, 4, 5, 6, 7, 8. 8 ones are there. That is the answer. Okay, so that's how we will solve this problem. Let's solve this one. You need to find the base by base x. What did I tell you? Before converting it to decimal, do not do any operation. First convert it to decimal. So what we will get? 1 plus 2x. This number is 1 plus 2x. 1 plus x to the power 0 plus 2 plus x to the power 1. 1 plus 2x. Then log 2 as it is. Before converting it to decimal, I am not going to do anything. So 2 plus 0 plus 2x square plus x cube plus x to the power 4. Can I solve this equation now? Would be very tough for me. So what I can do? Put x equals to 3. I need to put the values only. I cannot do anything. Put x equals to 3. So 7 here. Log 2. 2 plus 3 square is 9. 9 to the 18. 3 cube is 27 and 3 to the power 4 is 81. So log 2. What that would be? 20, 47. 47 plus 81. 47 plus 81. 128. Which is equals to log 2 to the power 7. So you are getting answer as 7 only. Just put the option and perform the operation. So this is correct. That's it. So the base is 3 only. Okay. Write down this number in 1's complement and 2's complement. So point we did not see, but there is nothing change. Okay. If there is a point, then there is nothing change. Okay. The same process we will do. So first our target is to 23.50 in binary. First I will write it to binary, then I will write it to sign magnitude representation, then 1's complement and then 2's complement. So in binary how it would be? So for 23, like I could have done it directly, but let's follow the process. So 23 to binary. So 2, 11, 2 5 ja 10, 1, 2 2 ja 4, 1, 2 1 ja 2 and 0. So it would be 1 0 1 1 1. 1 0 1 1 1 because we go to upward. 1 0 1 1 1. What about 0.50? 0.50 into 2, it would be 1.00. 0.00 into 2 would be 0.00. 0.00 into 2 would be 0.00. So in that manner only it will go. So 0.10. So that's how I will convert it to binary. Now minus 23.50 in sign magnitude representation. In sign magnitude representation, what that would be? 1 sign as it is, then 1 0 1 1 1.10. That would be its sign magnitude representation. This shows the sign bit. This is the sign bit. What will be 1's complement representation? For 1's complement, what you need to do? Sign bit as it is, rest all complemented. That's your 1's complement representation. And what about 2's complement representation? Sign bit as it is, starts from the back, 0, just as you get 1, rest all complemented. There you go. This is 2's complement representation. Okay. So in point doesn't change anything, just the point will come at the same place. It would all be same. So first you convert it to binary, then sign magnitude, and then 1's complement, then 2's complement. Okay. So now before moving on to the next problem, which is this problem, let's solve these two revision problem, or you can say, but just solve it on your own. You need to solve it. The 2's complement representation of q is 1 1 0 1 1 0 1. Then what will be the 2's complement representation of minus q? This is your question. So 2's complement representation of q is this. So what did you get to know? The first thing is this number is negative. Now first I need to get SMR of this. So what I need to do? I need to get 2's complement representation again. I need to get sign magnitude representation. So what I will do? This one as it is and take 2's complement of that. That would be 1 1 I am getting here. So 1 0 0 1 0. So this is the sign magnitude representation. Sign magnitude representation of q. I get to know that this number is minus, this will show minus and this will show the magnitude. This is the magnitude of, this is your q. Q is minus this magnitude. Now what I need to do? I need to write minus q now. What will be my minus q? Our q is minus this magnitude. So what will be minus q? minus q will be a positive number because this is a negative number. So minus q will be a positive number. So for positive number, I will write 0 here. And what will be its magnitude? This will be its magnitude. This will be its magnitude. This I have written sign magnitude representation of minus q. Did you understand this point or not? This is the 2's complement representation of q. I got to know that this is a negative number, but let's take the sign magnitude representation of that. So this is the sign magnitude representation of this. So this I have done. So this is the sign magnitude representation of q. So this number is minus this magnitude. Q is minus this magnitude. So what will be your minus q? So minus q will be a positive number. So that will be 0 and this magnitude. So this is the sign magnitude representation of minus q. And since it is a positive number, that means sign magnitude representation would be equals to 2's complement representation. So this is the final answer. This is the final answer. This is the final answer. So your 2's complement representation of minus q is this. Did you understand this point? Understood? Okay, let's see the next one. 2's complement representation of q is this. This is your q. What is your q? 0, 1, 1, 0, 1, 0 and 100. What do I get to know that? This shows the magnet, this shows the this shows what? This shows the sign and this shows the magnitude. So I know that this is some positive plus some value. So if this is 2's complement, then it would be SMR as well. Since this is 2's complement representation, it is some positive number. So it would be equals to the sign magnitude representation as well. So I get to know that the magnitude of q is this. So what will be your minus q? So your minus q will be in sign magnitude form I am writing. In sign magnitude form I am writing minus q. So minus q is there. This q is positive, then minus q would be negative. So 1 will come and this will show the magnitude. So this is the magnitude. So this is what? Sign magnitude representation. This is your sign magnitude representation. Now if you need to get 2's complement, then you can get the 2's complement. You can get the 2's complement. So what I am writing now? 2's complement representation of minus q. What that would be? So one sign bit as it is. Let's start from the back. 0, 0, 1. After that you need to complement. 1, 0, 1, 0, 0. So this is the final answer. 2's complement representation of minus q is this. Are you able to grasp the concept or not? This will be used in our next particular problem. Okay. Now see carefully. P and Q are represented in signed 2's complement representation. So 2's complement representation is given. PQ is subtracted from P. You need to tell the value obtained in 2's complement form. So if you are seeing this solution directly, then I highly recommend you to go back in the video and see this thing what we have studied. Like a lot of people will be solving assignment problems in a quicker manner, so they would directly come here. But I am telling you, come here as well. Then only you will be able to understand. So what we need to do? Q is subtracted from P. So what we need to calculate? P minus Q. So can I write it in this manner? Plus P plus minus Q. So I need 2's complement of plus P and I need 2's complement of minus Q. But the 2's complement of Q is given. Say yes or no. So I need 2's complement of minus Q. So this is my P. This is my P, which is this. So this is the 2's complement of already given. 2's complement of plus P is already given. Although plus P is a negative value. Plus P is a negative value which I can see. But I need this only. I need the 2's complement of plus P only, which is already given to me. Right? 2's complement representation of plus P is already given. Plus P is a negative value. Plus P is a negative value, but it is already given, which is this. Right? This is the 2's complement representation. But I need to get the 2's complement representation of minus Q. What that would be? So if Q is a negative value, then minus Q would be a positive value. Minus Q would be a positive value. So 2's complement representation of Q is given. What is that? That is 1, 1, 1, 0, 0, 1, 1, 0. I can get the sign magnitude representation if I take 2's complement only. So 1 will be as it is. To get the sign magnitude representation, what I will do? Start from here. So this will be the sign magnitude representation. Sign magnitude representation of Q. So what will be the sign magnitude representation of minus q? That would be this. This is the sign magnitude representation of minus q. And what will be its 2's complement? That would be equals to this only. 2's complement representation of minus q. Say yes or no. Did you understand this point or not? 2's complement already given. 2's complement of minus you need to calculate. 2's complement of q is given. From there, if you need 2's complement, you get the sign magnitude representation. So this is your sign and this is your magnitude. So what you need to do now? Sign will be positive and magnitude will be there as it is. So this is a sign magnitude representation of minus q. You got to know that this is a positive number. So for positive number, sign magnitude representation and 2's complement will be the same. So for this, both will be the same, right? So you need to add these two numbers now. This is your target. 111 0 11 0 1. 111 0 11 0 11 0 1. 11 0 1. 111 0 11 0 1 will be added to 000 11 000 11 010. So let's add that up. So what do we get? 1 1 1 0 1 1 1. 1 plus 1 is 0. This one goes here. This would be 0. This one goes here. This would also be 0. This one goes here. This would also be 0. This one goes here. This would also be 0. And this one we are getting. So this is the final answer you are getting. And this answer is in 2's complement representation. 2's complement representation. This is the final answer. Okay, so this is the final answer that you got. Now let's check if we have done the calculation. What could be the method 2? A dumb method, I would say. Those who haven't studied, they will follow it. How they can do it? P is represented as this. 110. 110 1101 1101. Okay. So this is in 2's complement representation. So what they would have done? Again, they would take 2's complement. So what they will get? They will get the sign magnitude representation now. This is the sign magnitude representation. Then what they will calculate? They will calculate this value, which is this 1 2 4 8 16. That would be minus 19. Right? This number is minus 19. 1 calculation I am doing correctly, no? Yeah, this number is minus 19. What about q? Q, it is given again 111 00 11 111 00 11 single 0. So they again will take 2's complement representation. 1 here 0 1 0 1 1 0 0. So this they will take. So this is their sign magnitude representation. What is that? This is minus 1 2 4 8 16. So this is 26. This number is minus 26. Now what they would do? They would perform P minus Q. They would perform P minus Q. So what they will get? Minus 29 plus 26. What they will get? Plus 7. Now they will convert plus 7 to, they will write sign magnitude representation. What that would be? 0 1 1 1. And it would be same as 2's complement representation. So this is the answer they will get. Same answer they are getting. So this is how you could have solved. But if the numbers are larger, then it would be a problem for you. But here you could have verified in that manner, or you could have solved in that manner as well. But if this question is coming in MCQ, better not waste the time. You will get the correct answer, then just mark it up. Okay. 2's complement of 16-bit number is 4f. The magnitude of the number in decimal is. So 2's complement is written in FFFF. That means what is FFFF? This is hexadecimal, right? It will not be mentioned that it is hexadecimal. You need to understand it. From hexadecimal to I can go to binary. 1 1 1 1. F is 15. 1 1 1 1. 1 1 1 1. Again 1 1 1 1. So what is that? This is basically, this is 2's complement representation. 2's complement representation. This number is 2's complement representation. 2's complement representation of a particular number is FFFF. What do you mean? What do you understand by FFFF? That means this number. This is the 2's complement representation. What you need to find? You need to find the magnitude. So you need to go to sign magnitude representation. You need to go to sign magnitude representation, right? So how will you go to sign magnitude representation? If there is some 2's complement mentioned, you again take the 2's complement of that. You go to sign magnitude representation. So this bit as it is, this bit 1 as it is, rest all will be complemented. So G1, 2, 3, 4, 5, 6. How many zeros will be there? 1 and 2, 16. So total 14 zeros will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So what is this number? This number is minus 1. First bit is for sign, minus, and this is for magnitude. So this number is minus 1. So what is the magnitude? Magnitude is plus 1. This shows the magnitude. This shows the magnitude. So magnitude is 1 only. So answer is this 1. In the following series, some integer is expressed in some different number system. What is x? In the following series, the same integer is expressed in some different number system. It represents the same number. So what do you think, which will have the lowest base? Look, this will have at least base 3. This will have at least base 4. Now you can get confused about two numbers, that sir, this can have base 2 and this can have also base 2. But tell me one thing, if there is same integer, let's just say 7, and 7 is represented as 0, 1, 1. So it is taking it 4 bits, no? So in binary number, it will take the maximum digits, or in binary we can call it bit as well. So let's call it digits only. So if base is low, that means it will take more bits. Base is 2, so it is taking it 4 bits, 3 bits, or you can say 3 bits. If base had been 10, then it would take only 1 bit, that is 7 itself. So certainly this has to be the lowest bit. Sorry, this has to be the lowest base. So let's consider, let first base is 2. First base is 2. So let's just say this has the base 2. So if this has the base 2, what it would become? It is 7 only, right? If this has the base 3, what it would become? 1 has the place value of 3 to the power 0 plus 2 has the place value of 3. So that will be 7 as well. Let's go in the same manner. If this was base 4, hit and trial. Hit and trial. This is hit and trial. If this was base 4, so it would be 3 plus 4, 7 only again. We don't know this. Let's just say if this was base 5, so this could have been base 6. So if this is base 6, then it would be 1 plus 6 into 1, 7 only. So certainly this is base 5. Certainly this is base 5. And the answer I am getting is 7. 7 in hexadecimal. So I need to convert 7 in hexadecimal to base 5. I do not keep any space. So what I can do? Basically I got to know that 7 in, not hexadecimal, sorry, 7 in decimal, really sorry, this is decimal. So 7 in decimal should be converted to 7 in base 5. This is our target. So how will you convert it? 7 base 5, 1 and 2. So what is x? That would be 1, 2. The value of x is equals to 12. That's it. Okay. 1, 2. Value of x will be 1, 2. Find the result of the following operation in 2's complement representation. Could be many ways of doing it. But what I will do, these numbers are small only, no? Let's get them in decimal, perform the simple operation and then convert the number into 2's complement representation. That we should do, right? Because I can convert this into binary, but converting this into binary, first I will convert it to decimal and then I will convert it to binary. So let's not do that. Okay, let's directly convert it. So 1 plus 2 plus 4 plus 7, sorry 8, what I am doing, 1, 2, 4, 8 plus 4 plus 3, 4 into 3, that would be 12. This would be 1 as it is, right? 1 has the place value of 4 to the power 0 plus 4 into 3, that would be 12, plus what about this? 1 has the place value of 5 to the power 0 plus 2 has the place value of 5, 10, and it has place value of 25. It would be 1 plus 10 plus 25. It would be 1 plus 12. It would be 1 plus 4 plus 8. So what you are getting here? 12, 13, 14, 15, 27, 37 plus 25. That would be 62. So you are getting as answer as 62. Right? But let's calculate it again because I don't have much confidence on my calculation. 15 plus 8 is 23 plus 4 27, 37 plus 25, 37 plus 25 is 62. So this is the answer you are getting in decimal, 62 in decimal. It is a positive number, right? So for this, first what I need to do, I will convert it to binary. 62 to binary I will convert. 2 31 0, 2 15 1, 2 7 1, 2 3 1, 2 1 and 1. 62 is this. So it is 1 1 1 1 1 0. This is in binary. Since it is a positive number, so SMR would be equals to 2's complement representation, and that would be equals to 0 here, then 1 1 1 1 1 0. That's it. This is the final answer. So this is the 2's complement representation of the answer. Okay, understood? Very easy problem. So 1 plus 4 plus 8, 1 plus 12 and 1 plus 10 plus 25. 62 you got, you converted that. You can check it here as well. This is 1, 2, 4, 8, 16, 32. So if all were ones, 1, 2, 4, 8, 15. It would be 63 and minus, yeah, it would be 62 only. So this number will be 62. You can check it. Okay. So it is in binary. Since it is positive number, so 2's complement and sign magnitude representation would be same. So this shows the magnitude and there is a sign bit. So that's the answer. Okay. Let's move on to the next one. Find equivalent hexadecimal representation of this number. Hexadecimal representation you need to do. So first you need to convert it to binary. So from gray to binary you are going. Gray to binary you are going. So you are ganda bacha. If you are ganda bacha, you will look down. 1 1 0 1 0 1. So I will look down. 1 is XOR with 1 0, 0 XOR with 0 0, 0 XOR 1 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. Again saying 1 1 XOR 1 0, 0 XOR 0 0, 0 XOR 1 1, 1 XOR 0 1, 1 XOR 1 0. So this is our binary. So this is our number, which is this, right? I need to convert it to hexadecimal now. So grouping of 4. Do not start the group from here. Start the group from this LSB. Okay. And 00 I can put from my side. So this is 1 2 4. So 6 1 2 26. So this is hexadecimal. Okay, very easy. First convert it to binary. Sorry, first convert it to gray, which is 110, and this is 1 2 4. So it would be 6 and 1 2. So it would be 2. 26 it would be in hexadecimal. Find the resultant gray code representation of. Basically this is also base 16. It should be given. This should be given. So let's change the color of pen. It should be given that the base is 16. There is this error from my side. Base is 16. So what we will do? First we can do this calculation on our own. 9b minus 3f. 9b minus 3f. Can we do it? Yeah. B is 12. Sorry, B is 11 and f is 15. F is 15, which is not possible. So I will take plus 16 here. That would be 27. 27 minus 15 will be 13. 13 will be D. So 8 minus 3 is 5. So answer is 5D. 5D. 5D in 16. So 5 in how you will convert it to the gray code. You need the final answer in gray code. So first you need to convert it to binary. So what will be 5? 5 will be, and what will be D? D is what? D is 13, right? Yeah, D is 13. So how you can represent 13? 1, 2, 4, 8. 1, 1, 0, 1. Right? This is binary, sorry. This is your binary. So first we performed the operation, then we converted it to binary. Look here, these operations are useful, no? Okay, I told you you can study all the operations. So if these kind of questions are coming, you will convert it to, first you will convert it to decimal, then you can perform it. Since this is a smaller number, it is possible here. This is a small number. 9b is a small number. 3f is a small number. So you can convert it to decimal, then you convert it to binary. So this is the answer you will get. Okay, I directly did it here. So I am saving the time. In that manner, you can save the time. Okay. Yeah, saving the time, and I did an error, and luckily I caught it. 27 minus 15 is 12, right? 27, 11 plus 16 you will get. So it is 27 minus 15 is 12, and 12 is C, not D. And this would be 8. 8 minus 5 is 3 only. 8 minus 3 is 5 only. Okay, so this would be C. Again checking. 11 plus 16 is 27. 20. So C. It is C. This is C. So this is. So this will be 1100. C is what? C is 12. C is 12. This is 5 only. So 12 is 1100. So what they are saying? Gray code representation of that. So you are going from gray to binary. No, sorry. You are going from binary to gray. So if you are BG, you will never look down. So 0, 1 XOR 0, 1. 0 XOR 1, 1. 1 XOR 0, 1. 1 XOR 1, 0. 1 XOR 1, 0. 0 XOR 1, 1. 0 XOR 0, 0. This is your gray. 1 XOR 0. Sorry. 0 will come as it is. 1 XOR 0, 1. 0 XOR 1, 1. 1 XOR 0, 1. 1 XOR 1, 0. 0. 1 XOR 1, 0. 0 XOR 1, 1. 0 XOR 0, 0. This is the final gray code. Okay. Do the calculation and then convert it. Hopefully I caught the mistake here. Otherwise in the examination it would cost me some time. Let's see this. Perform the following operation and tell the number present in the binary equivalent of the result. So we can do it by both methods, because this number is also easy. Which number is easy? This number is easy. Can you tell which number is that? 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are there. Using 8 bits, what is the maximum number you can get? Say yes or no. Using 2 bits, what was the maximum number I was getting, which was this? So if all are ones, that means this is the maximum number I am getting, which was 2 to the power 2 minus 1. So this was 3. So using 1, 2, 3, 4, 5, 6, 7, 8. Using 8 bits, this is the maximum number you will get, which is 255. Which is 255. So the answer is 255. 255 in decimal divided in decimal. So what we will get? 51. Now you need to convert 51 to your binary. And okay, you need to get the ones. Okay, binary equivalent, and tell the number of ones present in the binary equivalent. So you need to get the binary of that. How many ones are there? Number of ones you need to tell. 25, 1. 12, 1. 2 6 are 12, 0. 2 3 are 6, 0. 2 1 are 1 and 0. So the answer is 11, 00, 11. So number of ones are is equals to 4. Okay. What could be the method 2? Method 2 could be the direct solution, which I have taught you already. So 8 times 1, 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1. And you need to divide by 5. 5 is 101, right? 5 is 101. So first 1 will come. How much you are left with? 0 and 1. Now another 1 will come directly. So again 1 will come. 1, 0, 1. So you are left with 0 now. Now this one has already come. This one will come. Now 0, 1 will not be divided by 101. So another one you require. So 0 you will put here. 1 0 will direct 1 1 2 3 4 1 2 3 4. So this one is coming directly here, but another one I require, so I put 0 here. Now 1 1 is not divided by 1 0 1, so another one I require here, so again 0 I will put. Now this is being divisible, so 1 1 0 1. What I am getting here, 0 and 1. Now this one will come directly, this one will directly come, so again 1, so 1 0 1. So yeah, that's the correct answer. So this is the answer, that's the same as this. So since this number was small and directly you could have told that this is 255, so quickly you could have solved it. So 255 and divided by 5, 51, and then you convert it back, and number of ones are 4 only. Okay, easy problem. In a single byte, how many different signed bit decimal values can be stored? So byte means what? Byte means 8 bits. Okay, you need to remember it. Byte means 8 bits. So using 8 bits, how many different signed numbers you can store? What that would be? 2 to the power 8 minus 1. Look, using 8 bits, how many unsigned you can store? That was 2 to the power 8 minus 1. 255. Now for the rest, we know the range, right? We know the range for the rest. Range for signed number. We remember the range. What was the range? For SMR, what was the range? Minus 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. So what is 2 to the power 7? Which is 128. Yeah, 128. So it would be minus 127 to plus 127. How many these are total number? Minus 127 to plus 127. How many numbers are there between minus 1 to plus 1? If I am writing, how many numbers are total numbers are there? Minus 1, 0 and 1. So total 3 numbers are there. You can say that. But in the signed representation, basically these numbers are minus 127, minus 126 and dot minus 1. There would be minus 0, there would be plus 0 because different representation is there. Then plus 1, plus 2. How many these numbers will be there? These number will be 255 only. Why 255? Why these numbers will be 255? Because, wait a second. Answer will be 256, really sorry. Answer will be 256 because 0 will also be counted, no? Look, this was the range. What was the range for signed number? Range would be for unsigned number. What was the range? Range was from 0 to 255. This was the range. For 8 bits, what will be the possible combination? 0 0 0 0 0 0 0, then 0 0 0 0 0 0 1, then 0 0 0 0 0 1 0 0 0 0. So with respect to each combination, there is one number, no? Whether it is signed, whether it is unsigned, whether it is 1's complement, whether it is 2's complement, whether it is 3's complement, which with respect to each representation, there is a number, no? So if you are having 8 bits, then how many total decimal value you can store? That is 256. You can store 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or you can store minus 127, minus 126, minus 125, and go on minus 1, minus 0, plus 0, 1, 2 in that manner. Or in 2's complement, it would be same. So in 1's complement, it would be same. In 2's complement, what that would be? Minus 127, minus 126, minus 125, minus 3, minus 2, minus 1, 0, 1. But here this number will be minus 128 as well. Here you will get minus 128 as well in 2's complement. So minus 128, minus 127. So there 0 is 1 0 is less there, but this minus 128 is increasing. So whether it is signed number or unsigned number, if you are having 8 bits, then total 256 decimal value you can store. Total these values you can store if you are having 8 bits. So total 256 values you can store. So what is your answer? Answer is 256. These will be 256 actually. Total values are 256. So with respect to each combination, or you can say 2 to the power n. With respect to each combination, you will store one decimal value. With respect to each combination, you will store one decimal value. So answer will be 2 to the power n. So how many total combinations are there? 2 to the power n combinations are there. I hope this is clear to you. Given that largest n bit binary number requires d digits in decimal representation, which of the following is the correct relation between n and d? So let's just say if you are having 1 bit binary number, 1 bit 1 bit number is there. So what that could be? That number could be 0 or 1. So what is the value of D here? D is also 1. N bit binary number requires D digits in decimal representation. That means in decimal representation you only require 1 bit, no? Forget about n equals to 1, n equals to 2. N equals to 2, that means 0 0 0 1 1 0 1 1 1 0 1 1. In decimal it would be written as 0, this would be written as 1, this would be written as 2, this would be written as 3. So how many maximum digits, how many numbers you required? 1 only, no? Only 1 digit you required, no? 1 2 3. 3 is 1 digit. So only 1 digit you required. If n is equals to 3, it would be the same. Let's take n is equals to 4. So in n is equals to 4, there will be total 16 combination. So 0 0 0 0 0 1 0 1 0 and keep on going till 16. Till 16. So this would be 0, this would be 1, this would be 2 and keep on going till 16. So what is the value of D here? D is 2. So let's start this. Here you are getting n equals to D, that is gone. If you put n equals to 2 here and D equals to 1 here, then this is getting correct. So this could be one of the possibility. Here we have cut this. If you put n is equals to 2 here and D is equals to 1 here, so yeah, that is the answer we can expect. But if I put n equals to 3, if I put n equals to 3, so that would be 0 0 0 0 0 1 until 1 1 1. So this is 0, this is 1 and this is 7. So digits is 1. So if I put n equals to 3 here, 3, 2, maximum digit required is 1. So 3 is equals to 2, this is also wrong. So this is also wrong. Okay, let's put this one. D is, let's take the example of this. D is 1 less than n is 2, log tan 2. Log tan 2. What is log tan 2? Which is somewhat around 0.3. So 0.1 is less than 0.6. This is also wrong. This will be correct. You can put all these options will be matched. Okay, you can put any number. Let's take this number. So D is 2, should be greater than n, which is 4 log 2. So it is somewhat around 0.3, so it would be 1.2 only. So 2 is greater than 1.2. So everywhere this will be satisfied. So answer is D. So that's how we can solve these kind of problems, by taking the example and cutting the options. Okay. Yeah, that's it. So this is the end of the assignment. I hope you must have understood a lot of things, and this complete chapter will be working as a prerequisite of our next chapter, that is combinational circuits. So we are going to dive into combinational circuits now. So before studying combinational circuits, I highly recommend you to take one day and revise everything that we have studied in the previous chapters, chapter 1 and chapter 2. So take one day for the revision of the complete chapter 1 and chapter 2 and chapter 3 as well. 3 chapters are there. First one was logic gates and Boolean algebra, then representation and K-map, and now number system and codes and their arithmetics. So till now roughly around 20 hours of content is there. Revise that again, and after that move to the combinational circuit, and now the real digital electronics will start. The actual digital electronics will start now. Like the feel of, I will give you the combination circuit, I will give you the feel of combination circuit. It will not feel like that, sir, we are just solving the standard circuits. No, like we will certainly solve the standard ones, but even that those which are not standard, that also we will solve, and we will go into very depth of the combination circuits. Okay then, so let's start in the next session. Thank you very much. Hi everyone. So in this video we are going to start studying about combinational circuit. So very interesting chapter and very important chapter as well. And before studying this chapter, I highly recommend to revise the previous notes. You need to revise the logic gates, K-maps and Boolean algebra, all those topics, and number system. Then only you should come to combinational circuits. So here we will be using everything that we have previously studied. So what is a combinational circuit? So in the first chapter I told you we will make an IC. And how we will make an IC? By interconnecting the logic gates. So in combinational circuit, this is what we do. We do the interconnection of logic gates. So this would be our IC. And what this interconnection will, why we are doing this? So that in this particular IC, if we give some particular input, it can produce some particular output. So there will be m bit input and it can give us n bit output. Now m and n can take any value. 2 bit input, 1 bit output, 2 bit input, 3 bit output, 4 bit input, 7 bit output, 4 bit input, 1 bit output. So some particular input will be there and some particular output we will get, and these output will depend on the present condition of the input. Let's just say initially my input condition is 1 0 0 1, so these output will depend on these only. Now let's just say my next condition is 1 0 1 1, so these output will depend on 1 0 1 1 only. These output will not depend on previous values. So output only depends on the present value of input. So this is known as combinational circuits. Okay, there is no feedback present here, there is no feedback. From output nothing is going back to input. So output will depend only on the present value of input. So this is known as combinational circuits. Okay, so let's take our first design example. What we need to do here, it is written gray code. Okay, it is written gray code. I hope you will be able to understand. So what you need to do, you need to design a circuit which will detect the decimal number 5 to 10 in a 4-bit gray code. Let's understand what does this want to say. So let's just say you will design this circuit. This circuit I will design. What this circuit will do? This circuit will take 4-bit gray code input. This circuit will take 4-bit gray code input and detects means it will produce one output. How it will produce one output? So let's just say it is taking this gray code input. Now if the decimal equivalent of this particular gray code, let's just say if decimal equivalent of this particular gray code is 6, then your output will be high. Detecting means output is high. How do you detect? Let's just say at the output I connect a bulb. At the output here I connect a bulb. And if the decimal equivalent of this input is 5, then output will be high. That means the bulb will turn on. So detecting means this, output high or low. If I am saying it is detecting, that means output is high. If I am saying it is not detecting, that means output will be low. And let's just say if I apply an input whose decimal equivalent is 1, I apply a gray code input whose decimal equivalent is 1, then what will be your output? Output will be low. Output will be low. And if you connect a bulb here, so here 0 voltage, here also 0 voltage, so there is no voltage, so current will be 0 ampere and bulb will not glow. So this is what you mean by detecting. So you need to find the equivalent gray code from 5 to 10. For decimal value 5, what will be the gray code? Can you tell that? First you will convert it to binary, because directly you cannot write. So first you need to convert it to binary. What that would be? 0 1 0 1. So this is the binary code for 5. What will be its gray code? You are going from binary to gray. You are going from binary to gray. So 0 binary to gray, that means you are busy, that means you will never look down. So 1 XOR 0 1, 0 XOR 1 1, 1 XOR 0 XOR 1 1. So this will be your gray code equivalent. So if your inputs are 0 1 1 1, then this output will be high. This is what this circuit wants to say. Now let's take a random input. Let's take a random input. Let's take a random input as 0 0 1 1. So this is my input 0 0 1 1. Now I am asking you, you have designed this circuit, will this glow or not? Output will be 1 or 0. So tell me, this is the input, this is what? This is a gray code input. Our input is a gray code. So this is a gray code input. What will be its decimal equivalent? We don't know. First we don't know. First we need to convert it to binary. First we need to convert it to binary. If you are GB, if you are Ganda Bacha, you will always look down. So 0 XOR 0 0, 0 XOR 1 1, 1 XOR 1 0. So this is its binary equivalent. This is the binary equivalent, and what does it represent? Number 2. That means this is actually decimal number 2. So this is actually decimal number 2, and if it is 2, it will not glow. Output will be 0. I hope you are getting what we mean here. Now first we will make the truth table, right? And if we know the truth table, we have studied K-maps, we have studied minterm, maxterm. If we have the truth table, then we can write down the output expression. If you remember it, for all, if we see ones, then we will go to SOP. So, and 0 will be our complemented form and 1 will be our normal form, and we will write the expression in SOP if we see only one side of the output. If you remember it, say yes or no, you remember it because you have revised it. So let's start. So these all will be my inputs in gray code. This is the equivalent gray code of 0. This is the equivalent gray code of 1. This is the equivalent gray code of 2. This is the equivalent gray code of 5, 6, 7, 8, 9, 10. How I wrote it? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0. This is how we write the gray codes. For initial 16 values, we have written the gray codes when we study about gray codes. What did I tell you? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0. 2 times 0, 2 times 1, 2 times 1, 2 times 0. 2 times 0, 2 times 1, 2 times 1, 2 times 0. 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Right? So, for which values it will be high? So, if your decimal equivalent is 5, this will be high. If your decimal equivalent is 6, this will be high. 7 high, 8 high, 9 high, and 10 high. For these values it will be high, for rest of the values it will be low only. For these values it will be low. Although I could have written 0 for everyone only, why I am making this dot dot dot? People will get confused. For all these values it will be low, for these 5 values it will be high. Now you need to write down your output. So you can write down your output in this manner. G3 bar plus G3 bar into G2 into G1 plus 0. Sorry. G3 bar into G2 into G1 into G0 plus G3 bar into G2 into G1 bar into G0 plus G3 bar into G2 into G1 bar into G0 bar plus, and in that manner you could have written, right? But this is how we will not do it because it will take a lot of time. What we have K-maps. So we will use K-maps. Let me put the charger. Try making the K-maps on your own and write down the final expression on your own. Then let me put the charger in between. Okay, try doing it on your own. Yeah. So let's start now. So for 0, 1, 1, 0. Look, I have written G3, G2, G1, G0. That means this I am assuming as MSB and this I am assuming as LSB. Because this is how we usually write it. This is the habit we have. This is our MSB, this is our LSB. ABCD in, if you remember it. Right? So G3, 0, 1, 1, 1. 0, 1, 1, 1. That is 1. So 0, 1, 1, 1. This is 1. Now 0, 1, 0, 1. So 0, 1, 0, 1. This is 1. 0, 1, 0, 0. 0, 1, 0, 0. This is 1. 1, 1, 0, 0. 1, 1, 0, 0. This is 1. 1, 1. Sorry, 1, 1, 0, 1. And then 1, 1, 1, 1. So 1, 1, 0, 1 and then 1, 1, 1, 1. So this is what you are getting. Right? This is the K-map you are getting. So here I can see a quad and this is also a quad. So 2 quads I can see. And if we check in this one, so how we will write y? So what do we see here? In the first quad, G2 is the same and here G1 bar is the same. Plus in the second quad, what is same? G0 is same. In the second quad, G0 is same and G2 is same. Right? So this is the final our output. So now I can draw my equivalent circuit. How will I draw my equivalent circuit? So what do I need to do? First I will take the G1 bar. First I will take the bar. G1 bar I need to take. Let's forget it. This is your G1. So G1 bar I am taking and then G2 and then multiplication of both of them. G1 bar into G2. G1 bar into G2 and then here there is G0 into G2 and then there will be addition of both of them. Addition of both of them. Okay, So this input is G1. So here you will get G1 bar. This input is G2, which is same as this input. G2 is same as this input. So you can connect both of them together. So G2 will come here as well, and this input will be G0. So G0, here what you will get, G1 bar into G2, and this will be G0, G2. And if you add them up, this will be your output. G1 bar G2 plus G0 G2. Okay. So what you can do, you can go to the user and you can tell him that, sir, this is your IC. If you put G1, G2 and G0, G1, G2, G0 and G2, if you put these kind of inputs, it will produce an output of, it will produce your high output when the decimal equivalent is 5 to 10. Okay. So this is the IC that you have designed. You can put that in a box and you can tell that, sir, if you put these kind of inputs, it will give you high output for 5 to 10. Let's take another example. You have to design a circuit to detect that decimal number 13579 in a 4-bit 5 to 11 BCD code. So first thing is that we don't know what is 5 to 11 BCD code. So no need to worry. We have studied the BCD code. So we have enough aptitude to understand that. In 8241, what was the meaning of that? That 8421. It is the value of base, right? Place value of 1, place value of 2, place value of 4, place value of 8. So similarly, place value of 1, place value of 1, place value of 2, place value of 5. So it will detect 1357. So this circuit you need to make, and detect means it will give high output or low output. So this is the circuit, I will call it. It is a circuit, and my inputs could be, let's say, what example, A, B, C, D. Okay. So I have taken A, B, C, D as example. So let's just say if my input is 0, 0, 0, 1. So what does this represent? 0, 0, 0, 1, 0, 0, 0, 1. That means this is 1. If this is 1, that means output will be high because it will detect 1. If my input is 0, 0, 1, 1. So what this will represent? 0, 0, 1, 1. What this will represent? 1 plus 1, 2. This will represent 2. So my output will be low. Here output will be high, here output will be low. So in that manner you need to design. So here I am not going to write all the possible inputs. Here I will only write all the inputs which will give me 1. Because I do not need to look at 0. Here I was not looking at 0. I am looking only at 1. So I will write down all the inputs which will give me 1. So which all input will give me 1? Tell me. 5, 2, 1, 1 is there. What we need to detect? 1, 3, 5, 7, 9. So tell me for which inputs we can get 1. 0, 0, 0, 1. Here we will get 1. 0, 0, 1, 0. Here also we will get 1. Now how I can get 3? So 0, 1, 1, 0. 0, 1, 0, 1. This is how I can get 3. What about 5? How I can get 5? 1, 0, 0, 0. This is how I can get 5. How I can get 7? So 1, 1, 0, 0. 5 plus 2, 7. There is another way. 1, 0, 1, 1. How I can get 9? 5 to 7, 8, 9. So 1, 1, 1, 1. So for all these input, your output will be high. And for rest of them, it will be low. You can try on your own. For rest of the inputs, your output will be low. Okay, so for all these inputs, your output will be high. So there are 3, 3, 6, 7, 8 cases. Okay, so let's try making a K-map. So 0, 0, 0, 1. 0, 0, 0, 1. 0, 0, 1, 0. 0, 0, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 0, 1. 0, 1, 0, 1. 1, 0, 0, 0. 1, 0, 0, 0. 1, 0, 0, 0. 1, 1, 0, 0. 1, 1, 0, 0. 1, 0, 1, 1. 1, 0, 1, 1. 1, 1. Sorry, this is 1, 0, 1, 1. Sorry. And luckily 1, 1, 1, 1 is also there. So 1, 1, 1, 1. So this is the K-map we are getting. Very easy K-map. No quad is there. We are not able to make any quad here. But the result will be interesting. Okay, so these are very examples. Okay, these are not standard circuit. So you do not need to mug it up. That what will be the output of the circuit which will detect 13579 in a 4-bit 5 to 11 BCD code. In the examination, you will do it. If this question is coming, you will do it in the examination. You can do this process. You do not need to mug it up the final answer. But in the next lecture onwards, we will study about standard circuit. So there you might need to remember some particular outputs. But that also, there also I will tell you some trick or some way to remember the things. Okay, so no need to worry about that. So here what will be my y or f? If I am writing f, so what will be my f? So in this one if I check, so here a bar is not changing and c bar d, plus in this one if I check, c bar d bar is not changing, c bar d bar is not changing, and a is not changing, a c bar d bar, a c bar d bar. In this one if I check, cd is not changing and a is not changing, so a cd, plus if in this one I check, so here a bar is not changing and c d bar is not changing. So this is your final output, right? This is your output. What you can do in this one, you can take a bar common here, a bar common here, so this would be c bar d plus c d bar, and you can take a common here, it would be c bar d bar plus cd, right? I can write this one as a bar c XOR d plus a c XOR d bar. Say yes or no? So what is your f? Now you need to write down it in, you need to write this on your own. What will be your final f? I think you should do all this process on your own, because this is just the previous chapter thing that we are repeating here. So if you write down this expression, you can reduce it more. So what will be the final expression? So final expression of f is a XOR c XOR d. Say yes or no? A XOR c XOR d, because this is x bar y plus x y bar. So a XOR c XOR d, and since these are three inputs, so I can write it in this manner as well, right? So this could be also one of your answer. Now we need to do the circuit implementation. So how we will do it? Very easy. Just 3 input XOR gate is not possible, I told you already. So we need to make two input XOR gate. So this will be the equivalent circuit ACD. So you can tell them that sir, ACD would be there, and it will in 5 to 11 code it will detect the output 13579. Well and good. So here it is A XOR C, here it is D only. So final output is A XOR C XOR D, which is your output F. Okay, so that's the correct answer. Let's move towards our next design example. So what you need to do, you need to produce 2's complement of a 4-bit binary number, ignore sign bit. Don't do it on your own. Before, like, first you need to see the truth table, then you can do it on your own. So what we are doing, IC is there, we are giving a 4-bit input, 4-bit binary input, and it will produce the 2's complement. 2's complement means there will be 4 outputs only. Say yes or no? If I am giving 4-bit input, what is the 2's complement of 0010? It will be some 4-bit only, no? It will be some 4-bit only. So output will also be in 4-bit. So 4-bit input, 4-bit output. How I am denoting the bits? A, B, C, D only. So A, B, C, D. This is our circuit, which will give output as Y3, Y2, Y1 and Y0. Okay. But there is very like interesting thing. If my input is 0, 0, 1, 0, so what do you expect the 2's complement of that? What is the input? 4-bit binary input. Okay, input is 4-bit binary input. So generally, if they are saying that take 2's complement of a binary input, that means what you will say that sir, for 2's complement, first we need to convert it to sign magnitude form. So I will consider this is 1, and then I will convert it to sign magnitude form, which will be plus 1. So it will be 0, 0, 1, 0. Okay, now it is plus 1. Now I can take 2's complement of that, which will be equal to this only. So you will say that sir, 2's complement of this number is this number. But generally, I will tell you one thing. If they are talking about 2's complement, that means they are talking about negative numbers only. Okay, if they are saying that take 2's complement of a binary number which is this. That means they are expecting that you will take the 2's complement of this, considering here there is bit 1 already. So they are expecting that you will take 2's complement of -2. This is 2 only, no? So if they are saying that take 2's complement of binary number, if they are saying sign magnitude form, then it is different. If they are saying that take 2's complement of binary number this, that means how you will take the 2's complement? 1 as it is and 0 1 1 0, sorry 0 1 and 1 1. So this is the 2's complement. So this is the 2's complement of 0 0 1 0. I am telling you the actual scenario, like how in digital circuit or how digital designers talk. So if they are talking about 2's complement, that means they are already talking about negative number. So 2's complement of a binary number, if they are asking, that means they are considering this number is already negative, this one bit is already there. You need to take 2's complement of this. So how will you take 2's complement of this? 0 1, and since you got 1, you take complement of these two. Okay, so how will I make the truth table? So I am considering this is -0, already 1 is there, already 1 is there. So I will start from the back, 0 0 until I get 0, until I get 1 I will not change anything. So for 0 0 0 it will be 0 only. Here I will start from here until I get 1, until I get 1 I will not complement, after that I will complement. So all these bits will be complemented. I will start from here until I get 1, I got 1, these bits will be complemented. I will start from here, I got 1, so these bits will be complemented. Starting from here 0 0 1, this will be 1. Starting from here all these are complemented. Starting from here these are complemented. So you can see 1 0 0 1 0 0 0 1 1 1 1 0 0 1 1 0 1 0 1 0 0 0 1 0 1 1 0 0 0 1 0 0 and 1 0 0 0. This is the truth. Yeah, so one error I did in the truth table, which is this. So here it should be 1 only, no? So this is one error, 1 0 1 1. So if you do these kind of error, it would be very tough because the whole solution will go wrong. Okay, so what is your y3 in my min terms? If you write it in min terms, that is 1 2 3 4 5 6 7 8 5 6 7 8. So if I represent y3, so what it would be? 1 to 8, no? So 0 1 2 3 4 5 6 7 and 8, right? Min terms. So I can see a quad here. Let's say move it off. It was 1 1 1 1. So I see a quad. I see a quad here. I see a quad here. I see a quad here as well. And this guy will go alone. So for this guy, the expression is A, B bar, C bar, D plus A bar, B plus A bar. Here what is changing? Here A bar is same and what is same? And D is same. Plus in this one, A bar is same and C is same. So if you go in a good interview, these kind of questions will be asked there. A design a circuit, they will not ask the standard circuit, half adder, full adder, because everyone knows it. But here you need to use your own brain. So this is how you will design in front of them, and you will tell that, sir, this will be my output. Now I can design it. Now you can design it very easily, right? A will be there, B bar will be there. You can design it. We will see the design. But since I have the expression, I just need to use the logic gates now. Now what about y2? What about y2? So y2. So 1 2 3 4. At least till 4 it is there. 1 2 3 4. 9 10 11 12. 9 10 11 12. So 1, okay, starting from 1 2 3 4, not from 0. So 1 2 3 4 5 6 7 8 8 9 8 9 10 11 and 12, right? So this is 1, and then I can see quad here. 2 quads I can see directly. One quad is this, and another quad is this. Okay, so what will be your y2? So y2 is b c bar d bar plus b bar plus b bar, and here what is same, b bar d plus here what is same, again b bar is same, and here in this one c is same. So b c bar d bar b bar d. What about y1? So 0 1, so y1 is 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Does something click to you? 0 1 2 3, next is 2 3, next is 4 5 6 6, next is this is 7, this would be 8, this would be 9. Wait a second. 0 1 0 1 2 3 4 4 5, this is 6 7. There is something wrong. Let me check. 0 1 2 5 6 7 8 9 10. Let me check it. Yeah, so nothing is going wrong, everything is going fine only. So we have 0 1 2 3 4 5 6 7 8 9 8 9 10 11 12 13 14 15. So these are the numbers, no, 13 14. So yeah, these are the numbers. So here you can directly see this and this. So what is your y1? y1 seems to be c bar d plus c d bar, which will be c XOR d. Okay. What about y0? What is your y0? Y0 is simply equals to d. Y0 is d only. Say yes or no? If you check, y0 and d both are same, because first will be, at least this bit will be copied as it is, no? So y0 is equals to d. So y0 is equals to d only. I will not have to make the kml. So these are the expression I have got. F3, here I have written F3, but it would be y3, y2, y1, y0. y3, y2, y1 and y0. Okay, so these are the expression I have got. So how will I implement it? Now this circuit will look very complex, so better to represent in this manner. So you have A, this will be A bar, this will be A bar, this will be B bar, this will be C bar, and this will be D bar. Now what you need? A into B bar into C bar into D bar. So A is coming, B bar is coming, C bar is coming, D bar is coming. So this will be A into B bar, C bar, D bar. What else you need? A bar B. So A bar is coming into B is coming. So this is A bar B. Here A bar C, and here it would be A bar D. All will be added and you will get here, what was that? F3, Y3. So you will get Y3. Similarly you can do it for Y2, similarly you can do it for Y1, similarly you can do it for Y0 as well. This will be your Y0, this will be your Y0, this, sorry, D bar, not D bar, Y0 will be this will be your Y0. So you can do the same for Y1 and Y2. Okay, just just the feel of the question I wanted to give you. Okay, just the feeling I wanted to give, that how to solve these kind of problems. So you must have got the feel now, right? Let's move towards our next circuit. So design a combinational circuit which will produce ones complement of 4-bit number. Ignore the sign bit. So ignore the sign bit. You need to represent a ones complement. So ignoring the sign bit, what will be the ones complement of this? All bits will be complemented, no? So these are just a complement. So this will be, all bits will be complemented. All bits will be complemented. 1 0. It would be 1 1 0 1. Simply all the bits will be complemented. So this will be 1 1 1 1 1 0 0 0 0 0 0 0 0 1. All 1 will convert it to 0, all 0 will convert it to 1. 0 0 0 0 1 1 1 1 0 0 0 0 0 1 1 0 0 1 1 0 0 1 1 0 0. This would be 0 1 0 1 0 1 0 1 0 1 0 1 and 0. If you see 0 1 1 0, what will be the two ones complement? 1 0 0 1. That's it. So I am writing ones complement here only. So what did you understand? Y3 is equals to A bar, Y2 is equals to B bar, Y1 is equals to A bar, and Y0 is equals to D bar. So if I am having A, B, C, D as input, so these will be our Y3, Y2, Y1 and Y0. Say yes or no? A, B bar, directly this is the output. This is our ones complementer circuit. Ones complement circuit. Say yes or no? Right? Let's move our next question. Design a combinational circuit which will take 3-bit binary input and produces an output equals to the square of input in binary form. So what we are doing here? 3-bit binary input we will take and you will produce some output. So in output, how many bits will be there? Give me the answer. In output, how many bits will be there? Let's check it. So let's just say if this is my input, what this circuit is doing, which will take 3-bit binary input and produces an output equal to the square of the input. Equal to the square of the input. So this is, what is this? This is 1. In decimal, this is 1, right? What is the square of 1? 1 only. So your output will be 0, 1, 1. If your input is 0, 1, 1, so what is this number? This number is 3. What is the square of 3? That is 9. So what will be your output? Output will be 9. How can you represent 9? 0, 1, 0, 0, 1. So for that you require 4 bits, right? If my input is 1, 1, 1, what is this number? This number is 7. What is the square of 7? That is 49. To represent 49, how many bits you require? Think and tell me about it. 6, right? Because with 6 digits, what is the maximum? With 4 digit, what is the maximum number you can get? 15. That is 2 to the power 1 minus 4. With 5 digits, you will get 2 to the power 5 minus 1. That is 31. Here you will get 15. With 6 digits, you can get 2 to the power 6 is 63. 63 minus 2 to the power 6 is 64. So 64 minus 1, which is 63. So 49 cannot be covered in 5 bits. You need 6 bits. So output will be of 6 bits. Output will be of what? It will be of 6 bits. So output will be of 6 bits. 1, 2, 3, 4, 5 and 6. So output will be of 6 bit. Y5, Y4, Y3, Y2, Y1 and Y0. Okay, and this is your input, which I must have written in ABC. ABC. So let's check it out. So this is decimal equivalent 1, 0, 1, 2, 3, 4, 5, 6 and 7. Square of 0 is 0 only. Square of 1 is 1 only. Square of 2 is 4. So this is 1, 2, 4, 8, 16, 32. Square of 3 is 9. 9. Square of 4 is 16. Square of 5 is 25. 0, 25. So 1, 1, 0, 0, 1. So 16 plus 8 is 24. 24 plus 1 is 25. 36. So 32 plus 4. and 49. 49. So 32 plus 16 is what? 48, right? So 1 1 0 0 0 1. Okay, well and good, no issue. Now tell me one thing, will I make the K-map here? No, for y5, if I need to write down y5, what that y5 would be? Y5 would be a into b into c bar plus a into b into c, right? y5 it is 1 here only. So a into b into c bar plus a into b into c, which can be reduced to ab. This is your y5. Well and good. Okay, next I have only example only. So this is your y5. What about y4? So for y4 you can see a into b bar into c bar plus a into b bar into c, b bar into c. So you can take ab bar. So c plus c bar is 1. C plus c bar is 1. This is your y4. What about y5? What about, no, sorry, what about y3? What about y3? What about y3? So a bar into bc plus y5, a bar into bc plus a into b bar into c, b bar into c, a bar into bc plus a into b bar into c, a into b bar into c. Okay, so a XOR b into c, a XOR b into c. What about y2? y2, so this is your a bar b c bar, a bar b c bar plus a b c bar, a b c bar. So bc bar, a plus a bar is 1. What about y1? y1 is always 0. And what about y0? y0 is equals to c, 0 1 0 1 0 1 0 1, y0 is equals to c. That's it. So these all are the expressions. This is the expression, this is the expression of y2, y1, y0. So you can implement that. I am not implementing. How will you implement y1? Simply you will ground it. This is your y1. y1 is 0, so you will simply ground it. Okay, y0 is c, y4 is a b bar, y3 is a XOR b into c, and y5 is ab. Okay, that's it. Okay, this is the answer. Let's see the next question. Design a combinational circuit which takes two 2-bit binary input. Two 2-bit binary input. That means it will take two inputs. It will take two inputs, but every input will have 2 bits. That means it will take the input A and B. Let's just say it will take the input A and B. So this input A and B, these inputs will be of 2 bits. These inputs will also be of 2 bits. So these inputs will be A1, A0. Same goes for this B. These inputs will be B1, B0. So better we should represent it like this. So A have 0 to 1, B have 0 to 1, B0, B1. So two inputs are there and it will produce a single output. It will produce a single output. The output will be high. The output will be high when the decimal equivalent of the input is, when the decimal equivalent of the input is circuit A even odd number and circuit B, A is for odd number. Two questions are there. First one is for odd number and second one is for even number. What they are saying, 2 bits produce a single output. The output will be high if the decimal equivalent of the input is, decimal equivalent of the input is, of the sum of the input is. Okay, really sorry for all these blunders. Of the sum of the input is, of the sum of the input is, of the binary sum of the input is. So let's just say this is my input 0 1 1 0. I am saying A1 is my MSB and A0 is my LSB. So what does this represent? 1. And what does this represent? 2. 1 plus 2 is 3. So what it is? 3. So if it is an odd number, it will be high. This is what our first question is saying. Our second question is saying, let's just say if this was my 1 0, 1 0. So this is my MSB. So this is 2. This is also 2. 2 plus 2 is 4. So in the second question, this one will be lit. Okay, if this is the input, in the second question it will be lit, and if this is the input, in the first question it will be lit. I hope you must have understood the problem. So let's write down all the possible combination. So what all can happen? That 0 0 is 0 0 is added with 0 0, 0 1 is added with 0 0, 1 0 is added with 0 0, and 1 1 is added with 0 0. So all the possible combination of 4 bits we have written. That 0 0 is added with 0 0, 0 is added with 0 1, 0 0 is added with 1 0, 0 0 is added with 1 1, 0 1 is added with 0 0, 0 1 is added with 0 1. So basically all the 16 possible combination I have written. 8 times 0, 8 times 1, 4 times 0, 4 times 1, 4 times 0, 4 times 1. Because anything can be coming into the input side. 2 times 0, 2 times 1. So 0 0 is added with 0 0. What will be the sum? 0. 0 0 is added with 0 1. What will be the sum? 1. 0 0 is added with 1 0. So this has the place value of 1, this has the place value of 1. Sorry, 2. This has the place value of 1, this has the place value of 2. So 0 plus 2, 2. 0 plus 3, 3. 1 plus 0, 1. 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. 1 plus 3, 4. 2 plus 0, 2. 2 plus 1, 3. 2 plus 2, 4. 2 plus 3, 5. 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, sorry, yeah, 3 plus 2, 5. 3 plus 3, 6. I hope the addition is fine. 1 2 3, 1 2 3 4, 2 3 4, 5, 3 4 5 6. Okay. So what is about YA? YA will lit for odd number. This is for odd, and YB for even. Let's check the odd number. 0 is not a odd number, so this will be 0. This will be 1. This will be 0. This will be 1. This will be 1. This will be 0. This will be 1. This will be 0. This will be 0. This will be 1. This will be 0. This will be 1. This will be 1. This will be 0. This will be 1, and this will be 0. Let's check back again. 0. Let's solve this one. Even 0 1 1 0 0 1 0 1 1 0 1 0 0 1 0 and 1. So these will be just the complement of each other, no? This will be just the complement. YA would be complement of YB, right? Because this will lit for odd, this will lit for even, so both are complemented only. Very easy thing. So all these are correct only, right? If these are coming complement only, so I hope I have written it correctly. Okay, so we can either find it for YA or we can find it for YB. Let's try for YA. So what is your YA in terms of min terms? So that is 1 3 4, 1 3 4 6, 1 3 4 6, 9 11 12 14, 9 11 12 14. So 1 3 4 6 9. So this schema I will not draw. Start from 1 1 3 4 6 7 9 10 11 12 13 14. So what about this? So this is a chord I can make. And this is the chord I can make. So I can make 2 chords. Okay. So what will be your, this is for YA. So what will be your YA? What do you think? So here in this chord, which one is constant? Y0 is constant, and y naught is constant and y2 bar is constant, plus in this quad y naught bar is constant and y2 is constant. So what you are getting, y naught XOR y2. So this is your ya. Ya is y naught XOR y2. So what will be your yb? Yb will simply be y naught x nor y2. So we did all this calculation, then we got to know that our answer is very straightforward. So what will be the design? So these kind of questions can come in your examination. They can simply ask you the output. So there you will have to do all these calculations, the 0 0 0 0 1 1. So for which one it will be even or odd. So in that manner you need to do the calculation. So and then simply an inverter after that, and this is your y naught, this is your y2. So this will be your ya and this will be your yb. Well and good. Are you getting this point? Or how I could have designed it? What I could have done is that 3-bit input is not possible actually. So what I could have done is that this, no sorry, here I will get y naught XOR y2, right? And then another, if I am having another XOR gate, this I could have done. Here I will put y naught, here I will put y2, and here I will put control, and this is my final output, final output, which I am denoting as y. So if C is 0, then my y would be y naught XOR y2, and if C is 1, what will happen? Here you are getting y naught XOR y2, right? XOR with 0 will be this. XOR with 1, what that would be? Y naught XOR y2 XOR with 1 will be the bar of that. And what will be the bar of that? It would be this. So this is known as control unit. So which you can put at input. Okay. So you will put that in a box and you will keep this bit outside. Keep this bit outside. This bit is C. This bit is C. So you will keep this bit outside C and you will tell to the user that, sir, if you put C equals to 0, no, then your output will show that your sum is odd, right? Sir, if you put C equals to 0, your output will show that the sum is odd, and if you put C equals to 1, then your output will show that the sum is even. This is what you can tell to your user, that sir, there are 3 inputs, y naught, y2, and C is the control bit. If you put C equals to 0, then this should be the output. If you put C equals to 1, then this should be the output. So this is how also you can design the circuit. Okay, just a way I am telling. So in that manner you can design it. And in the examination these kind of questions can come. Okay, so you should be aware of that. For YB we are not doing, we are only doing for YA, because we know YA this will simply be complemented. So let's solve this question. You need to design a 3-bit for a 3-bit input, design a combinational circuit which detects majority number of 1 or minority number of 0. Both are same thing, no? If 1 is in majority, that means 0 will be in minority. So for a 3-bit input, you need to design a combinational circuit which will detect majority number of 1s or minority number of 0. That means if my input is 0 0 1, here what I am designing majority number of 1. So here 1 bit is coming 1 time only and 0 bit is coming 2 times. That means it will be low. If my input is 0 1 1, then 1 bit is coming 2 times and 0 bit is coming 1 time. That means my output will be 1. So this is the meaning of question A. Question B is just opposite of that, right? Majority number of zeros, that means minority number of 1. Are you getting this point? So let's write down all the possible condition. This could be the possible condition. So if here what is the majority? Majority is 0 only. What is this? This is majority number of ones. Majority number of ones. And this is majority number of zeros. Number of zeros. So here 0 is in majority, 1 is not even there. So this is 0. Here 0 is in majority. So again this will not be high. Here also 0 is in majority, this will also not be high. Here 1 is in majority, high. Here again 0 is in majority, not high. Here 1 is in majority. Here also 1 is in majority. Here also 1 is in majority. And for this, here zeros are in majority, zeros are in majority, zeros are in majority. Here 1 is in the majority, zeros are in majority, and rest all will be 0. So if you can solve it with SOP as well, you can solve it with POS as well. But you will get a very interesting result here. YA is M 3, 5, 6, 7. And let's try solving YA. You will get a very interesting result, which you will remember as well. Okay. So A, B, C. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, and 3. This is your A bar A. This is your B bar C bar, B bar C, BC, BC bar. So what is your Y? Y is BC plus, here A is constant and C is constant, plus AC. Here A is constant and B is constant. So AB. So Y is AB plus BC plus CA. Do you remember anything about this expression? Do you remember anything about this expression? This is a self dual function, right? Self dual function. If I have written YA in this manner, okay, let's not do it. We will again make the K-map. So this is one of the expression. Let's make the K-map again. Now I am doing it with the SOP. No, I have already done it with SOP. Now I will do it with POS. So this is A plus B plus C. So this will be A, this will be A bar. This will be 0 0, sorry. B plus C, B plus C bar, B bar plus C bar, B bar plus C. So where 0 will come? 0 0 0 and 0, right? One, 2, and then 3. So Y is equals to A plus B. I am writing for this one, A plus B into B plus C, and let's write for this one. Here C is constant and A is constant, so C plus A. So A plus B into B plus C into C plus A. So Y, which we got, AB plus BC plus CA, all are equivalent only. I am again making it for YA only. This was for YA, this is also for YA only. So this is your YA. Again this is your YA only. So YA has got two expression till now, this one and this one. So will you be able to remember it? AB plus BC plus CA is equivalent to A plus B into B plus C into C plus A, right? Okay, now one more expressions we can get. How we can get more expressions? So again let's write down this thing. So A bar A, B bar C bar, B bar C, BC, BC bar. 1 1 1 1. I will do very interesting thing. What I will do, I will just make this, okay, and I will keep them alone. Let's see what we get. This is not the minimized term, that's for sure. This is not the minimized term, but let's see, we will get something interesting here. What is that? Y is equals to BC plus, what about this? It would be A B bar C. What about this? This would be A B C bar. So what I am getting? BC plus A as common, this would be B bar C plus BC bar. So it would be equals to BC plus A into B XOR C. So one more Y expression you got, that is BC plus A into B XOR C. You can do the same thing for AB. What you can do? One more thing I will show you. So let's remove it off because you already know this is already written here. Okay. So what you can do is that same example is there, 1 1 1 1. This is A bar, this is A. So what I will do is that now I will keep A and another number, that is C. Let's keep A and B as constant. Okay, let's keep B, A and B as constant. So we are keeping these two constant, this and then this. If you remember, we solved an example like this as well in assignment problem. So there I told you that later on I will tell you why they are equivalent. So now I am telling you why they are equivalent. So if I am doing this example, so here for this pair A and B are constant. For this pair A B bar C, and for this pair A bar B C. So A B C can come common, A B bar plus A bar B. So what is the answer you are getting? A B plus C A XOR B. Right? So this is your Y. Similarly, Y could be, for BC we have done, so AC plus B A XOR C, and Y is BC plus A B XOR C. Also your Y is AB plus BC plus CA. Also your Y is A plus B into B plus C into C plus A, and also your Y is summation M 3 5 6 7, and all these are same only. And if you remember in self dual, I told you this is a self dual function, because if this is the dual of it, no, dual hai, this is the dual, right? This is dual, this is the dual of it, and this is same. So this is a self dual function as well, self dual function. Okay, now let's talk about YB. If I talk about YB, so YB is equals to YA bar. And what is YA? YA is AB plus BC plus CA, AB plus BC plus CA, and it is self dual function. If it is self dual function, then do you remember, if it is self dual, then what will be its bar? So first we take the dual and then we take individual complement. First we take dual and then we take individual complement. If you need to go from here to here, what you will do? First you take the dual and then you take individual complement. If you remember it, right? First you take dual and then you take individual component. So dual of this will be this number only. Now I need to take complement of that. So what I will do? Individual complement. So this I have already taught in that chapter where we studied about duals. So this could be one of the expression, or what could be the other expression? This same expression is there, no? A plus B plus B plus C plus C plus A. Dual of this will be the same value. Dual of this will be the same value. Then I can take individual complement. Tell me one thing, that this is also YB. The other expression of YA is this, AB plus C A XOR B. Now if I am saying that take the complement, so what I am doing, since I know this is self dual function, so I can take individual complement now. Is that correct? Is that correct, that I take this complement? No, you need to take individual complement. So this complement you will take, and if there are two complements, that means both complements will get cancelled. So basically complement to complement, this will get cancelled, no? A, this how you can write, A XOR B bar, then another bar is there, so another bar, this will get cancelled, so A XOR B you will get, so this will be A XOR B only. So individual you component you need to take. I have seen like people generally will take this is the complement, individual complement. So this will again be A XOR B only. So what could be the other expression of YB? That would be A bar B bar plus C bar A XOR B. It could be A bar C bar plus B bar A XOR C. It could be B bar plus C bar A bar B XOR C. So YB and YB. What else YB is? Summation M. This you might not be able to remember, so no worry, even I don't remember this. But I remember this one, 3, 5, 6, 7. So which is 0, 1, 2, 4. 0, 1, 2, 4. So this is your YB. Are you getting this point? So these many expressions we can write. Right? So what is the conclusion? Majority number of ones detector, that is 3, 5, 6, 7, and majority number of zeros detector is 0, 1, 2, 4. These are the expression, these are the output expression. AB plus BC plus CA, A plus B into B plus C into C plus A, AB plus C A XOR B. Which of them are the most important ones? This is the most important one, okay? And AB, this one is most important. So I hope from now onwards you will remember this. So all these expressions can be written in these manners, because in MSQ these kind of questions will be coming. In MSQ they can frame a lot of problems and a lot of options, then they can say which of them are equivalent. So that's the thing, okay? So I hope this lecture is clear and you are building the basics of our combinational circuit. So you have built the basic that what we are going to do in the combinational circuit. None of them was a standard circuit, and no one will actually teach you all these kind of circuits. They do not really teach these kind of circuits because they think that this is not standard. But we also need to deal non-standard circuit as well, because they can come in your examination. Standards will come, but non-standard we have to deal. So we have dealt it in very first lecture only, so that your concept building up is good. Okay, then no answer you need to mug up. Okay, you do not need to mug up these values, you do not need to mug up these values. Here you also do not need to mug up these answers. Okay, you don't need to mug it up. Even I don't remember the final output, but in the last one, when I told you majority number of ones detector or majority number of zeros detector, then you can keep it in mind. If you forget it as well, then you can quickly derive it as well in the examination. You will see 3, 5, 6, 7. Okay, that's it. This is AB plus BC plus CA, and there are more expression that I know. A plus B into B plus C into C plus A, or AB plus C A XOR B, AC plus B A XOR C, BC plus A XOR B XOR C. Okay, and same for the dual. It is a self dual function, so this thing happens. So this is a very important function. That's why we are dealing it here. Okay, then. So yeah, that's it from my side. Let's meet you in the next lecture where we will study about the standard circuits. Okay, then. Yeah, thank you very much.